ग्रोवर साहब का भी है ना?
हाँ, डाउनलोड हो गया।
डाउनलोड किया?
हाँ,
चेक किया ना?
नॉट, अदरवाइज इसमें है।
नहीं, आपका डाउनलोड करके लोड भी किया
जो आपको भेजा।
नहीं, आज सुबह भेजा।
हाँ हाँ,
सुबह, आज सुबह वाला ही किया ना?
हाँ, चेक कर लीजिए।
हाँ, बट यू विल जस्ट चेक। नहीं तो ये इनका सर का अभी का ले लो।
It's not even reading. Just now I copied.
वापस निकाल के डाल दो। ओ, आइडेंटिफाई नहीं कर रहे।
Oh my God.
डाउनलोडेड सुबह वाला किया है तो चलो रखिए।
किसी बंद कर दो, बंद। Just reset everything. It's not even coming. This is not coming.
इसको देखो, ये डिटेक्ट कर रहा है। लूज करेगा।
एनकेएम दिखा दिया ना, एनकेएम देखो, एनकेएम पहले एनकेएम लगेगा। जी क्यों
एनकेएम इधर लैंडमार्क से।
हाँ हाँ, दैट वन। अच्छा है ना सब है।
पेस्ट
ठीक है ना, चेक कर लेंगे। एक बार देखो, फर्स्ट पेज हो गया, बस 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 ठीक है। ग्रोवर
सबका
है ना, मेरा हो गया।
हाँ, हो गया सर, थैंक यू।
उसमें नहीं है।
नहीं है तो कॉपी करो अभी। एक क्या है, एचबीसी नहीं, अरविंद कुमार नहीं, अभी सर का अभी कर लो नाम।
एक मिनट, पहले इजेक्ट कर देता हूँ ये।
मंडल साहब को दे दो। हाँ, मंडल साहब को। कॉपी। डबल क्लिक।
ठीक है, कुछ
हाउ मेनी आर देयर स्लाइड्स? हाँ, ठीक है।
थँक्यू सर. कोण आता फक्त आमच्या सर राहिले, त्यांची फाईल अजून आलेली नाही, म्हणजे
ह्यांचं झालं का आपला फोन यार
आता व्हायचे आले. हा, आली पण आली फायनल प्रोग्राम.
हाँ ये है ना, ये
व्हायचं का? आय एम सॉरी फॉर द एरर. नहीं तो
हाँ
बस
आ गया ना?
आ गया.
अभी आया. यस सर, अभी आया. आपका राह देख रहा था. वेटिंग फॉर योर अराइवल. 15 मिनिटं झाले. सेंड करून, मेल सेंड करून वाया जावा नाही.
हो,
है ना क्या
डाउनलोड केलं नाही. डाउनलोड मी इथे ना वरती. हाँ हाँ, तो आणते ना.
नहीं हो पाएगा
डायरेक्ट डेस्कटॉप में कर दीजिए. पेस्ट नहीं आना. ठीक है ना, पर कॉपी टू
दोनों में
आणते आ गया.
अभी बंद करो यार, अभी चालू करता हूँ.
चलो, यूट्यूब चालू किया उसमें.
ये ANTI
एक्स्ट्रा है।
ये TIFR 2 कौन किसका है?
नहीं उनका है, लेकिन उसको मैंने रिनेम किया है,
हाँ,
ये इसको डिलीट कर
तो
देता
ठीक है। और मेरा खोल के रखो। यस
हूँ।
सर का भी रखो,
हाँ नहीं वो बात
बेंगलुरु सर का।
यस। सो प्रभु इज सेइंग दिस टुडे, विल यू से दैट फर्स्ट? ओके। Yeah, first two talks you don't bother. Vaya 15 minutes you should bother. Generally you don't bother. After that is only. No, but where you are? These two things.
Myself.
ऊपर नहीं, Facebook पे। Yes. बस मजा लेक्चर चालू
शेयर करूँ थोड़ा,
हाँ
शेयर करूँ।
ओपन करा सर, शेयर कर वाया है ना। हाँ
So I just tell the speaker, na,
हाँ
5 minutes.
यस 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 ओके। ऑनलाइन कोई हाई कितने मालूम है क्या?
5 participants, 5 participants.
Can we settle down?
हाँ
शेयर नहीं करो।
नहीं शेयर है चालू, स्टॉप शेयर बोलेंगे, शेयर तो क्या है?
डेस्कटॉप पर शेयर करो। बहुत ओके करना।
अरे
वहाँ से इसने किया।
शेयर स्क्रीन करना, पूर्ण स्क्रीन पर बस मुझे देखा है। ठीक
रेडी?
हाँ ठीक है।
After
Yeah, I'm waiting here.
okay. Okay, good morning all of you, and welcome to TIFR alumni function. I'm Prabhu, Secretary of TIFR, currently in the Department of Condensed Physics and Material Science at the Kollam TIFR campus. And it gives me a great pleasure to welcome all the dignitaries, delegates, friends, and our former colleagues and well-wishers of TIFR for this grand occasion. Welcome all the alumni members. Please feel at home because this is your function. I wish to take this opportunity to thank all those who helped this happen. And also, there is an exhibition by Anna, and we strongly encourage all of you to visit this and help this organization, which is just near Afghan Church, which many of you must have seen for many years. It has been going on. And now, on behalf of team, I thank the various contributions from Amplitude Corporation France, which is Advanced Photonics, Mumbai, Laser Science, Coriolis, RIP GmbH Germany, and General Help of TIFR Tunela. And I welcome Professor Mahmoud Raya, President of TIFR Alumni Association, to initiate this meeting. Professor Raya, please go. Good morning, it's a pleasure to be here. And what I want to do is to talk about a bit of sort of look back at who we are and what we are as soon as I can get important. So, TIFR is a statement of purpose which not many of us know. The TIFR's official statement of purpose is that TIFR should be dedicated to the pursuit of excellence in fundamental science and mathematics. We should pursue research which should bring prestige to India and occasionally even material benefits to India. We should nurture young scientists and we should have responsibility in science education. So that is what this institute is supposed to be. Today, TIFR, of course, has spent 75 years. We have done some large experiments, some small experiments. Some will be discussed here, some will not be discussed here. And over the next 2 days, we will discuss at least the major programs that have happened in TIFR last 2 years. But there are many, many small ones which we have not been able to
accommodating this program. So I think at the beginning of this session, we should try and remember some of those activities which will not be presented here. These are not even going to be acknowledged. It's a pity because they're in their own very creative activities. So let me mention those who we will not have time to discuss. I'm not going to what I will mention in this details or some of the things that you will find here. I will not mention simply because there are full talks about it as time comes. So some of the lesser known activities of TIFR in computer science and computer communication, I think TIFR has done a lot of things which have sort of been forgotten with time. TIFR, for example, the first wall-based and eventually solid-state detector computer was designed in India in 1955. And I just want to warn you that these dates that I'm giving are something partly from my memory and partly from literature. So they may be off by a year or two here and there. Then BitNet, the first internet connectivity from India to the world, started in 80s. We had an extensive program of monsoon predictions based on the CDC 316 that we had at that time. And eventually, of course, it went to the other institutions, but we did an extensive work on monsoon prediction using data from real-time ships and real-time data from ships and so on. Then we did our first Apple satellite experiment, and that disk is still there, the structure on which the disk stood is still there in the colony or in the refuge area, when we first tried to connect PRL to TIFR using Apple satellite to study how satellite communication will eventually work. And this was good 40 years ago. Early experiment in managing computer software and hardware, we got Vector as our first computer from UN, and then a lot of work was done on trying to understand hardware-software relations and so on. Adjust and Aaron are two major projects we took for defense, and there were a large number of people who worked on that from 1981 to 90. Eventually, the technology was handed over to defense, and the group was dismantled. Data center for CERN is still active. We replicate CERN data here for other users to use. In 1970 to 75, Ayawat and Mahadevan came to TIFR with RN and worked extensively on digitalization of script, and that remains a standard about how to create corpus for unknown scripts and so on. That remains a worldwide standard. It was copied several times later on. Archaeology work of Devendra Lal and others on carbon-14 dating and monsoon, rainwater carbon-14, etc. were another set of classic experiments. We also had some experiments to try and detect tachyons. Did not get anywhere, but at least we had tried fairly hard to do that in 70s. We manufactured integrated circuits to learn how the technology works. Eventually, that technology was also handed over to somebody else. Then there is this experiment to study equivalence principle, extremely sensitive experiment to see if fifth force exists or there are variants in the equivalence principle of gravitational and inertial mass and so on. And there are some that I'm sure I have forgotten. There are some interesting individual initiatives like hydrogeology and water management of Professor Rama, where he tried to handle the Gangetic Plain flooding by creating reservoirs and so on. Teaching of music and computers again was an interesting experiment. It went on with Paritosh Pandya till 2020 and so on. Rock magnetism work was done in 1970s, which also remains one of the great works of TIFR. Then there were studies of reference frames and relativity and whether relativity, the idea of everything is relative or not, is true or not. There were some alternative attempts to understand quantum interpretation. There were some experiments on ultra cold atoms. There was some work in ancient astronomy, archaeoastronomy, and there are many others, some of which I probably never heard of or have slipped my mind for the moment, and I apologize for the same. These led to two parts. Some of them were just full hide, some of them were just doomed to fail, some of them were overtaken by events, and all kinds of things happened. But the idea was that all of them were bold, original, and path-breaking, and that remains the hallmark of TIFR. We are not really worried about whether we will succeed or not. We are more worried about doing something that is nice, something that is creative, and that challenges the prevailing wisdom. Pursuers of these ideas were not afraid to try something new and were quite willing to fail, and some succeeded, some failed. But the idea that you should remain creative is something that has become ingrained in TIFR. TIFR's outreach program, for example, also remains a good standard of its own. Bhaba's original vision was that TIFR would simply seed research in India. But over a period of time, while we have helped many institutions like Samir and CST, etc., to come up and take up independent charge, even solid state corporation and so on, we also seeded many international collaborations, and there are many stories in TIFR folklore about how Bhabha would not accept any collaboration where India did not have equal share of responsibility and credit, and that we were not going to make ourselves simply available to some foreign collaborations. Many experiments of large-scale communication and all that, which have now become mainstream, were originally the first experiments done at TIFR. Several directors of institutions have come out of TIFR. Many advisory committee members have come to TIFR. Leaders in many fields have come from TIFR. And many entrepreneurs have found their roots in the work at TIFR. TIFR, therefore, has been like a large banyan tree from which it is often not even easy to make out the original roots, but those branches are everywhere. TIFR, this is not an accident, this is not a chance. It is a very well-designed plan. We have a remarkably novel model of administration which has allowed flexibility, which is not possible in almost any other institution. We have an extremely capable engineering services and other facilities which have allowed us to create things that other institutions would have struggled to create. Under this lies a very peculiar self-confidence of TIFR and a very intense work culture where there is no such thing as seniors not going and dirtying their hands in the lab. The faith was in gathering the best of minds and giving them freedom to do whatever they wanted to do. Something that many institutions have always feared to do. Even those institutions that allow you to pursue research generally load you up with teaching responsibilities, which negates many of the advantages of TIFR. TIFR has always been creative. I have always been creative, and destructive activities have been really very few. We have essentially been very creative. And despite the success of other institution has been able to replicate this kind of width of activity. And the motto of TIFR has always been something that you can't see. Has been that you'll never know until you have tried. And TIFR loves trying. So we at TIFR today have people from a variety of backgrounds, and we don't appreciate how much that variety of background of people have contributed to the culture of science, because each background has its own way of understanding the fundamental principles of interpreting those principles and their own perspective of how universe works. That cosmopolitan nature of TIFR and its staff has worked remarkably well in favor of TIFR, because every person with its own background, eventually science is individual dependence. And when you have individuals with variety of backgrounds, that certainly produces new ideas of creativity. Even at senior levels, the freedom to pursue knowledge is something that that only TIFR provides. Some laurels have come, some have not, but we have never cried for, and we have never fought for, and we have never complained about some laurels not coming to us. And TIFR has always been confident. In fact, we have often been called arrogant, but never in doubt of itself in its place in the world. It's a remarkable institution. Behind the success lies the willingness to try something new and willingness to fail. TIFR has never criticized failures. And even people who tried projects which did not succeed, they still got credit for having tried something new. Yet TIFR has so many scientists of very high level that it is not possible to give acknowledgement to everybody for what they have done. In other words, for similar kind of work in another institution, you would have got much greater recognition than you get in TIFR, because of the way TIFR is. And I don't know how many of you know, but when you join TIFR, you have to go and report to one Mrs. Shore. And on the opposite side of the table where you sat, he had this saying. He made it clear that in heaven, an angel is no one in particular. Right on day one that you are joining, you were told that, look, you may be university top ranker and you may have come with great laurels, but here you are just one of the many who have achieved, who are here. And you should always remember that. And those humbling statements still resonate in my mind, that in heaven, an angel is no one in particular. And here, you are in a crew which is unbelievably excellent. The personality of TIFR has also been affected. So we are very self-infected and introverted as an institution. We have never taken cognizance of the recognitions, and we have never found distress in not getting them. We've got our recognitions, we've been happy with them, and then just carried on all along. Like all introverts, we are never convinced that we deserve the recognition we get, and always sure that we are worthy of the recognitions we did not get. And that's a very peculiar characteristic of TIFR. The lack of flamboyance has also unfortunately restricted our national role. While we, as a group, TIFR can contribute much more to national policy making, we have never pushed our people or ourselves into national bodies to the loss of the government, but it also been to some extent a loss to ourselves. Also, many people who come to TIFR from outside suddenly say, oh, we never even knew an institution of this depth and quality existed in India. Others have tried to take our place, others have tried to suppress us, others have tried to underplay our achievements, but TIFR has never bothered. And TIFR is never worried about somebody else outshining us or trying to outdo us. It has all been a part of our natural side. And that is because TIFR has remarkable self-confidence. And that majesty of TIFR becomes self-evident. Others may claim, but once somebody looks at it in detail, they will know what TIFR is. Originally, TIFR was supposed to be a seed institution for others in India. But over a period of time, we found that the manner of working of TIFR is not easy to replicate. And even though it has been remarkably successful, many have been unnerved by its model. And we have had some truly extraordinary members of TIFR who needed their own space to work and their own space to expand. The result is that TIFR has eventually ended up creating its own center. So HBCSE, NCRA, and each of them have their own great minds behind them. Obviously, they will now play a significant role in the coming days. In the first 50 years, we had very little biofield stations. Now they dominate the culture of TIFR. And they will play a significant role in future, even though we are not going to discuss them today. That requires a separate meeting, and at some stage we should have a meeting about the future of TIFR. The changing nature of science. Science itself has changed. What it was 75 years ago and what it is today is very different. Research is changing its nature. Research now requires more and more understanding of more realistic, complex systems. Isolated system studies were the hallmark 75 years ago, where you neglected secondary effects. Now that is no longer true. More and more complex systems need to be studied. The basic principles of nature have been substantially clarified over this time period and beyond, but the quantum field remains a challenge to our understanding. But millimeter-sized systems, as individual isolated systems, we reasonably understand. We need to understand the complexities when multiple parameters come into play and how complex systems work out. Quantum world, of course, has its own challenges which need to be looked at. Some events of the adequacy of understanding of nature have also been continuously questioned, and there are many unsatisfactory explanations which need to be looked at. The bottom line is that the challenges have only increased since TIFR was born 75 years ago. So has TIFR's strength and breadth of activity increased. But TIFR will have to continue to reinvent itself, refocus itself, and continue to look for ways to answer the questions that nature keeps posing. What is the role of alumni association in that? Alumni association of TIFR can work with TIFR in several ways. There are always limitations to what you can do officially, and informal organizations can definitely help in many ways. And there are many places where we think the alumni association can help. We can encourage talent across the board, not just among students, but even among faculty and so on. We can reward excellence, whether it is just in PhD or whether it is some extraordinary work. We can help students get international exposure. One of the hallmark of early TIFR successes was its international exposure. And we need to continue to give international exposure to our students, not just through conferences, but even through visits. We should allow TIFR members to explore research ideas beyond the realm of activity. So if somebody thinks of something extraordinary for a quick look, the current mechanism is very difficult to maneuver through to get funding. So in principle, if alumni association has funding, we can look for small projects. Similarly, support international collaborations and other activities as the time passes. The bottom line is, for all this, we need resources, and that is going to be the primary objective of the association, at least in the near future. In longer future, hopefully, we will be able to do these things. All that TIFR believes is that the best is yet to come, and may this always be true for our institution. Thank you very much. So that is the driving force behind this meeting. We want to see how we have reached where we have reached, and then at a later date figure out how to go further and to see where we want to reach. So with those few words, thank you very much, Prabhuji.
Thank you, Professor Bhaiya. That's such a nice and elaborate talk and all the entire overview of the TIFR and overall TIFR Alumni Association. Now we request Professor, our director, Professor Jairam Shunglur, to say a few words.
Yes, thank you, Prabhu, and welcome everybody. I'm glad for this opportunity to say a few words at the start of this conference. The organizers actually have been remarkably generous. They've given me half an hour to do a welcome. I don't actually need half an hour. But I think that's actually a good thing because we'll get to the meat of the conference faster. Of course, we are here because we are celebrating and looking back at 75 years of TIFR, and it's a very, very good thing that we're doing that. And so I'm very glad that the Alumni Association has organized this conference. Now, the alumni are a very important part of any institution, and we're very lucky to have such an engaged and involved alumni. And I really look forward to continuing this engagement and sort of trying to see how we can all grow together. I do have a few slides to share, and we'll probably go over some of the very similar grounds that Vahia had just done, but perhaps with a slightly different take. And since we are talking about 75 years at TIFR, I thought it would be good to start at the start. Thank you. All right, so I thought let's, a good place to start was, Baba's letter to the Tata Trust, where he's actually sort of proposing the setting up of TIFR. And, the other thing I should really acknowledge here is the TIFR archives, which really have done an excellent job. And I think those of you who are here in person could also see, the stuff that they have put together for this meeting outside. And, it's really a remarkable collection of documents of our history. So anyway, here is the letter. It's dated 22nd March 44, and it's addressed to Sir Saurabh Saklapwala, who was at that time the chairman of the Tata Trusts. And Dr. Baba writes, I have for some time nurtured the idea of founding a first-class school of research in the most advanced branches of physics in Bombay. There is at the moment no school of research in the fundamental problems of physics, both theoretical and experimental. It's absolutely in the interests of India to have a vigorous school of research in fundamental physics. The letter is actually quite long, and he then goes on to spell out, the importance of having a premier institute for research in fundamental sciences. I'm not going to quote from the letter, but I'll just sort of summarize in my own words the points that Dr. Baba makes. So the first thing he says is that fundamental research paves the way for applied research. And that it's very important to have a premier institute of fundamental research, because having such an institute allows one to create a group.
Not getting shared.
Yeah. Okay, now? Sorry. Yeah, that's fine. So let me just start at the top of the slide. The first point he makes is that fundamental research paves the way for applied research, and Mayank sort of, gave us some examples of how that happened. A premier institute of fundamental research creates a group with a critical mass, which is much more effective than having small scattered groups, and that really is very important. A lot of things that have happened at TIFR is simply because there was adequate manpower to carry out these large projects.
It sets the standards for high quality research in the country, and it also has people who can then provide advice and direction for other scientific programs in the country. And finally, it trains the scientific manpower needed for nation building. And as we go through this conference today, I think we see that we've actually done very well in all of these things that Baba has set out when he was spelling out the vision for our institute. But I also want to sort of yeah. Oh, okay. Sorry about that. All right, but he also makes the case. I mean, over there he was talking about all of the the specific ways in which it's advantageous to a nation to have an institute, a premier institute of fundamental sciences. But he also actually makes the case for just doing curiosity-driven research. And that he does about a year later in the inauguration of TIFR, where he says, today we all know of the great importance of fundamental research, and the recent release of atomic energy for practical purposes has brought forcibly before the public how entirely new avenues can be opened up by fundamental research, namely the study of nature itself unhampered by any preconceived practical ends. The pursuit of science and its practical application are no longer subsidiary social activities today. Science forms the basis of our whole social structure, and without it, life as we know it would be inconceivable. And of course, much of what Dr. Baba said then is, has only grown in relevance and importance as we've sort of gone along. And in that inaugural talk, although the letter itself spoke only about physics, in that inaugural talk, Baba connected to a number of different subjects. He spoke about fundamental physics, both theoretical and experimental, mathematics, cosmic ray studies, nuclear physics, chemistry, as well as astronomy. So it was a talk in which we clearly sort of had a much broader vision for the kind of science that would happen in the institute. And interestingly, biology is not mentioned in his inaugural talk, but Sir Saklatwala, in his response to Tata's, to the letter to the Tata Trust in 1944, had actually written that in addition to the things that you're saying, we should also look at the important future applications of physics and biology. So it's very clear that from the very, very early days, the vision was for a very broad program in the basic sciences. That letter that Dr. Baba wrote in 1944 also spoke about his visions for how the institute would grow over time. And so he talks about the utility of having not just one institution, but a group of associated institutions. So looking, through the text of that letter, the idea appears to have been to grow over time by spawning a federation of nearby institutions. In practice, we have evolved slightly differently. We have, of course, grown significantly over time, but this has been realized in the form of having TIFR centers spread across the country. So it's a similar idea, but in actual implementation, it's sort of moved in a slightly different track. These centers have typically been focused on specific areas, as you all know, excepting for TIFR Hyderabad, which was conceived on a much larger scale as a second campus of TIFR. And so I've just put up the slide, which I got from Sandeep, which sort of says a little bit about how geographically spread we are over the country. And I think one of the good things to do over here would also to be to put in, the locations where we have field stations or conducted large experiments. And I think we'll probably find it covers pretty much all of the country. So I think we could, and as we will find out as we go through the next 2 days, we'll find out that, TIFR has certainly lived up to its original vision. And we are gathered, in fact, here to celebrate TIFR's achievements in a wide range of fields. And we'll have talks about all of this over the next couple of days, and we'll hear it, obviously, from the people who were in the front lines actually doing this stuff. So I'm not really going to talk about any of this in detail. But I did want to say a little bit about manpower training. So again, just going back to Baba's letter of 1944, right at that time itself, he had envisaged student training, and he said the institute would be affiliated to Bombay University
And the university would also send its advanced research students to the laboratory to work on their doctoral thesis. And indeed, that's how things worked out. TIFR was this people who enrolled for a PhD work at TIFR got their degrees from Bombay University. And TIFR, in fact, established one of the first graduate schools in the country. Courses were offered from the 1950s onwards, and student intake into a structured graduate school program commenced in the early 60s. And 2002, as you all know, TIFR became a deemed university, and it's actually quite large. There are about 1,000 students currently enrolled in the TIFR deemed university. So, the contributions to training manpower at the highest levels have really been quite significant. And TIFR students have gone on to play very important roles in the scientific community, both in India and abroad, with their contributions acknowledged with Padma Awards, Bhatnagar Awards, Infosys Awards, leadership roles across the country. I also wanted to touch on TIFR and the wider science ecosystem. Mayank mentioned this about the number of different initiatives and institutions that have been fostered by TIFR, including ECIL, the Semiconductor Laboratory, SAMIR, NCST, CDOT, and so on. And we will have a talk on this later. I did think that the outreach that TIFR does through the Homi Bhabha Science Center for Education, Center for Science Education, is actually really worth noting. The Olympiad program, which is run by HBCSE, has a catchment of several lakh students. There's this program, Vigyan Pratibha, aimed at students at sort of high school level, which is again touching students all across the country. And very recently, there's been this new program, this new initiative at TIFR called Vigyan Vidushi, which is basically taking cognizance of the fact that there is a tremendous underrepresentation of women in STEM subjects, and trying to do a little bit about it by actually organizing schools for people at the undergraduate, for women particularly at the undergraduate level, to sort of expose them to research and try and encourage them to take up research as a career. All right, so I think that's about all I had want to say as way of introductory remarks. Before I close, I just thought I'll just talk about very briefly about two large infrastructure projects which are coming up. So the work on drawing the master plan and the construction of the phase 1 of the TIFR Hyderabad campus is commencing. So this is not, in fact, the master plan for TIFR Hyderabad. It's just a kind of concept that the consultant had drawn up at the time of providing the bid. But now work has started in working with the consultant to come up with the master plan as well as the tenders for constructing the phase 1 set of buildings. And there's also a proposal for a new building at the Colaba campus, which will greatly sort of ease the difficulties that we face with because of space constraints in our campus over here, and that is at a very advanced stage in the approval process. And so we are hopeful that goes through and we can start on this project also pretty soon. So I think that's about all I had wanted to say. Thank you all, and welcome again to Landmarks 75. I'm sure we'll have a wonderful time hearing about all of the things which have happened over here. All of the remarkable things that have happened over here over the last 75 years. Thank you.
Thank you, that's up, Professor Chingalur. And now we are going to begin our session where there will be 2 talks before we break for high tea break. And the first talk is going to be by Professor Arun Kumar Grover. I want to just say a little bit about these talks, that there will be no question and answer session after this. So because this is the nature of the talks are like that. So therefore, after the talk is over, you have enough time to talk to the speaker, and during the mixing time, we can spend a lot of time. So let me just quickly introduce Professor Arun Grover. Professor Grover is a condensed matter physicist from TIFR. He served as the 12th Vice Chancellor of the Punjab University. Chandigarh from 2012 to 2018, and he had served as the convener of the Homi Baba Birth Centenary Commemoration Committee of TIFR in 2008 to 2010. An initiative commenced in 2012 by him, which caught national attention, has been the nucleation of the Chandigarh Region Innovation and Knowledge Cluster, that is called CRIC-C, and which brought together all the institutions in and around Chandigarh on a very common platform. So, Professor Grover, please, welcome.
Good morning. So I am grateful to the organizers to have asked me to speak on the topic history of the TIFR and India. At the outset, I reckon that there are at least 10 more persons in the audience today as well as on the Zoom who could have given this talk maybe better than me in view of their longer and deeper involvement in progressing the purposes of TIFR. But anyway, the task is assigned to me and I shall proceed. So, writing down historical facts alone is not enough. They become relevant only if interpreted by one's perspective. So this talk will reflect my preferences and prejudices. So it is my comprehension that when Bharat gave the proposal for TIFR in 1943, he couldn't have imagined the speed at which the TIFR would progress as the times would go by. The Indian independence was very near, but it was not definite how it will come about. And the TIFR managed to progress because Nehru became the head of the interim government and later on the Prime Minister of India, and he had two advisors, Bhatnagar and PMS Beckett. And these two helped propel TIFR as well as atomic energy at a very, very vigorous pace after 1947. So Bhatnagar and Saha had known each other since 1920s. Okay, and the World War II gave them an opportunity to work together in partnership with the other scientists, teacher scientists in India. Bhatnagar had moved from Lahore to Calcutta as a director, first director of both scientific and industrial research, and Saha had moved to Calcutta for Allahabad in 1938. And so Saha had known Subhash Bose since the presidency days, and when Subhash became the president of Indian National Congress, a planning committee for the Congress was conceived, and Vishwesvaraya was to be chair of that committee, but Saha persuaded Bose to have Nehru as the chairman of the committee. So as the war went by, then sometime in September of 1943, a month after Ara had proposed the creation of TIFR to J.R.D. Tata in a letter written in August of 1943, Saha masterminded getting together of all the scientists in India for a symposium convened by the National Institute of Sciences. And in that symposium, the Indian scientists had drawn a concrete framework for research and development for post-war India. Bharat had also contributed a paper to that meeting, and the proceedings of these meetings were published later in 1944. At the end of the meeting, Saha persuaded Bhatnagar to invite A.V. Hill, Nobel laureate A.V. Hill, the then secretary of the Royal Society, to come to India and interact with the Indian scientists. And this is how the agenda for the post-war development of India was evolved. And Bharat's efforts were concurrent to it, but not a part of that agenda as it was invented by A.V. Hill later. So who are the contemporaries of Bharat in the old days? Okay, you can recognize all these names, and 10 of these names along with Bharat figure in the book titled Bright Sparks, which gives you biographies of 40 scientists of yesteryears. So you can see that Bhabha had many competitors, okay, when he proposed TIFR. Where were these scientists located? Bhabha, of course, was at IISc Bangalore, but this is a list of major centers of research in India, and you can see the research was going on all across India at that time, and this is where all these people were distributed. So this is just the listing of the Council of National Institute of Sciences in 1944. J.C. Ghosh, the then director of IISc Bangalore, was the chairman of the council, and Bhavan and Meghna Saha were members of this council as well. So this is an extract from Venkataraman's book, Venkataraman, who wrote the biographies of Raman and Saha. And in this book, this Venkataraman gave the founders account in 1984 in BRC, and in that he said Subhash became the Congress president in 38, and Saha persuaded Bose to form a planning committee, and he got Saha. He made Saha made Nehru as the chairman of that committee. And then Venkataraman goes on to say that in the atomic energy race in the independent India, Saha lost and Bhabha won, mainly because of his dynamism and vision. Saha was equally visionary, but Saha was 16 years younger than Bhabha, and Bhabha had more international exposure in some sense than Saha. Okay, so this is just a photograph taken in 1938. This was published in the INSA book on Saha in 2019. This is Subhash Bose and Saha together, along with the industries ministers of the then states. Elections are held in India in 1936. So many states had ministries, and these are the industries ministers with Saha and Bose. So, okay, so now let's come to the meat of the talk, and that is the Bhabha stay at Indian Institute of Science in Bangalore. So the Britain declared war on Germany in September of 1939. Bhabha got stuck in Bangalore. Dawji Tata Trust created a reader's position in Bangalore for Bhabha, and planned a series of lectures on cosmic rays to be delivered at the physics department of IISc in the beginning of 1940. So before he commenced his lectures, he set up a meeting with Krishnan at the Indian Science Congress Association annual meeting, which was to be held in Madras in January. And he goes there, meets Krishnan. Meeting was presided by Birbal Sahni, who had been elected FRS in 1936 at that time. So Bhabha meets both Krishnan and Birbal Sahni in that meeting. So the lectures that Bhabha delivered at Bangalore, the news of that spread everywhere, and that made Saha invite Bhabha to give a similar series of lectures in Calcutta, which of course Bhabha did later in the year, and proceedings of that. He also supplied a summary of those lectures to Saha to publish in the Science and Culture. So in the year 1939, Raman had nominated Krishnan for FRS. So that FRS came through in the beginning of 1940, and later in the year 1940, Raman nominated Bhabha for the election of the Royal Society, and that does happen in the March of 1941. Bhabha got elected as a FRS, and now Bhabha was the FRS. He was promoted to a professor's position, and the invitations of professor's position started to arrive in Bangalore for Bhabha. So in fact, Raman tried to persuade Bhabha to move to Allahabad, where Saha had vacated his position and he had moved to Calcutta. But all that position is, what the teaching in a university could be, etc., etc. So Bhabha wrote a letter to Krishnan soliciting his opinion. Okay, and then in December 1941, the Japanese did whatever they had to do at the Pearl Harbor, and then they started to move in Southeast Asia. and at some stage has threatened airstrikes on Calcutta, which never happened, but that scared Krishnan and also Bhatnagar. So Bhatnagar decided to move the site for National Physical Laboratory from Calcutta to Delhi, and Krishnan decided to leave his Mahendralal Sarkar professorship at IACS, and he accepted the position at Allahabad, which was vacated by Saha. So 42 it all happened, and in the middle of 42, Baba lost his father, and that became a turning point in his life. Baba at that time actually was writing a book on particle physics or cosmic radiation, which was to be published in Oxford University Press. The book actually finally never gets published because Baba only supplied half of the manuscript and later half never reached there. So January of 43, he delivered the presidential address of the physics section of the annual meeting of the Indian Science Congress Association. So Baba used to attend this annual meeting of the Science Congress Association. That is how he was getting to know the community in the country intimately. So June of 43, Baba wrote to Pauli. By that time, he had set up a lab for doing cosmic ray research. Actually, he had obtained a grant of 1,200 pounds to recommence the experiments which Millikan had left halfway. Millikan had visited India twice. He was in Bangalore. He flew balloons from Bangalore, Madras, as well as he went as far away as Peshawar. Also from there, he flew those balloons. So there was some data, and Bhavan decided to recommence those experiments in the search for some characteristics relating to the mesons. So that was the title of the grant that was there. I don't know how to remove this. I think something. Huh? इसको remove करोगे?
Just enter through.
No, I can change, but this is not going. No? This comes. Because it comes here also. It doesn't allow the last sentences to be. Okay, so no, it's not moving.
Going back.
Yeah. Okay, so I was telling you that 43 is the time when we have now set up to do experiments at Bangalore, recommencing the work that Millikan has done earlier. And 43 is June of 43, he also receives a gift from Krishnan in the form of Harishchandra as a student to work with him on the theory. So experiments are going on. He has got a bright student. Okay, and it is in that background that proposal is sent. He sends a letter to J.R.D. Tata in August of 43. Okay, trying with the idea of starting an institute for fundamental physics. Okay. So all right, after August, that meeting happens in Calcutta of National Institute of Sciences. Okay, as to how to organize research in India after the war. And then A.V. Hill was invited to talk to the Indian scientists. So in January of 1944, Baba delivered a lecture in Delhi University and the CSR at that time was located on the campus of Delhi University, and Baba's lecture was presided by Ramaswamy Mutliar, who is the one who had got CSR going by identifying Bhatnagar in 1939. So you see now the pieces are falling in place. So in February of 1944, Bhava consults Rustam Choksi, whom he had known for a very, very long time. Choksi was teaching in Mental College, and he seeks his help or to put up a financial proposal for TIFR for the Dorothy Tata Trust. So, and he seeks only just 45,000 rupees from the Dorothy Tata Trust in the first letter that is sent on March of 12, 1944. Okay, and he had become familiar with CSR, what CSR was planning. So Tata was of course planning 5 national labs. So he seeks 10% of the money that was to be supposed to be spent on NPL as the CSR's support to TIFR. This is the kind of money that he seeks in the beginning. So it is in that background that the proposal gets discussed. So in April of 1944, before A.V. Hill left India, A.V. Hill wrote a letter to Bhabha, sharing with him something he had learned from Saha, that Chandrasekhar can be enticed to return to India. So Bhabha, of course, had known Chandrasekhar at Cambridge. Saha also had known Chandrasekhar before Chandrasekhar went to Cambridge, because Chandrasekhar had presented a paper at one of the annual meetings of the ICSA, and where, of course, Saha was present. So you see, the competition now starts in trying to get people to return to India after the war at their respective institutions. But anyways, Bhabha was smarter. He immediately wrote to Chandrasekhar, and Chandrasekhar accepted the invitation. Only thing he asked was that that the new institute should reimburse his dislocation expenses. So, in the meanwhile, proposal had been submitted, and after the proposal is submitted, Bhabha receives an invitation to write a paper for reviews of modern physics, a special issue of reviews of modern physics, which was being brought out in honor of the 60th birth year of Niels Bohr. So Bhabha submits that paper, and in that paper is Tata Institute of Fundamental Research in Physics. TIFR is still to commence, but this paper has this byline, Tata Institute of Fundamental Research in Physics. A companion to this paper was written for the proceedings of Indian Academy of Sciences, and in the companion paper, the in physics is dropped and it only says TIFR now. So in the meanwhile, Bhabha also received a letter from Paul Dirac, and he said that the mathematics should be an integral part of the new institute, and that is how, right from the beginning, there are 2 schools, physics and maths in TIFR. So the first meeting at Council of Management of TIFR happened on May 18, 1945. That is 2 weeks before the TIFR starts functioning from IISc campus on June 1. And you can see that the Tata Trust gave the 45,000 that Bhabha had asked for. Government of Bombay pitched in with 25,000, and 10,000 was to come from CSIR. So now Bhabha the institute has commenced. You need people. So Bhabha invited Kosambi and mathematician Levy, who was at that time working in Calcutta, to come and join TIFR. Levy, of course, arrived in 48, but the mathematicians were already in place. And for a physicist, Bhabha chose H.J. Taylor, who was a cosmic ray physicist working in Wilson College. So Taylor accepts to be an adjunct professor at TIFR. So this is how the first few faculty members for TIFR are got in. So the very next year, CSR gave TIFR a block grant of 75,000, and it was for a chair of astrophysics and also inviting a visiting professor. So this money was specifically got to have Chandrasekhar for TIFR, and Bhatnagar also became once the CSR gave the chunk of the budget, so Bhatnagar assumed a position on the TIFR Council of Management. So Chandrasekhar, of course, in 46,
declined to accept Baba's offer because Chandrasekhar wanted to come on a leave first, but he learned that he will not get a deputation from Chicago, and that would have meant that he will have difficulty in getting a visa for returning. So he declined the offer. So then in 46 itself, Patnagar had created a committee for atomic research within CSR. That is after the war ended and with the two nuclear bombs. So there was this committee for atomic research, and Baba was offered the chairpersonship of that committee, and that committee had all its meetings in the Kenilworth building in the initial years. So India becomes independent. 11 days after the Indian independence, the board for research on atomic energy is created, replacing that the committee. So now there is a board, just as CSR was commenced with a board of scientific and industrial research. Now there is a board for atomic research. So that happens on the 26th of August 1947. Many important decisions got taken on 26th of August 1947. That is the day Prime Minister Nehru presided over the CSR meeting as the president of CSR. So many important decisions happened 11 days after the Indian independence, and one of them was the creation of Board of Research in Atomic Energy. So a year later, in 48, Atomic Energy Act was passed by the Indian Parliament, and Atomic Energy Commission gets constituted with Baba as the chair and Krishnan and Bhatnagar as its other two members. So Department of Atomic Energy, of course, happens 3 years, 6 years down the line, and Department of Atomic Energy comes into being only in the year 1954. So until the year 1954, all the money for TIFR came via the CSR. CSR was the only government department, so everyone received their money, or the governmental money for research, through this CSR system. We start to receive our independent money only after year 1954. So cosmic rays was the first large experimental activity at TIFR. So Baba needed to have more people for this. So he inducted Pyara Singh Gill, who was his competitor during the war years. Baba was sending payloads in American bombers. So Pyara Singh Gill had a British plane at his disposal where he was flying his payload. So they were working in competition, but riots started in Lahore. So Gill asked for a position at TIFR, and Baba let him join in June of 1947. So P.S. Gill came as the first professor of experimental physics at TIFR. He didn't stay very long, that's another story. But soon after this thing in 48, Baba invited Raja Ramanna, and he arrived in 1949. Then Bernard Peters was in India at Madras flying balloons, and Baba invited him to join, and he joined in 51. Then in between, in 47 itself, Baba had met K. Chandrasekhar at Institute of Advanced Studies, Princeton, and he invited him to set up a school of mathematics on the lines of School of Physics that he had in mind. And so Chandrasekhar also arrived in 1949. So Ramanna, nuclear physicist, mathematician K. Chandrasekhar, joined him in 49. And later on, Dr. K.G. Ramanathan joined in 53. And then finally, Professor Menon joined, Dr. M.G.K. Menon joined as a reader in the year 1955. So TIFR as a national center. So in 48 itself, the Atomic Energy Research Committee of CSR had envisaged TIFR to be a center for all large-scale experimental research in physics. Later on, in the year 53, Bhatnagar put a proposal in a 27th meeting of the Atomic Energy Commission, and the Commission noted that it had recognized TIFR as the only laboratory of the Commission for Fundamental Research in Atomic Science, So in view of this decision, the commission would not set up another laboratory of its own for fundamental research in atomic physics. So during the laying of the foundation stone of Colaba campus, okay, all this was revealed by Bhatnagar on 1st of January 1954. So TIFR had moved from Kenilworth to OIC, and when these buildings sort of got commissioned, okay, the TIFR moved to its present premises in the year 1962. So whenever TIFR needed in the initial years, Baba would get it as a special grant from CSR. The first hostel also the money came from CSR. So this is the beginnings of TIFR. So now let's see what was happening in India at that time. So before 1930, before the war, 30 to 38, we all know that C.V. Raman got the Nobel Prize in 1930. And in 1931, C.V. Raman and J.C. Ghosh, who was to succeed Raman later on as the IISc director, they sought the creation of the Advisory Board for Scientific Research. The editor of Nature at that time, Richard Gregory, supported the articulation of Raman and Ghosh, but the government in London as well as the government in New Delhi were not receptive. The Viceroy Lord Wellington, he said in 34 that this cannot be done. So as far as industrial scientific research, so no support was coming from the government. The industrial research, TISCO indeed set up a laboratory in Jamshedpur for control and research laboratory. So this actually is the precursor of the National Metallurgical Lab, which is one of the first CSR labs, which will happen as the time would go by. So it's only the start of the war that the government in London and New Delhi realized the importance of reaching out to teacher scientists in India to aid the war efforts. So this board, BSIR, as I told you, was commenced in an effort to aid the war effort of the British. So it is in that proposition, but Nagar had moved from Lahore to Calcutta. His lab was taken over by the military, and CSR got into being on September 26, 1942. So in 43, the symposium that was conceived by Saha, everybody was there. So you can see the names who were there. Baba had not attended the symposium physically, but he had sent a paper for this, this thing, which was published in the proceedings later. So what did these people discuss? They discussed how should the wartime infrastructure in science and technology be assimilated for peacetime civilian organization, and what should be the overall organization model in science and technology for post-war India. It wasn't clear whether post-war India would have a Commonwealth stature or would have complete independence at that time. All the same, the plan had been all worked out, and the scientists had articulated the need to create a National Research Council for India. What should the National Research Council look like? Okay, all that was also spelled out. The NRC was to plan the main lines of scientific research in accordance with the national needs, and it was supposed to ensure the balanced development of all branches of science with minimum overlapping. So this is what NRC was supposed to do. NRC was supposed to have 4 boards of research: scientific research, agricultural research, medical research, and engineering research. Okay, so everything of fundamental nature is a part of the scientific research. And prior to the war, British were only giving money, little bit of money for agricultural research. So Imperial Agricultural Research Institute had been in place right in the mid-20s. Okay, so the only agricultural research and little bit of money was being given for the meteorological work, work related to weather predictions and so on, or the surveys of India, geological survey of India and so on. There was no support to scientific research elsewhere in the country. So, and what did they seek? the Indian scientists at that time, in the year 44, they only sought 5 crore rupees to kickstart the support to research in India. And this is 5 crore that you see the budget that Baba was asking from Tata Trust was just 45,000 rupees. First budget of TIFR was just 80,000 rupees. So, and what did Bhatnagar say in that meeting? He said it is abundantly clear that the research will have to be subsidized and encouraged both by the state and the people on a very large scale. By people, he meant the corporate houses or the industrialists who had some profits to share. So, A.V. Hill summarized everything in the form of a report which he submitted in August of 1944. Summary of this report was published in a 4-page article in Nature of 1945. So this had 24 sections, and this is just the headings of that longish report. And you can see from these headings, everything was covered. Literally everything was covered. And there are specific recommendations. Amongst the specific recommendation was that create an overseas fellowship scheme for training Indians abroad. It is that fellowship scheme which gave India eventually a Kurian, which gave India Brahm Prakash, Satish Dhawan, Hargobind Khurana. All these people had gone to US and UK on the Government of India fellowship, and then they returned to India. So that report said create aims like institution, monitor population control, and A.V. Hill had said that agriculture in India is most important industry. Okay. Then A.V. Hill report specifically says that India needs first quality brains trained in atmosphere of original research and practical experience. That is what TIFR was supposed to do. It had called for creation of MIT-like institutions. It had supported NRC, and most importantly, it said reduce the gap in the salaries of scientists and the civil servant so as to attract the best mind for academia. This is also a part of the A.V. Hill report, and this is what Baba eventually implements. And A.V. Hill report said support universities as science education is the fundamental basis of scientific progress. And after writing all these things, A.V. Hill said in October of 1944 that disaster lies ahead if India's industrial development and national welfare are not immediately attended to. So, and let me come back to the rest of India at that time. So, from 44 to 1956, January of 1944, JRD Tata released the Tata Birla Plan. 1 crore rupees were given to Bhatnagar to create 5 national labs. Sargent Committee gave a report to revamp education. AICT was created. Okay, and reports to create IITs and AIMS also happened at that time. After independence, Bhatnagar became the first Secretary of Education, and Bhatnagar also went on to be the first chairman of UGC in 1953, and UGC gets passed in 56. So these are the 5 national labs which got opened parallel to creation of TIFR, and these 5 national labs, okay, 3 of the directors of these national labs were invited from abroad, and they obviously were people of very high stature. 4th lab had Krishnan as the first director, NPL Delhi, and Atmaram, who had been a part of scientific and industrial research prior to the creation of PSIR. He was the first director of CGCRI in Calcutta. So Baba's TIFR had to compete with these national labs and the people of reasonably high stature, okay, as the time goes by. After the independence, more labs get created. Birbal Sahni proposes his institute in Lucknow. CDRI was sanctioned in the 26th August meeting of 47. Then Raman proposes RRI, and then Saha has his Institute of Nuclear Physics in 49. Then Mitra had proposed Institute of Radio Physics at Calcutta University, CFTRI. So lots and lots of institutions, okay, get going in the first few years of Indian independence. So IARI, agricultural research was the only thing which was being supported, and BP Paul was the director of IARI as India becomes independent, and BP Paul has been referred as the Homi Bhabha of agriculture. So there were, every field has its own Homi Bhabhas, and all these Homi Bhabhas were competing for the national attention. So Bhabha had also known Mahalanobis very intimately, and this is a letter written by Mahalanobis to Bhabha. I am feeling somewhat disillusioned and fed up with my own generation. Okay, because at some stage everybody is now competing. Okay, and when they compete, then few unpleasant things happen. So this is Bhatnagar addressing the gathering on 1st of January 1954, and Saha was not present on 1st January 1954 at the foundation laying stone of TIFR. All others were there. So, Bhatnagar didn't live very long. He passed away exactly 1 year later. Saha also didn't very long. He passed away in 16 February 56. J.C. Ghosh, the first director of IIT Kharagpur, moves into Delhi to fill up the vacuum created by Bhatnagar, but he also passes away in 1959. The only person who survives in Delhi aiding Nehru was P.C. Mahalanobis, okay, who remains a member of the Planning Commission for 17 years. And of course, PMS Blackett, who had been inducted by Nehru as an advisor on January of 1947, he continues to be an advisor to Government of India right up to the year 1971. When Blackett had become advisor to Nehru in January 47, Blackett was still not a Nobel laureate. Blackett receives his Nobel Prize only in 1948. So this is a photograph all of you have seen many times. This is Bhabha with Blackett and Bhatnagar. Okay, and so what did Bhatnagar and Bhabha do to reduce the gap between the salaries of the teachers and the civil servants? Bhatnagar, of course, had increased the salaries of all the teachers by 25% when he became first chairman of UGC, and Bhabha picked it up from there. And as the Department of Atomic Energy got created, he gave a proposal of starting a training school where the engineers and the scientists would be inducted as class 1 officers. And he devised this career progression scheme as a personal promotion scheme, assessment scheme for the scientists and the academics in TIFR. And this is how the gap between the salaries of the civil servants and academics started to decrease. And by the time it took for 50 years, but at some stage, a professor's position does become equivalent to that of Joint Secretary in Government of India. That, of course, happened in 1996. But today, IITs have a salary structure which is even better than the civil services in India. So this brings me to the end of my planned presentation. Okay, and I have tried to present a narrative leading to the conception and evolution of TIFR in the earlier years in the backdrop of plans for development of all other fields. Okay, and Bhabha was all the time competing with a large number of people. Everybody received support. Some things evolved faster later, and now you can see India is full of many institutes for whom Bhabha set an example of how to create an institution, okay, which will be envied by everyone. I mean, of course, later on, so many other institutes have come up on the lines of TIFR. To name a few, CCMB came up, NII came up, Ayuka happened. So many other things happened in India. All the DAE supported fundamental research institute are also modeled in some sense on TIFR. So TIFR did have a head start, as I said in the beginning, by virtue of proximity of Bhabha to Nehru independently, and Bhabha being supported by Bhatnagar. And Bhabha succeeded, and because Bhabha was very careful in selecting his colleagues, giving independence to his colleagues, also nurturing young people by providing what he said, intelligent financial support and proper conditions for work. So this is what has to be sustained. Okay, if the TIFR has to march, continue to march, and we just had a wonderful presentation of the vision of TIFR by the present director, and I hope all those things would happen sooner than later. We of course need support, and we need to solicit support beyond the government of India, because the government today is saying that every institution must identify its benefactors. If TIFR is producing human resource today, this human resource would get employed by the present and the futuristic academic institutions of India. If the futuristic academic institutions of India are going to be sustained by the corporate sector of India, then I think we should put up a proposal or support from the corporate sector of India, because they are going to be the main beneficiary of the produce of TIFR. So while we seek money from the Department of Atomic Energy for expansion of TIFR Colaba campus and creation of TIFR Hyderabad campus, we must simultaneously make proposals and bid to seek corporate sector support on sort of 50-50, 1:1 basis. We have to continue doing well. Thank you very much.
Thank you. Thank you. Thank you, Professor Grover, for such a wonderful talk and the historical perspective. I just want to make this announcement that after Professor Nabo Mandal's talk, there we will break for the tea, and during that time we will have a photograph session. We will take the photographs of everybody. Please gather, walk straight outside on those steps, go leading towards the almond grove, and we will just take a photograph there. Now it's my pleasure to introduce Professor Nabo Mandal, our next speaker. Professor Nabo Mandal joined TIFR in 1977 and was associated with pioneering Kohler Goldfield proton decay experiment from its inception. He has worked at Argonne National Laboratory USA, Collider Detection Facility CDF at Fermilab USA. He was involved in the important discovery of top quark, and in 1995 he joined the CMS experiment at Large Hadron Collider project at CERN Geneva. He was the technical coordinator of the CMS Outer Hadron Colorimeter project, and he was involved in the development of world-class underground laboratory in India, which has been formed under his leadership for the development of India-based neutrino observatory, famously known as INO. Now I request Professor Mondal to start his talk. Just 1 minute, actually. Yeah, just hold on. I will disable them. No, it's okay. I'm just trying to remove this. Remove it outside because it is disturbed.
Okay, let me thank the Alumni Association for giving me the opportunity to know more history. I mean, this will be more history than physics. So I will be talking about journey of TIFR in cosmic rays and particle colliders. So landmarks, and since I have to cover these 2 areas, so that's my landmark. And this is cosmic rays and non-based particle physics experiment and particle physics at accelerator. And then I'll start with some statements about future. Now, with this cosmic rays, there are so many things that happen, and it's impossible for me to cover everything that will happen. So I will pick up some glimpses from here and there, and give you some idea what are the type of excitement we had in those days. So we'll start this exploratory work at KGF during the early 50s, moving to the mountain to extensive research studies at TIFR C block. As soon as the new building came in, we had the rooftop occupied, availability and KGF surface and underground areas with extensive research. Then begin to KGF, begin deep underground and mapping roots up to great depth, the famous experiment, neutron experiment, proton decay. And at the time when we were doing cosmically using the charged particle, there was also looking to the very active gateways and start at looking and 16 we are participating in the Madison and Baricham experiment, then in full L3 experiment at CERN and BG experiment at CERN. I will not be talking about the experiment that is going on at COVID, but I will make some statement at the end. So that's why I'm not including the ongoing experiment, CMS and others. Okay. So actually, the journey of TIFR in experimental science started before TIFR was created, really speaking. And that started, and you know why I'm telling this statement. It started at Cosmic Research Unit at Bangalore, where Homi Bhabha was located at that time. That's what I said, seeds of cosmic research at TIFR was really strong, even before TIFR came into existence in 1945. And that's in 1943. Bhabha wanted to start cosmic ray experiment, and he was carving for data during the war. No data was there, he was not getting, so he started starting himself with this experiment. So he invited Mridul Shekhar Sena. He was actually working that time with DM Brooks at Bush Institute to build a cloud chamber. And M.S. Sena came to Bangalore and built a 12-inch circular cloud chamber, similar to the one that available at Brackett Lab at UK at that time, and Vijanko Sena happened to have worked with that cloud chamber. And later on, so happened that Professor Sena was my teacher at my university days, but that's I only learned after coming here that he had built the first cloud chamber of TIFR. Anyway, so and then you have to use it for the study of scattering properties of Melbourne, while in Bangalore itself, and of course, additional Odin was talking about in December 1945. He flew to a telescope with GM counters, sandwiched with lead plates using US plane stationed at Bangalore during the wartime. And the first measurement of high altitude measurement intensity that actual latitude was done by this one. So this was the activities that was going on. And when Bhabha came from Bangalore to Bombay, he carried with him this 12-inch cloud chamber. That's what I said that TIFR started the experiment activities in Devon. As soon as this TIFR was established, actually started growing the field, and of course, we had the cloud chamber, that circular cloud chamber 12-inch that was built there, but also expanded in other areas like GM counters, diagonal counters, and this is the glass going section, and for the Navy visiting, and the main purpose of glass going section is to build actually this glass GM counters. That's one major job that they do, and of course, that is this emulsion chamber, this photographic, developing lab, where this emulsion developed and taken care of. So these are the activities with which TIFR started its journey at the beginning, and soon the first international conference on elementary particles in India that happened in TIFR in the Old Age Club in 1950, and many luminaries were present in that. And that's what actually talked out the future plan of cosmic research in TIFR. And one of the person that was attending that meeting was Bernard Peter. And as you know, and for next almost 8 to 10 years, he actually saved the cosmic research in TIFR in many areas actually. And this was I have picked up this role that I call it. These are the first set of leaders that led these activities in cosmic rays in India, in TIFR in particular. And I'm not going to talk about the work by all these people. And here is Homi Bhabha himself, and Bernard Peter, Biva Chaudhuri, Roy Daniel, Sukumar Bishwas, V.V. Srikantan, Yatpal, Devendra Lal, and M.G. Menon, who came in 1955. And of course, these people actually are interested in balloon-borne emulsion experiment, and that's what they are carrying on. And I will be talking about these diagonal lines, and Homi Bhabha, B.V. Srikantan, and M.G. Menon, and their activities thereafter. So this is actually at that meeting at 1950, it was idea that you have to measure the
Bhabha was interested mostly in the cosmic penetrating component, because he has this cascade theory, and he wanted to understand whether there is only one penetrating particle or more than one. So he asked Srikantan to go to a polar gold field and at Bulandshaft near in KGF with the underground detector that I'm not showing here. These are the arrays of surface arrays here, and I can show you that much bigger how it looks like. And in a much many years later, and Kolar Goldfield again, a surface array, you can see all these arrays that are sampling the earth shower coming, and there are deep underground, and there are actually these buildings are also hosting the muon detector because there is a granite which will stop other particles to go through this detector. So these are the various activities over the years, and expertise developed and new instrumentation built and new expertise developed. One thing I must tell you here, that these scintillators were all built in India at BRC, and at that time TIFR could take the pride that they have the maximum area of scintillator detectors anywhere in the world at one time. So that was the type of development of instrumentation happening, along with science that was going on. Everything was developed locally, and because see, everything was developed locally simply the other reason, because not much foreign exchange was available in those days. So you have to build it from on. But this shows some ideas of what was going. And then many people have participated in this experiment. I'm just not going who participated in one. Here are the main name: Acharya, Chatterjee, Sunil Gupta, Siddheswar Lal, G.T. Murthy, Naranan, Raghavan, Ramanamurthy, Rangaswamy, Shiva Prasad, Srikantan, Srinivas Rao, and Subramaniam, Tonwar, Vacha, Vishwanath, and so on. So I hope I am not missing some. I think Srikant Rao's name is missing here, so, and participating. So now to give some additional expert, when they're making those air showers, they are also building some other detector to study the special characteristics of the air shower. For example, here, what you call the total absorption spectrometer is a marvelous thing they have built in 60s. Actually, sometimes I wonder they built that in 60s. If you look into carefully, what they wanted to study the core of the air shower, where many hadrons are going, their properties, what kind of particles they are, and how it is. So this detector, if you see, there is a combination of many detectors that you find in today's particle collider experiment at CERN or Fermilab, anywhere you go. At the top, what you call is the air Cherenkov detector. This air Cherenkov detector will separate out a pion from a proton and so on. So charge separation it will do. Below that, a cloud chamber was put. The cloud chamber will detail study of the hadron component. And finally, below that, what is called a scintillator iron layer, 20 layers of scintillators and iron plate to absorb the total energy. That's what is what you call calorimeter these days if you go to CERN or Fermilab. So this was in 60 built by our people here in India to study in details about those particles in those days. So this is the structure they have built, and the person who built this one, Ramanamurthy Subramaniam and Srikantan was the main person who built this whole detector, using of course the workshop at TIFR, using all the scientific people, technicians that we have trained and developed in the process. They are building this type of experiment. While this is the large cloud chamber, this is one time can take the pride of the biggest cloud chamber operational anywhere in the world. This size is 2 meter by 1 meter, 1.5 meter cloud chamber. It was in the mid-60s, used for many years in UTI, even when we were joined. Actually, when we went to UTI first in 1978, this was fully operational for hadron interaction studies. And here you can see the picture in that cloud chamber. The interaction taking place and shower developed and dying. And here is the penetrating longer moving shower. So many such pictures were taken, studied, and part of the earth shower at UTI. So this was and this one, of course, I should put this one. This was that time in the 60s. Professor Miyake came to India, and on the invitation of Professor Srikantan and Menon, and Miyake was an expert in cloud chamber, and he helped building this particular cloud chamber of that big actually. Well, these are the story about these things. Why this is going on at UTI, a new lease of life for the KGF activities, simply because the mines were closed in 1954. What happens is that government of Karnataka took over the running of the mine. So mine continues to running. So Ramanamurthy was in Bombay, and that time he was pressing that let's go back to KGF. We have left that job of measuring the muon intensity and only gone up to some 270 meters and so. So then KGF mine got a new lease life, and in 1956 it became Kolar Gold Mines Undertaking, and later by the government of India, Bharat Gold Mines Limited as a public sector undertaking, and it continued till for some more decades actually. So Kolar Goldfield Laboratory restarted in 1960, and these are the people who started that. I mean, this is not their picture when they started that, and I mean they are much younger in those times when they started. Professor Menon, Srikantan, Narasimham, and Ramanamurthy, and with them was Professor Miyake, who came from Osaka City University to participate in this experiment. And what they are doing that time is using a GM counter array. It is the GM counter at the middle, and on the top and bottom are scintillator coincidence. The top scintillator is by 2 photomultiplier, and bottom is 2 photomultiplier. The coincidence will give them the muon rate, and then they take it test detector underground at different depth and measuring the number of particles. So this is the experiment, and actually this give you many depth actually they gave. I mean, they just map the whole, almost whole earth, I would say. So from up to something like 2.7 kilometer depth that they went, and they are measuring the intensity. And at that 2.7 kilometer depth, when they reach there, which is equivalent to 8.4 kilometer of water, okay, deep water, when they reach there, and they were running that experiment, and there was no count. And all these guys, Narasimham tells me that they got tired. They just came back and told the scientific assistant who was there that if you find any count, then you send me a postcard. And they were in Bombay waiting for a postcard. That next 2 months, no postcard came. And after 2 months, they decided to celebrate. And they went to the Kalaghoda and had some good dinner because they have not seen anything. And that's what I told you, that this is the MNR null experiment. They have not seen anything. They have not seen anything is the most important statement. And because this is the depth intensity curve they can measure up to many, intensity was decreasing by many orders. And then this is the depth they are going. And finally here, no count here, actually. Okay. So they realize that they have now reached a place where they can do low background experiment like neutrino. So Menon, Ramanamurthy, before they published their result, Menon, Ramanamurthy, and Srikantan and Miyake, they published a paper in 1963 saying that we have found the ideal place for carrying out experiment to study cosmic neutrinos, improve the lower limit on photon lifetime, which at that time was 10 to the power 26 years, and to prove the existence of intermediate vector boson, the predicted mediator of weak nuclear force. So these are the kind of ideas they had suggested and in the paper, and told that we can do that experiment. And this paper started the ball rolling for a series of experiments at Kolar Goldfield over the next 30 years to study neutrinos and the baryon non-conservation. And Miyake, Narasimham, and Ramanamurthy, that is the MNR, they actually published their paper just a little later, 1964. And when this thing is going on, there is a strong competition for the neutrino experiment. And that time, 1963, the Jaipur Cosmic Ray Conference took place. The International Cosmic Ray Conference came to India. Many stalwarts came here. Here, Cecil Powell talking to Nehru over the after dinner, and here Baba and Menon in the dais. So in that conference, Ramanamurthy presented this muon depth intensity result from KGF and shows that we have found a place. M.G.K. Menon discussed the plan for setting up the neutrino experiment, and also Frederick Reines, who already discovered neutrinos, he actually discussed the plan of setting up neutrino experiment in South African mine. Actually, Frederick Reines wanted to start his experiment on Kolar Goldfield, but that's a different story. I'll tell you in another day. Okay, so proposal for direct, that's how the Tata Dharam Osaka City collaboration came into existence. And Arnold Wolfendel was a good friend of Menon also. He and his group from Dharam University and Miyake's group from Osaka City University joined the experiment. It was already known by that time that the high energy cosmic ray particles interact in the Earth's atmosphere and produce pions and kaons, and those pions decay and produce neutrinos. And in Soviet Union, those days Soviet Union, Jetsapin and Kuzmin, they have already calculated the flux of those muons, their angular distribution, so that so you know the intensity of these neutrinos. And then 1962, this is the Lederman and Steinbacher and Melchor. They have done this experiment where they have detected muon neutrino as a separate species than electron neutrino and measured their cross section to be around 10 to the power minus 38 centimeters square. So all these inputs, the flux, the cross section, everything was available to KGF group. They quickly estimated the expected rate of neutrino interaction underground and optimized the size and shape of the detector that is needed to detect these neutrinos immediately. And a long tunnel at 2.3 kilometer depth at the Heathcote shaft in Championship mine, the picture I have shown in the beginning, was chosen as the site for the experiment. And in the next, immediately within a short time, they started not one detector, but they put this 100-meter long tunnel, something like 7 detectors actually, of different shapes and size and different purpose. And there are 3 different kinds. This is, I pick up not so good picture from Narsimam thesis. And this is actually, it's called, first was this telescope. This has actually, neon flash tube. Neon flash tube is 1 centimeter tube, long tube, glass tube, and there will be low pressure neon gas will be there. When the charged particle will go, it will flash because of the high voltage applied. And then you can have a camera in the front and you can take picture. And if you put this neon flash tube next to each other, many of them stacked to each other, then you can get a track. Okay, and then you can connect those tracks to find out the track of this. So these actually are the neon flash tube here, and these are the lead plates in the middle, so that low energy particles will not disturb them, gamma rays and so on. So this is how they were, and then these two, they have the and here we have a magnet also in the middle. This is the magnet. That magnet came from Osaka City University group, and this is to measure the momentum of the particle. So they have all these series of experiments operational by beginning of 1965 itself, and they were rewarded very quickly, and they found the first neutrino event. You now can see the picture probably, that neon flash tube. These are round. Each one is a neon flash tube, and the particles is going. This is a picture. So this is the detector. So these are the neon flash tube trays. These are the lead plates, as I told you, and scintillators both sides to trigger. And then when the particle is going at that depth, 2.7 kilometer, 3 kilometer depth, and at that angle, almost horizontal, there is no way the neon from the surface can come and mimic this event. This has to be created locally by the neutrinos and producing this neon. And this is the first event that was actually published on the Independence Day, 15th August, in the physics letter on 1965. I call it Independence Day gift by the TIFR scientists to the nation. And within, after just 2 weeks after this present publication, Fred Reiners published his result from South African mine in PRL actually. So the Indian group beat him by 2 weeks actually. So much was the competition in those days. Okay, so this is how. So now importance of KGF neutrino experiment. Study of neutrinos underground became an important area of research in the field of particle physics around the world later, and several Nobel Prize winning discoveries were made using neutrinos underground. Even today, atmospheric neutrinos remain an exciting area of research in particle physics, and we propose such an experiment. Not only that, actually, so they are detecting neutrinos. Now they realize that not necessary that all the neutrinos will be created from the atmospheric neutrinos interacting in the rock. Many of these neutrinos may be coming straight from some sources. So they are starting also looking. So there's actually what they did is simple. They point back those neutrinos even to the sky and see what they're coming from. Of course, I don't think they expected any miracle to happen because their numbers were only a handful of neutrinos they measured. But they established that a process by which neutrino astronomy can be started. And this is, I call it the beginning of neutrino astronomy. And today, a huge detector, 1 kilometer cube detector at South Pole is doing only that, neutrino astronomy. And multi-messenger astronomy that we talk today is actually, for neutrinos is playing a part. And TIFR already published their result and in early days. And so I call it the starting of neutrino astronomy. There are some other events like polar event, puzzle event was detected there, which even today need explanation. There's something like some heavy particles is decaying in the air, in the gap between rock and the detector, and giving rise to this thing. And there was excitement in the 70s, and even Sally Glasso wrote papers on this one. And there was a famous paper by Rajsekaran and KVL Sharma also on this one in Pramana. So now, after this experiment, this comes the era of 70s, and this is the era of grand unified theories. In the early 70s, Georgia and Glasso, and at the same time, Abdul Salam and Jogeshpati, they have their theories of combining the 3 forces, the strong, weak, and electromagnetic, into single forces. And as a consequence of that, photon will decay. And that's what he said. Sally Glasso made the statement, diamonds are not forever, they will all decay. Okay, and it's a grand unified theory and photon decay. So strong, weak, and electromagnetic theory, I mean, coming from a strong one single gauge forces at large symptom. A consequence of that, you can put the quark and the leptons in the same multiplet, and they can be exchanged to each other through some gauge bosons at very heavy energy mass of the 10 to the 16 or so. And then if that happens, then the proton can get converted into a positron and a pi 0. Okay, so proton will be sitting there and will be there. So it's just a simple experiment. You just have collect a large number of protons and just wait there, let them decay, and you just record the decay product. That's all you have to do. And that's what the Indian group, that Kolar Goldfield, along with the Japanese colleagues, they tried to do in the late 70s. And what they're doing, and this is my colleagues, Krishna Swamy, Narasimham, they're all busy, testing those proportional counter that will be used. Not one or two proportional counter. The first experiment was 100-ton detector. It needed actually 1600 proportional counter of size 4 meter or 6 meter. Each of them were built not here, even in our workshop, at Kolar Goldfield itself, just in the lab there. So, so that's what we are testing there. All these proportional counters that were built here, and then slowly we built up. And that time I have joined already the group, and we started building layer by layer the stack of proportional counter, and in between iron plate, and build the detector slowly. Okay, and then when we finish, this is what it will look like, the complete detector, the stack of proportional counter X and Y direction, and looking at this is the electronics here, or the amplifier input. But the electronics lab was very huge, because all these 16,000 channel of electronic had to become, and then they have discriminated, recorded, and so on. So all electronics, everything was built actually at Kolar Gold by our engineer, by scientific officer, by technician was stationed at that point. And then, of course, another much bigger detector of something like 300 ton was built, called phase 2, and these two operational till 1992. That's some of the beautiful neutrino event. This neutrino event was going, upward going neutrino event in the detector, how they will look like. And here is what you can see, the atmospheric muons is going down. This is the atmospheric muon component, and if you go below, say something like 55 degree zenith angle, you will get only another component. These are all neutrino events. You have to tell that one. So physics studies push the proton lifetime to 10 to the power 31 years. New limits on magnetic monopole flux studies of neutrinos are some of the basic things that was done. And the people who are involved in that one, Krishna Swamy, Menon, Narasimham, Mondal, Srikantan, Sasi Dugat. I'm not, I mean, there were students, I'm only putting the names who are TIFR faculty here, just because otherwise it will be too big. Okay, so end of road for KGF experiment. The KGF experiment, which rode piggyback on the mining activities, had to finally close down when mines themselves closed down in 1992. This was final. So I think this was something to go. A glorious chapter of cutting-edge experimental particle physics research in India using in-house facilities and technologies got ended. Now let me come to this very high energy gamma ray astronomy that I was going to talk about. So far I have talked about the charge component, the proton and heavier elements in the cosmic rays, but already there was in the 60s, it is known that there are sources of very high energy gamma rays. And these high energy gamma rays, what they will do, they will come to our atmosphere and they produce electromagnetic shower. Gamma rays will produce, electron-positron pair, and then they will produce further gamma rays and so on. So quickly electromagnetic shower will be produced, but this will be unlike the air shower picture that I have shown, which is much broad, much spread out. This will be very concentrated, but these electrons actually will produce Cherenkov radiation in the atmosphere. Okay, and this Cherenkov radiation can be detected at by putting detectors at the surface and can be looked for such sources in the sky. And this was started in the very beginning, very exploratory, I would say. 2-mirror system was set up in UT in 1969, and just using the word surplus mirror that was available, and they put it up quickly, and then they set up this experiment. Of course, this experiment was just put some limit, didn't go much beyond that. But soon they expanded that array in the 70s, 8 large and 12 small mirror array at UT in 1977 started, and they shifted because UT they ran it for few years and looked some sources, and then because UT was not so good for doing such research, because most of the nights you have to do is cloudy in UT, and also the lights all around was increasing every day in UT. So they decided to find a new place, and they moved the whole array to Panchmari during mid-80s actually, and then a bigger array with 168 mirrors, all built 168 mirrors. Now these mirrors are all built at BRC facilities, and then they are all aluminized at the Thane actually in a private company, and that's how was built, all of them, and they were set up at Pachpadi during mid-90s. So Pachpadi they went in mid-80s, but this bigger setup with 168 mirror came in mid-90s, and then finally they moved it to the what you call the Hagar. So this array at Hanle and started in 2008. This is a beautiful site at you would know the Hanle where the optical telescope is located. This also is located there, and this is 7 stations. Each of them has 7 mirrors and beautifully packed. Many sources and many. I'm not going to talk about the physics, and that you can talk to the individual thing. And the people, the first exploratory work was done by this group of physicists, Chatterjee, Murthy, Ramanamurthy, Srikantan, and Tonwar, and later on Acharya, Bhatt, Varsachitni, Gupta, Vishwanath, they participated in this experiment here, and Pachpadi as well as in Hanle. And as you know, this field has grown up from there, and in Hanle now you have the big amazing telescope, which is running as a collaboration of the BRC, TIFR, and other institutions, IIA, and so on. Okay, so now let me move from the cosmic rays, from cosmic rays to particle accelerator. And again, it was in 60s that M.G.K. Menon and William Owen Locke. William Owen Locke, he became the leader of the third nuclear emulsion group. But there's history. William Owen Locke was the co-graduate student with Menon at Bristol in the lab of Cecil Powell. So they're good. So when Locke became the leader of the nuclear emulsion group in the early 60s, Menon immediately contacted him, and then that's how they started the collaboration between TIFR and CERN in first in emulsion chambers, and then so during the early 60s, TIFR was involved in the analysis, in the only analysis of nuclear emulsion exposed to beams of ions and photons at CERN. But then the emulsion was coming to an end, era of emulsion, and bubble chamber was coming up. So TIFR decided to go establish a bubble chamber group, and then some of the physics highlight in those days are the production and decay properties of hypernuclei using emulsion, study of this antiproton photon-antiproton interaction using Sackley bubble chamber. This is the large European bubble chamber with the European hybrid spectrometer to study production and decay properties of charm particles. There are many papers they published in those days, and many people actually participated from there. Ganguly, Guttu, Malhotra, Subramaniam, Raghavan, Rangaswamy, N.K. Rao, he was in TIFR at that time. M.S. Swamy, who moved later to Aligarh University, Muslim University, he was in TIFR. So these are the people who are involved in this bubble chamber days. And in fact, Daniel also has a paper. On one paper, I know that in the emulsion era, but I don't know how much he was involved actually. Well, then really came the L3 experiment, LAPE experiment in the 80s at CERN, and that is the time TIFR went there full play. So TIFR is always known for instrumentation development. So this time TIFR not using the data, but decided to put detector there. So this fabricated the glass tube proportional chamber for the hadron calorimeter NCAP with the Aachen group, and Suresh Tonwar played a big role in that one in building those brass proportional counters in TIFR using his earlier experience in instrumentation, and the significant role in the software development that time of this one. Sunanda was in charge of the software and experiment. That is almost we are now in our era. So TIFR was responsible fully for this L3 Z line shape fit and analysis over the entire left 100 period. Well, I'll tell you what that would mean. Actually, it means a lot. And the precision determinants of Z mass, widths, and coupling of distinct spaces. I'll come to that picture, then we'll know. Then also strong contribution in B physics using neural network. Neural network and AI and things like that is the buzzword these days. But TIFR scientists have started in the late 80s already using neural network for analyzing of the data. The quantum chromodynamic Higgs searches were continuing, and then the energy was increased from the energy was increased from 100 GeV to 200 GeV, and for measuring the W mass and so on and physics. So this is what I'm talking, the line shape. See, once the LAPE was running, E plus E minus was colliding in the Z peak. So they can scan the Z peak from the Z peak was at 91 GeV, but you scan from 88 GeV to 94 GeV to get the whole spectrum. This is the resonant projection of Z. And studying the shape of this line shape, they can estimate or extract the parameters of the standard model. In fact, this analysis what put the standard model on the strong footing. And that was the main contribution of the TIFR group that time. And in fact, Atul Group even today is a part of the particle data group. And they stand up for Z mass, top quark mass, 6 mass, strong coupling constant, and so on. And many people are involved in that time. Tariq, Sunando, Somnath, Atul, Prince Malhotra, Raghavan, Sudhakar, Talwar, Mojumdar. This is Kajuri, Govindo, Gagan Mohanty, and so on. And many other students, of course. And so TIFR and D0, we joined in 1990 because the closure of the KGF group decided to have some of their own. So we decided in 1990, participated in the design and center muon scintillator. We have, from the beginning, we should contribute detectors. So we built the muon scintillator detector and fabricated 120 muon scintillator detector using help of BRC and TIFR facilities and performance studies, online studies, all voltage. This is one of our students is building those, scintillator fiber detector for the muon detector. And these are the detectors that we have built. In fact, if you have visitors need to go to see D0, they will see our detectors only because this is the outermost layer. And this plays a very good role because the muon timing was very important from background. And so they put this detector, we put this detector layer. In the physics also, we are involved in top free physics, supersymmetry, leptoquark, composite detector dimension. 8 TIFR students received PhD through their participation in digital experiment. So the people that participated here, Acharya, Sudeshna Banerjee, Shashi Dugan, Krishna Swami, Mondal, Natsimam, Srinivas Rao, Vishwanath, are the main participation from TIFR side. Now, I have now given you some idea what was this field was in TIFR. Now let's look into the future. So TIFR has a glorious past in the area of cosmic rays and energy physics. You will agree with me after seeing those slides. Several pioneering experiments were performed using indigenously developed technology, tools, and detectors. Very good. While the size of the group has shrunk, I think our group is very small. I was shouting here for almost 15 years that these groups are disappearing, but now look, they are disappearing. But it is heartening to note that the current members of the group are holding on to the tradition, at least to some extent. The UT Earth Hour array is running continuously from 1960 onward, and now this you can see the real Earth Hour array, how big it is from that original one. Onward in different shapes and sizes, breaking new ground and making discoveries in new areas. And we all know that. The CMS experiment at CERN by TIFR groups have made major hardware as well as software contribution, has made fundamental discoveries. TIFR has also made hardware contribution to the Bell 2 experiment at KK. Looking forward to new discoveries there too. It is, however, not clear if ion-OICAL experiment, the largest fully funded basic science project conceived and designed mostly at TIFR, will ever see light at the end of the tunnel. I am not sure. I'm not so hopeful. So our field allows students, engineers, scientists to put their head together and develop technologies and tools before even starting the experiment. You have seen that you have developed all those things. This is a great learning experience for students and engineers who will go through this drilling exercise, will be better equipped to face the new technological challenges of the emerging world. TIFR was the only institute in the country to take up such projects from inception and convert them into real experiments. That's in many fields, not only in our. Will TIFR abandon this path? I leave it to the current generation to ponder over this.
Thank you, Professor Mandal, for such a nice overview. Now this session is over. Let us thank all the speakers of this session for such a wonderful talk. And now there is some announcement. I mean, basically two announcements. One is we are going to break for the tea. But at the same time, as you go out, there will be also an exhibition of different photographs which is going on. And there is a quiz competition for that, or you can say there is a prize for identifying those photographs. So please do participate in that. And the idea is, I mean, one is that whether you can identify those events, those people, the occasion. And the second is also for our own purpose, our own knowledge that, whatever things that you know or that insights that you have, we also would like to know about those. So please do take part in that and identifying those photographs. Uh, Now, one last request is we will be assembling here after 30 minutes again for the second session. Again, all the sessions, there will be, because of the nature of these talks, there will be no question and answer. So please talk to the speakers after the session is over, and you can have a lot of your time you can spend, reminiscing all your memories. So thank you very much. I also wish to thank all the Zoom people who have participants who have at various times of the day. I mean, some of them for late night for them, or late evening for them, or very early morning for them. So thank you for joining. Another 30 minutes we will come back here. So let's break for the tea. Before the tea, please come to the stairs of the Almond Grove for the photograph. Thank you very much.
हेलो, मुझे कोस्ट बना दो। पांडु जी, मेक मी कोस्ट। हेलो हेलो हेलो, मेक मी कोस्ट। पोडियम पोडियम वाला है।
Professor Acharya? Okay. Okay, welcome back, all of you. I hope you had a nice break and thanks for the photograph. And also, again, I remind you, please do take part in that quiz or whatever we can call it competition because for the photograph identification because there are prizes for this. It is also down the memory lane for us, all of us. So you can identify the people, occasion, venue and everything, that will really be very nice for our archives people also. So having said that, let's go to second session of today. And I request Professor B.S. Acharya to chair this session. And there will be two talks. So Professor Acharya.
Language. Can I get this out? Just got it? Get a glass of water. Sorry. Excuse me 1 minute.
Yeah. So let me give you a little bit of the motivation for OT radio telescope. In the 50s, there were all these sky surveys, the telescopes, which are the dishes and things like that, which were got from the war. People are making surveys of the sky at high galactic altitudes at low frequencies. The 3C catalog at 170 megahertz was one of the reference catalogs at that time. The problem in radio astronomy is that all the telescopes are diffraction limited, so the resolution is very poor, lambda by d. So even a 45-meter dish or a 100-meter dish has got a resolution only half a degree or worse at meter wavelength. So because of the poor angular resolution, the position is very not well known, and because of this, it's not possible to identify what the optical equivalent of the radio source was. Now, later years, people actually tended to go to high frequencies because lambda is smaller and you can get better resolution. But the science at high and low frequencies is very different. And if I keep talking about meter wavelength, it's because for the next 2-3 decades, the low frequency radio astronomy was neglected. There was nothing much happening. And everything was happening at high frequency. And this is the lacuna which actually UT telescope would fill. Now, since you had no optical identification of the source, you had no estimate of the distance, and so you had all these sources, hundreds of them. You have no idea where they were, what they are they near, are they far, are they strong, are they weak? And it was a mystery at that time. But radio astronomers were not prepared to sit quietly. They started to do statistical studies of these sources, famous log and log S curve. Essentially, if you look at the number of sources, it's proportional to the volume, which is proportional to R cubed. The flux of the source, if you think of it as a standard candle, decreases 1 over R squared. If we plot log and log S in a steady state kind of picture, it should have a slope of 1.5. Now, when radio astronomers looked at their data and made these plots, they found that they had a slope of 1.8, which created a lot of controversy. They concluded that there were more sources farther away, which is also in earlier epochs. And so this evolutionary model is required for explaining the data. Previously, you had two competing models, the steady state model where nothing changed, everything was same everywhere. And the evolutionary model from the Big Bang, which said that things will be changing, you can't expect things to be the same at all times. So this was a strong indicator for the evolutionary models at that time, which first kind of indication about this. So there's a lot of interest in knowing what are these radio sources? Are they really far away? Are they strong? Because people are questioning whether the whole methodology of this analysis. So the breakthrough came in studying lunar occultations and this discovery of quasars. The position of the ephemeris of the moon is known as great accuracy. So you know the position, the angular size at any with accuracy of any amount of accuracy you want. So if you see a source going behind the moon from the time of occultation, going behind and coming back, you can actually get a good estimate with a high resolution of the angular position of the source. So since all these 3C sources were known, people were actually using the lunar ephemeris to predict when they would get occulted within some uncertainty. And there was a prediction that in Australia, this 3C273, I am sorry, this 3C273 would get occulted a few times in 1962. And so these occultations were observed, and they got the position of the source with great accuracy, better than a second of arc. And the optical astronomers could locate a source, a star-like object, which they call which became what is known as a QSO. And when they measured the spectrum of the source, they found it redshifted with a redshift of 1.58. Now, as you know, once you have a redshift from the Hubble distance relation, you can get a distance. And both the redshift and the distance made this one of the most distant sources known at that time. And it's also a very bright source, so it is also most luminous. And so suddenly the radio sources became very interesting because they were one of the most luminous objects in the sky. Now, the beauty of it was that for studying lunar occultation, all you needed was a large collecting area and the ability to track. At that time, most of the large collecting areas and tracking sources were actually two-dimensional dishes, parabolas, which are very costly to build. It's much cheaper to build a cylinder which is just as good for lunar occultation, but it costs much less, but it requires some extra electronics to do what is called phasing, which I'll explain in a minute. So this is what inspired Soru to propose a telescope to study lunar occultation, to just survey the sky using lunar occultation. The other studies were essentially targeted to, I know a source which is going behind, so I'll study it. Here he wanted to make a blind survey, statistically, no bias, just pick up whatever gets occulted, and that's an unbiased sample of sources. Statistically, that is what is required if you want to make any proper study. So to get this large collecting area, he proposed to have a cylinder, which is half a kilometer long, 30 meters wide, mounted with an effective area of 8,000 square meters. Visitors at Ooty would tell them, yeah, this telescope is 4 times the size of a Jodrell bank dish, which is one everybody knew at that time. So we didn't tell them that sensitivity is more than just collecting area, but it was not required. So the telescope is made equatorially mounted by essentially mounting it on a north-south hill, whose slope is the same as the latitude of the place, because of which the axis of the telescope becomes parallel to the axis of the Earth. And just by rotating the cylinder on its axis, you can follow it, track its source. After some survey of South India, they came up with a place, and this is possible because India is close to the equator. You couldn't do this in Europe and places like that because the slope will be too high. So with some survey, they actually found a place in Ooty, 11 degrees latitude, and after this thing, I mean, Ooty was also, people were familiar with it because cosmic ray was doing something there. And so they said on this, and they started construction between 1967 and 1970. A parabolic dish, you see, if all the radiation comes to the focus in phase because of reflection and propagation. But for a cylinder, you have essentially a line focus. And so what you need to do is on this line, you have all this, you have a bunch of dipoles at the focus. And by adding the signal from all the dipoles with appropriate phase differences and phase and delay compensation, you can actually form a beam or a point of focus in different parts of the sky. So a complicated system of electromagnetic and mechanical phase shifters was generated. Essentially, the signals from all the dishes are now combined with some appropriate phase shifts, because of which you could essentially get a beam which in the north-south direction would go from plus minus 30 degrees or a little more. The frequency of telescope was 327 megahertz, resolution was 2 degrees east-west because the telescope is only 30 meters, and 5 minutes of arc in the north-south, and you can track for 9 hours. You can see the telescope in the west, in the east. It's a very impressive thing to see it rotating, trundling along. And this is where the focus here of all the dipoles. This is a picture of construction of Ooty telescope. You can see ground being broken by MGK Menon, and at various stages, dishes going, the cylinders going up. They're going up. Many of them have come up. You can see dipoles here, and finally, in 1970, things have started to work. So let me come back to lunar occultation a little bit. The first occultation observed at Ooty was on February 18, 1970. The source 22.21. Unfortunately, I could not locate the original place for that, but at least I've shown you a source getting occulted, a strong source, point source. You can see these frontal fringes, diffraction at the edge, which is what you see for a typical lunar occultation. If you look at this picture here, you can see at this time, the source is getting occulted. So you know the position of the moon. At this time, it's coming out. Again, you know the position of the moon. You know the diameter. So you draw the circle, they intersect at some point. That is the position. And the moon's position is known accurately. So you know the position of this to a second of arc. You also notice one thing, that when the source is getting occulted, the edge of the moon is crossing the source in one direction. When the source is coming out, the edge of the moon is coming out in a different direction. And so you essentially get information at different position angles. During immersion, you would see it as a double source. During immersion, you would see it as a single source. And from this, you can get two-dimensional information about the source. Also, if you look at the Ooty beam is very wide, 2 degrees in the north-south. but is very narrow in the, 2 degrees in the east-west, but is narrow in the north-south. So essentially, the UT telescope picks up fixed regions of the moon and 12 beams covering the, it covers the whole moon all the time, and you simply keep following the moon as the moon trundles along in the sky. So regular observations tracking the moon for 9 hours goes on for the next decade or so. And typically every day you would see 1 or 2 new sources. Many of them are very routine, boring sources, but some of them are interesting. But this is what you need to do if you want to get a statistically stable sample. So occultation from this, so during this period, 1970 to 1980, something like 1,000 sources were observed, positions were found, structure was found, they were cataloged, published, and so forth. The most interesting thing which everybody was, what the UT telescope was built for, was to do cosmology and study things like what's happening in the universe. So they looked at all the sources, the size of the source versus the flux. And this is what is now the first statistically significant study of theta S in radio astronomy. And essentially, if you look at this plot here, which is plotting this size of the source against flux, all these low frequencies, all the low flux and low angular studies, angular size studies are coming from UT. There's one small survey which is isolated here, but nobody believed in it until the UT results show that this is how the shape is going to be. Ideally, in a simple universe, Euclidean universe, you'd expect this to be a straight line, but you can see now that the slope is changing. Again, you need a model which is more than just the steady state. And when they did the statistical study of this, they found that to explain this, you need evolution again, with sources being smaller at earlier epochs. Again, this was proving that this evolutionary model was required. But at this point in the 1970s, most astronomers sort of accepted that the steady state was not really viable. So astronomically, this was not a big deal. But in the local press, it was a big deal because they saw 2 Indian astronomers fighting it out, and so it made a bit of a splash. A number of interesting sources got occulted. They were studied. For papers were published. You can see the source. So 3 components you can very clearly see during one occultation. You can see this 3 components, this another 3 components, different position angles, and you can get things like separation. There are 3 components, and if you look at it, you'll probably find that this is the optical galaxy. And these studies actually were published and printed and go on. But regular observations came to the stop by the end of the decade because people sort of, most of the sources were very boring. There's a lot of effort to observing all these charts and keeping records. And you get only 1 or 2 sources, maybe every few months. And people lost patience and this thing sort of died. It came to an end. Now, the UT telescope, this occultation takes only about 10 hours a day. So there were other things to be done with the empty time of the telescope. And so some of the big things were, let me just give. One is interplanetary scintillation. If you look at a point source through the solar wind, it twinkles. It scintillates just like a star twinkles when you look at it through the atmosphere. Just like a star twinkles, but a planet doesn't because different points of the planets move the twinkling out. Large sources don't twinkle, only when sources are smaller than something like 0.3 seconds of arc, which is a second of arc, best resolution at that time was something like a second of arc. Only if a source is smaller than 0.2, 0.3 seconds of arc will it twinkle, because otherwise it gets wiped out because of averaging. And so if you now make models for the solar wind by studying a source, if you see twinkling or scintillation, you can actually get size estimates and decide how much flux is in the compact component, how much is in the extended, and you start making information, get information about the source. So as a part of this, there was a regular, scintillation project going on. An IPS survey was made of the southern sky. Till then, all the IPS surveys were done in the north, Cambridge. And so this is the first IPS survey of the southern sky. A survey of the galactic plane was done using interplanetary scintillation, and we found that while in the galactic anti-center direction, you could see a lot of scintillating sources. In the galactic center direction, There was no scintillating sources, which showed that there was enhanced scattering of interstellar scattering in this galactic plane, in the galactic center. After about 1990, when the UT telescope was refurbished, it became fast and more sensitive. The interest of using interplanetary scintillation to getting source sizes changed, and rather they use interplanetary scintillation to study the solar wind itself. So there's a whole lot of a whole decade was actually used for studying the solar wind. There are two kinds of studies you could do. One is you point this telescope to one radio source and just monitor it for 10 hours. And once in a while you see things like a transient where some coronal transient event is passing across the line of sight. This is the intensity of the scintillation. This is solar wind velocity, which you can estimate. And you can model this and see what kind of things are happening and correlate it with things happening on the sun. It's another event. It's got a very different shape, and so the geometry is very different. And so this is a thing which you could do. It was done for about a few years. The other thing which has been done is essentially try to get a whole sky picture by studying different sources every day and trying to see how things vary. With the new telescope, which is the enhanced sensitivity, you could study something like 600 scintillating sources at any given time. So the telescope was used to study these 600 sources day after day after day. And if something changed from day to day, you could make models of it to see what is changing in which part of the sky and try to correlate it with things happening on the sun. This sort of interplanetary weather monitoring was very valuable in many ways. It was very interesting. It's the only place which you could do it. But again, it was a very routine thing and sort of it didn't have too much interest for the group. Other projects, you had pulsar observations, the telescope, the large collecting area. So things like the first publication of the UT telescope was actually a pulsar paper where they actually found an error in this measurement properties of this and they published it locally. There was a pulsar search. They detected some 8 pulsars. There were studies of interstellar scattering where they had coordinated observation between UT and Australia. So various things happened in pulsars. Spectroscopy was a big thing for some time. They put a limit on the amount of deuterium in the galaxy. They started studying radio recombination lines, essentially lines of hydrogen transitioning in the neighborhood of 270 quantum number, which falls in the radio band. And so this could be detected, and you could make studies of this to study how the interstellar property behaves in different directions. This was largely taken up by the Raman Research Institute and their students. So by the end of the decade, that is the beginning of 1970s, 80s, the interest in occultation died. There were some bit pieces happening in pulsars and scintillation. And so the group started wondering what we should do next. And the obvious thing was the whole radio astronomy world was going to synthesis, observations of interferometry and synthesis. There was an absence of, I think they found a state, sorry. There was an absence of good synthetic synthesis radio telescopes at low galactic latitude, low equatorial, near the equator at meter wavelength. And so the group decided to build a synthesis telescope at UT, what they call the UT synthesis radio telescope. I think you have to change the font, otherwise I don't think I can see it. But anyway, let me continue. So what they did was essentially they had the UT telescope here, and they had 9 telescopes around it, going up to 4 kilometers. Again, we were all stuck with cylinders in those days. So they were all baby cylinders, north cylinder, south cylinder, and so forth. And essentially, you form interferometers between UT telescope and each of the cylinders. Now, if you look at what an interferometer measures, if you think of a source as a 2-dimensional function and take its Fourier transform, the interferometer measures one Fourier component of this particular source. So each interferometer measures one Fourier component. As the Earth rotates, the orientation of the telescope with respect to the source changes, so it measures different Fourier components. And so essentially what happens is, at the end of 9 hours of observing, you get a bunch of Fourier components which you measure, you put it on a grid, take its inverse transform, and do some image processing, and you get a map of the source. So more elements you have, the more Fourier components you have, the better your image. So a bunch of images were studied, sources were studied, and as I said, there's a source, NGC 4631. At high frequencies, a very narrow source. At low frequencies, it becomes much bigger. So you think there is a diffusion of electrons, make models. Galactic plane survey, there was a galactic plane survey, SS 433, W50. Very steep spectrum of source where essentially the source can be seen only at low frequencies. It can't be seen at high frequencies. So it's seen at UT, but not in the other telescopes in the world. So this went on for 2-3 years, but then after that, essentially the interest also died down because it was very hard to maintain. The cylinders which we had, worked on the same principle as the phase shifters of UT, which that electromechanical system was creating a lot of trouble and needed a lot of maintenance. And so they were only 4 kilometers away by the line of sight. There's a deep valley in between, and there's a very poor road system. So often getting to these places was often a big project. And so after about 3-4, maybe by mid-80s, with it sort of the imaging stopped and people stopped using the principal telescope. So again, people started wondering what next should we do. So there's a need for a high quality imaging instrument at meter wavelength because all the telescopes which are there at that time were at high latitude and they also had high frequency. And the group had a lot of expertise at low frequencies. So essentially they said, let's think about making a competitive low frequency radio telescope, what they call the giant meter wave radio telescope. Also, the group knew how to make cost-effective antennas. Cylinders were very effective in collecting area. And it was believed that India would be much more radio quiet compared to the Western world because there's not much development. You can always find places where there's no interference. It turned out to be a false assumption because after we built it, cell phones grew everywhere and we had a lot of problems. So by 1984, a draft proposal was made for 36 cylinders of 100 meter size scattered over 30 kilometers. It is also clear when this was all being talked about that you could have the telescope in a place like Ooty. Because close to the equator, the ionospheric scintillation is much worse. It's horrible, in fact. So very often, the nighttime observations at Ooty were washed out with scintillation. And the experts told us that you should have expected this because there's something called the electrojet, equatorial electrojet, which produces a lot of scintillation. If you want to get decent observations at low frequencies, you have to go north. Now, so leaving Ooty, Bangalore was a necessity just to avoid the ionospheric problems at low frequency. In 1985, there was an IU meeting in Delhi where a lot of astronomers came, and there's a lot of discussion on this telescope. And finally, they all convinced the group that cylinders are not a good way to go if you really want to have high quality dishes, high quality observations. You need to have dishes. So essentially, this dishes versus dashes was the conclusion at the end of the symposium, because cylinders at if they go northern latitudes, have to be at a very steep slope. Or if you make them altazimuth, there's a lot of issues they're not going to now. By 1970, about 30, the proposal changed from this original thing of 36 cylinders to 30 dishes of 45 meters of an inexpensive design. It is not specified. By 1988, the proposal was cleared and funded. The design for the dish, inexpensive dish, worked out. And essentially, during this period, 86 to 89, site surveys were done and Kodak was selected 80 kilometers from Pune. Competing was indoor, it was supported by CAT, but then finally they decided to stick to Pune because it's closer to Bombay. Land acquisition takes place, buildings started at Pune University for the Pune campus and so forth. And by 1990, construction of the antenna starts. So let me give an overview of GMRT, which many of you know. It consists of 30 antennas of 45 meters, 12 in a central square, and 3 in 3 arms each with about 6 antennas. The idea of having this central square arm is because, as I said, each interferometer measures one frequency component of the source. And to measure large sources, you need short baselines. To measure compact size, you need long baselines. So this is a compromise where you can measure both large and small sources without moving antennas. The dishes were made, if you look at it, they're practically transparent. That is a smart design, smart stretch mesh attached to rope trusses. Normal other dishes, you'll see a lot of circumferential steel members. Here, those steel members are simply ropes. Dishes were connected by optical fiber to the lab, which is the first in radio astronomy, but common now. Large amount of data because of the spectral correlator. And these are essentially, and as they feed, you had 4 feeds you could rotate to bring the focus, and they would observe at these frequencies 150 megahertz, 235, 327, 610, and 100 to 1000 to 1500 megahertz. This is just a picture of construction of the telescope. I'll go quickly. I'll not go into this. We had assistance from various people. And I'll come to the operation. So in 2001, August, GMRT was dedicated to the scientific world by Sri Ratan Tata, chairman of the TIFR Council. And a call for proposals was sent, and every 6 months, the proposals are screened, limited, and time is allocated, and people are known in advance when they're observing, so they can plan. The first GMRT cycle started in January 2002, and typically every GMRT proposal call will be oversubscribed by a factor of 2, and you will get about 60 odd proposals, half of them typically from the international community. I'll talk about the science and usage of GMRT. I mean, this is the pie chart which shows who has used GMRT in the first 38 cycles. Currently, the 43rd is running. And I will not talk about the science which is coming out very much because it's a versatile instrument which can be do almost everything you can think of in radio astronomy can do. And typically about 50 papers are published in a year based on GMRT results. All GMRT data, essentially interferomic data, is archived. And the rule is that the proposer has complete rights for it for 18 months, and after that, it is public to the world. Anybody can take the data and analyze it. This is typically a GMRT time observing. If you look at it, all in time slots, different people giving time at different places. This is black is where frequency, the feed rotates. Black is maintenance. There'll be empty slots which you can use if you want. You get the approval of the director. And so this kind of observation is made at the beginning of the GMRT cycle for 6 months in advance. And everybody knows what the telescope is going to be doing for the next 6 months. GMRT started getting upgraded because, as I said, the electronics was very old. And so around from 2012 to 19, most of the systems have been upgraded. The frequency feeds have been modified. The picture I showed you of the eyes of the radio telescope now is completely gone. It's almost completely observable. Observing bandwidth has increased, control systems have changed, all kinds of things are done. And this is how the sensitivity of the UT telescope is sort of changed. You can see that the sensitivity is now sitting over here. And the only thing which is going to be more sensitive is the square kilometer array when it is completed probably by the end of the decade. So the GMRT is essentially the most sensitive telescope in these low frequencies, and is the premier telescope maybe for the next decade. I'll stop here. And I asked our Dean NCRA, Nitin Kanekar, to give me a list of what he thinks are the 5 most important papers which came from GMRT. I won't even discuss them. I'll just put them up for you to read. If you're interested, we can talk about them. And I will stop here. Thank you.
Just 1 minute. Yes, I do. Yeah.
Thank you, Pramesh Rao, for your nice talk. summarizing the activities of radio astronomy in TIFR. So let's move on. Next talk is on astronomy, balloons to satellites. It will be delivered by Dr. Raghuram Rao. Professor Raghuram Rao, he also hails from Kasaragod district, like the previous speaker, in the northern tip of Kerala. He lives in Mumbai, okay, and he joined in 1977 to the X-ray astronomy group of TIFR and retired in 2019. Okay, so this one. So his most his contributions as well as his interest primarily rests on developing X-ray instruments for space as well as balloon observations, and also configuring space payloads for diverse applications using balloon as well as satellites. He was also involved in projects such as Indian X-ray astronomy experiment, as well as he has fabricated CZT imager for the AstroSat satellite. It is one of the 5 instruments. Okay, CZT imageries. Okay, Professor Rao.
Thank you, Acharya.
Yeah.
So, good afternoon. It is so nice being here and meeting all the old friends. And I'll be talking about the landmark in this area, balloon astronomy, balloons and satellites, basically space astronomy. And this job is a bit simple because the landmark in space astronomy in TIFR is AstroSat. We all know about AstroSat. And as Mayank was asking me to reduce so that we have lunch in time, so I will make it fast and tell why AstroSat is the landmark and how we achieved that. And while doing so, my approach will be completely personal and anecdotal rather than going to the rigorous of that what cost all of us to work on this very wonderful instrument, how we went about doing that. So there may be, I may be biased in picking up some names and ignoring some names. I ask for apologies in advance. Basically, space astronomy, I think I should introduce with some pedagogical picture. So astronomy is nothing but studying about the cosmos, studying about the stars. So in this picture, what we show is that we use the all branches of electromagnetic radiation, look at the cosmos. And this all the way from radio, infrared, optical, X-ray, gamma rays, and sometimes we do use non-EM signals also, like neutrinos or particles, even cosmic rays. Okay. Now the thing is, what is shown here is that most of this electromagnetic radiation is absorbed by Earth's atmosphere. We don't see them here. We have to take the instrument up above the surface, at least to have some chance of looking at them. What is plotted in the half length, how high you need to go above the Earth's surface in kilometers, so that these wavelengths, at least 50% of the flux come to the top of the atmosphere is visible. So you can see that only windows are radio and narrow optical beam, optical range. So in that sense, optical astronomy has huge advantage the last 300 years, and the space astronomy is only recent, last 40, 50 years. And in fact, from the optical observation, we know quite a lot about cosmos. We know almost everything. In fact, if you can, there's some in the late, in 20th century, every single known laws of physics are applied up there in the skies, and every theory is proved to be operational there. So there is like argument in the arrogant saying that, like argument said, give me a liver long enough and I'll move the earth. Similarly, Eddington said that even if there is a civilization which is covered by dust, we can't see outside. Give them laws of physics, they can figure out there are stars, and we can calculate by simple pen and paper what is their mass, size, and temperature of stars. Okay. Now, when I say that every single principle that we physicists discover in the earth is applicable there, this is simultaneously a profound and a trivial statement. Profound in the sense that this tiny earth, what we discover in the laboratory, is applicable throughout the universe. And trivial in the sense, if it is not applicable, we won't know it. We won't realize it. We won't accept it. Okay. Now, what I want to emphasize here in the space session is that there exist objects in the universe which copiously emit in non-optical region, like the strange animals called gamma ray bursts, which emit in a matter of seconds, equivalent of the rest mass of the whole sun. And now we have some idea that are coming during the birth or death of compact objects, but exactly how we generate, we don't know. Similarly, blazars, which from the end of the universe beaming towards us. So there are so many mysteries in this one. So space astronomy is important. That is the context I want to put in this one. Now, there is a fascinating story of space astronomy, how it is developed from Second World War onwards. Because to measure this radiation, which cannot come up to the Earth, you have to take the instrument above, either balloons, rockets, or satellites. So initially, there are captured German V2 rockets, which were used to send instrument, measure. They are very, very low sensitive instruments. They did measure X-rays coming from sun. And as I said earlier, all physics of stars we know. And from our knowledge of physics of stars, it's unlikely that the then instruments will detect anything from stars, because sun emits very, very feeble X-rays, one part in 10 million of the whatever it emits in optical. So general consensus, there's nowhere else to be seen. Okay. Then these are from rocket, which can observe stars only for a few seconds. Then 57 to the first Sputnik was launched. It's a great space race. And 62, first non-cell X-ray source was detected at the birth of X-ray astronomy. So the detection of something so bright is contrary to whatever we expected from the traditional classical physics. After that, the space astronomy zoomed up. So the first X-ray source detected Cygnus X1, and it is known to be a black hole sources, because the black holes, till then we had only concept from the radio observation. The first confirmation of there exist some objects which is massive than any ordinary stars, and this is nothing we know about this one. So many of the space astronomy observation, in particular X-ray astronomy, is about such compact objects. Now, where are we in TIFR? I want to segregate the period in three periods, which is completely subjective. Okay, the first is what I call 67 to 80, the era of dreamers. Okay, so when the first X-ray source was detected in 62, there is fascinating development happening in MIT and American Science and Engineering, a private institute funded by Riccardo Giacconi, who got Nobel Prize in 2002. B.V. Kandan was witnessing all this development right then and there, and he came back and initiated in TIFR. So there is when I joined in 77, this issue was full of excitement of this new area of X-ray astronomy, and I want to share a little bit of the excitement because I was toward the end of it. And 80 to 2000, I'll call era of strugglers. I'll come to that wide way, say that. And 2000 onwards, when we proposed astrosat in this one, let's say new renaissance era, and we could make competitive observation in space astronomy. And Nabhamandal gave a list of pioneers in X-ray astronomy, and he selected 3 for his thing. From that same list, I'm selecting 3 who have done pioneering work in space astronomy in TIFR. Of course, B.V. Srikantan, as I said, she was witnessing the birth and growth of X-ray astronomy. He was fascinated by it. Immediately come and say that, of course, we had this well-developed balloon
uh, infrastructure mainly for cosmic rays. It was straightforward and almost trivial to convert it to a platform for X-ray observations. And he motivated the band of youngsters to do the X-ray astronomy in this one. And of course, if you take a lenient view that space astronomy can be done not only by electromagnetic radiation, but also particles. So Kumar, this was, I mean, when we are in the students, it was fascinating that there is Kumar, he proposed something for a space lab, got accepted, and something made from India will go in space lab and fly and measure the cosmic rays and measure the composition anomalous cosmic rays. In that sense, there is a pioneering work by Kumar Biswas. Of course, Professor Daniel was a very well-known cosmic ray physicist, but he's the person initially handled the balloon facility, and later on he was instrumental leading the infrared group, part of the space astronomy in TIFR. Now, as soon as this one initial days from 62, let's say almost 75 or 77, most of the observations are done by rockets and balloons. And since in TIFR, we could quickly convert our know-how to make the X-ray measurements, we were highly competitive. Looking at the Cygnus X1, I'll come back again and again to this source, first black hole source, and how rapid changes are seen, okay, and some other source, this one. So any measurement in that is fantastic observation, and we had enough technical expertise, enough enthusiasm, enough youngsters who are dreaming and dreaming big and doing this one, wonderful work in that. Now, out of this many things, I want to subjectively pick out these two gentlemen. There are many people contributed, but there are two reasons I want to highlight these two gentlemen. One, they are very strong personal influence on me. Second, they are the prime motivating and force for realizing AstroSat. Professor Prahlad Agrawal, my thesis guide, of course, he taught me everything about the building X-ray detectors, but I'm mostly talking about the other style of learning which I did with this student. So he was part of a satellite experiment called HEVO-1 and building proportional counters at Caltech. When he came back to India, he brought the technology and he was using it to multiple projects in India. So one of the most fascinating things in Professor Agrawal is that nothing is impossible for him. In the sense, suppose we say that this won't work, you will always bang his table and say, why not? Okay, so that why not culture in the group is mainly motivated by Professor Agrawal. So here, one of the large area X-ray proportional counter which he built and operated, and this is the forerunner for the biggest, one of the biggest instruments in AstroSat. He was, and one more thing, he is extremely practical man. Without his practicality and his political sensitivity, it would have been impossible to maneuver and move such a huge project like AstroSat through various national organizations and ISRO culture. And Professor Shyam Tandon is a completely contrast in nature, in the sense that he's the one person during those days, everything was built from first principle, and there were some style of doing things very fast and quickly. He's the one, he imposed quality in each and every one what is being done. So this quality consciousness is many of us learned painfully later on with our close interaction with the ISRO culture and ISRO way of doing things. From first principle, he has imbibed from beginning itself. And other things which is extremely fascinating about him is that from every single problem, maybe technical, maybe physics, maybe philosophy, he has the ability to look at it and understand it from first principle and quickly change and look at it from any differing perspective. And he is the one of person responsible for the infrared telescope. Actually, it's a technology marvel. I remember in the 80s, Baji covering this and putting in the front page of Frontline and saying that what a wonderful instrument it is. That I'll come to this. These are the two other people who contributed to for the Ashok. Now, at that time, there were multiple ambitious projects. Okay, so we are doing extremely competitive research as compared anywhere in the world. Like, for example, as I explained, Professor Agrawal was doing the largest hard X-ray telescope, and Tandon was the largest far infrared telescope. And there is a University of Calgary collaboration for hard X-ray astronomy. And Professor Damle at that time also realized that you need huge collaboration, and he had a vibrant collaboration with the Soviet people for a Natalia Gamma ray experiment. And as I explained, there will be space lab experiment. And in the west, things were moving on from balloons and rockets to satellites. Okay, so the Indian rocket and satellite industry is in a nascent stage. As early as 1975, Soviet Union gave an opportunity to launch the Indian satellite. That was basically an experience for Indian people to build satellites. And in that thing, the neutron monitor TIFR collaborated, the first satellite. And later on the Bhaskara, which is a basically remote sensing satellite, there was a all-sky X-ray monitor. Professor Agrawal was developing that. I still remember I joined in 77, in 78 or 79. It was launched, it must be 78. Professor Agrawal is in Goddard Space Flight Center in US, and its propulsion counter is leaking. As a student, I had to carry this propulsion counter all the way to the airport, Centaur Hotel, where you are sitting, and hand over, he has to take to US, test for leak and bring it back. So such things were happening at that time. And of course, Professor Agrawal also was instrumental in making a rocket experiment for soft X-rays, which was one of the first all-sky very low energy map, which eventually formed the thesis of Professor K.P. With all this excitement, 1980, I call it era of struggling started. Why do I say that? Actually, this date could be 1985, because that far infrared telescope Spain Shamden built initially 30 centimeter, then 75 centimeter. Unfortunately, 1980, it went to the sea because we couldn't recover it. He rebuilt it, T100, 85, and beautiful results were coming by late 80s. And the Anuradha experiment they talked about, Kumar Biswas was responsible for Space Lab. The results launched in 85. Though these results will keep coming post 80, personally, I feel that 80 is the time is something changed. Basically speaking, space astronomy moved on to the era of satellite. Two reasons. Okay. One is that in balloons and rockets, observation time is very small. Now we can continuously observe many sources. And secondly, there were many new technical improvements which quickly came, which was imbibed in a satellite. We could not do it in the rockets and balloons. Like 77, first major X-ray satellite, UO1, and Einstein Observatory 1978, which using the X-ray focusing. So I'll briefly tell this focusing, non-focusing part in X-ray observations. So X-rays come, you put a detector, you detect that. Okay. Now, if you want to increase sensitivity, you need to focus X-ray single point. And reflecting X-rays extremely difficult. They are very short wavelength, they will scatter rather than reflect. You need a grazing incident. So the making a very highly polished grazing incident scope is a technical marvel, which has happened later on in Chandra Observatory. Okay. So that technique, this is years of development in the West, and we didn't have any headway in that. So I remember in the late 70s or 80s, we go to the library, suddenly there is a full volume of astrophysical journal letters telling the latest results about one satellite, like IRAS or HUO1. So there, the results were totally outstanding and nothing what we have observed and experimented. And I still remember in there is one huge NASA memorandum of X-ray astronomy it is. Me and KP in the night will after dinner will go and look chapter by chapter. So initially our heady days we have learned all about neutron stars, black holes, etc. But what the improvement sensitivity of the focusing detectors in satellite platform did was that detecting X-rays in all types of various sources unimaginable, starting from normal stars, supernova remnants, clusters of galaxies, active in galactic nuclei, and even ordinary galaxies. So looking at that, our own effort looked very trivial, and something hit me and KP. And KP much more later on confessed to me that at that moment he decided that in India somehow he will bring X-ray focus indeed, and he did indeed for AstroSat. So what were we doing? Okay. So there were many things. For example, Shyam Tandon moved on to fifth force experiment, later on moved on to Ayuka. But the IR telescope continued with the balloon observation by putting better focal plane instruments, and IR group moved on to a lot of ground-based optical observations and optical synthesis. And Professor Agarwal continued with the large X-ray proportional counter and making multiple X-ray data. Professor Manchanda went on doing different types of X-ray detectors, and he did the ground support for HLA satellite. And Professor Damle continued the Soviet collaboration. So the smart young man is, you may be recognizing there on the right top. And one more thing happened at that time is proposal-based archival data analysis. So generally doing science, you need to have the hands-on experience of using data. That's the era. Most of the data were public, and Professor KP Singh pioneered that effort in India. I remember we did a sort of thought experiment, me, Wahi, and KP. KP led this thing in a matter of, it's a project mode. We started a paper factory sort of. In a year and a half, we had a dozen publications. So when we wrote a proposal, data is to come in magnetic tapes by surface mail, and we used to drag it and do all this work. These are all important for later on. I'll come to that soon. Now, Professor Agarwal, the never say die spirit, in this spirit also, he was needling ISRO, saying that X-ray astronomy moved on. We can't survive in this area unless we have satellite platform. Of course, Indian rocket system was not matured. It is till 2000. Okay, so whenever this opportunity comes, he grabbed it. Okay, for example, there is Polar satellite launch vehicle. They were experimenting development flight 1, development flight 2, development flight 3. In development flight 3, there is some opportunity of putting a small proposal counter. Okay. So this was a quick effort saying that we are testing the rocket. If you want, you make this instrument. Of course, we are building proportional counters for balloons, etc. Balloons is little bit easy. When you send it up, it doesn't work, bring it back, repair it, and send it again. But we have to build something which will last for years together. There's a order of magnitude higher planning involved. I still remember the ISRO, some team came to inspect whether we'll quickly deliver, because they are testing the rocket within a time from 1 year. You have to do that. And evening we are testing the detector, we're leaking. I remember why we are going out and say that, come on, one last effort. Finally, we demonstrated, and this was sent in space. More than that, it was first experiment. So basically, it's a photometry. It detects how many X-rays we detect from the sky. But all that we learned from KP Singh came useful. So whatever data is available, there's a huge number of publications. You can notice many of them. Dr. Kasturangan was graceful to be a co-author to these papers, and it infused a large number of students, and large workshops and courses, and wider availability data was norm in X-ray astronomy. So time was ripe to move on to next phase, to have our own full-fledged international observatory. That is the Reliance AstroSat. Now, AstroSat, now we have to pause, and I have to explain a bit. As I explained, rocket technology goes zooming up in the West. Not only these satellites, which I explained, NASA had the 4 great observatories. Each of the wavelengths, there is the best possible satellite like gamma rays, Compton gamma ray observatory, Hubble Space Telescope, Chandra X-ray Observatory, and space. So all wavelengths are fully covered. So right now we are beginning. Do we go back to the 1970s and 80s, have the same small X-ray instruments, or do we think of something there? The philosophy is simple. There are certain things which you are expert in, build on it. Certain things, but don't forget the science. And what new science we can bring into that. So generally, when the space era comes, now every object emits almost in all wavelengths. So if you want to apply your physics, it's very good to have multi-wavelength observation. These days, this has become a trend or a fashion. So maybe, okay, our individual instrument may not be comparable to the great observatory of each wavelength, but they're sensitive enough for the bright sources to make measurement all the way to infrared to gamma rays. So with this concept, it is a doable and also it is competitive and scientifically rewarding. So it is the first multi-wavelength astronomy satellite launched at here on the 20th September 2015, and large number of institute, university, everybody worked together. Now here, again, I will explain each of the instrument here itself to get the legacy of what formed during the early days and the struggle years so that we can move forward. Let's start with ultraviolet imaging telescope. So there are 5 major instruments. 3 of them were led by TIFR. Other 2, though there is no direct connection, there is indirect connection. So UV telescope is led by TIFR alumni, Shamtandar. And of course, some critical elements by the leadership of Swarna Ghosh, it was tested and qualified here. And the whole approach of doing the quality instrumentation of Shamtandar, which is started with the balloon experiment, moved on later on for the 5th, 4th experiment, and later on in Ayuka, that all came into force. So he single-handedly, single-mindedly moved various organisms of ISRO to make one of the most beautiful infrared telescopes. Why is it competitive? Because it's wide field and very good seeing. So the things, suppose like for recently, a couple of nature papers came on that looking at the deeply wide field areas of near the galaxies. Okay, so the complete quality concentration of building good telescope came into picture in the ultraviolet imaging telescopes. Then you have the large area proportional counter, PC Agarwal, proportional counter Agarwal. I mean, so he had the experience of almost a lifetime to building that. And this large area proportional counter in high energy X-rays is one of the largest area ever flown. So we had the legacy for that, but building 3 of them and such a large thing in a quick time was extremely difficult. Many people contributed. Professor Yadav, of course, Professor Ante also became part of this team. So Ashwat attracted not only all of us, including theoreticians like Ante. So then soft X-ray telescope is the dream of KP Singh. I mean, during the 80s itself, he has said that he will somehow bring the technique or the method of X-ray focusing in India. That is a complete effort from him. And this all-sky monitor was completely built from the ISRO team. But TIFR connection is that identical unit in the collaboration TIFR in 1995, we had flown in Indian X-ray astronomy experiment as X-ray sky monitor. So the legacy or the know-how, there is a hand in TIFR even building this instrument. And cadmium zinc telluride experiment, I think in the days when we are struggling, for example, we are in TIFR and Upendra Desai from NASA came. He said that, what are you doing? He said, we are building proportional. Come on, there is a new generation cadmium zinc telluride detector. So he'll, from his pocket, will say this small detector. So me and Vaya will go and fiddle around this one. That experience helped to build this CZT detector. Not only that, I think the renaissance is slightly different. We are better off monetary wise. I remember in 80s and Professor Agarwal got optical CCD. It was not working and it was lying in the lab for 5 to 10 years. Similarly, X-ray, the CZT detector we bought from Israel. And of course, the first time when we bought in the laboratory, it was not working. So, but Agarwal had this thing, he pushed and this thing and got enough money for me and Vahia went to Israel and find out how to make it work and brought it back. So this is some sort of piggyback experiment in the sense that bringing the new generation X-ray detectors for the Indian platform. So this is the details of the telescope, this one, okay, and this is the largest area detector, and this is the each of the conical foils, 40 cells, 130 of them. So this one, each one of them KP painstakingly built. Of course, we were doing there is extreme space crunch in our laboratory when 3 major instruments are being built, and here to snatch space from the basement and get people to work on it, and foil by foil we had assembled this one. Of course, X-ray CCDs were collaboration with the University of Leicester. And even now in the CCD, this one of the finest energy resolution 145 EV for 6 kV X-rays. And CZT data, which I talked about, based on the CZT detector bought from Orbitic Solution, assembled to, let's say, a large area, and scanning sky monitor, which developed from ISRO based on the legacy of collaboration between TIFR and ISRO. Of course, ultraviolet imaging telescope, 2 of them, and Shampton is the major responsible for developing that one. So, as I mentioned, this astrostudy wouldn't have possible without the active collaboration of the vast number of institutes all across India. And making them working together was a tough job, but eventually, I think there are 2 major components. That instrument building capacity started in the early 70s and even 80s. Some of us took the kept on the flag flying. That helped us, and of course, I should emphasize the complete technical know-how and professionalism and quality consciousness of ISRO played an extremely major part. So this is one of happy union of care for technical competence and professional ISRO and everything coming together and building something very nice and beautiful. So there are certain good things about AstroSat which actually can make it extremely competitive. It is making it extremely competitive. It's in the low inclination for X-ray astronomy. It's fantastic for reducing the background. And we have continuous time tag data. So like, for example, we can, timing is so good, we can connect the timing from launch till today. So even the faintest millisecond pulsar, we can co-add and measure. So with the time base of 7 years, you can go down to extremely faint millisecond pulsar. So this extremely good timing measurement is one of the very good features of this one. And soft X-ray telescope is not that sharp. That actually is a blessing in disguise, because many of the very good focusing telescopes focus the X-rays to a single point. If you look at the bright sources, they burn the CCD or burn the X-ray detector. So since the focal length constraint frequently lower, the seeing is wider. So even the bright sources without piling up. So this is fantastic for the making X-ray spectrum of very bright black hole sources or transient sources. And we have above hard X-ray polarization capability of CZT imager, which was serendipitously much later after design of the detector, which was realized and proven. And now we started working for the last 7 years. And 7 years, we had a feel-good meeting at ISRO. And I'm now just flashing few of the slides made by Girish during that meeting. So there are extremely good results, I think, so from each of the instruments, and large number of publications. And there's a peak in the publication because we had a 5th year celebration in our own journal, some large number of papers. And AstroSat users all spread all through India, because the spreading the community was important for to even to get the proposal like AstroSat to be approved. So here in the 80s and 90s, the large number of workshops and schools which Professor Agarwal was instrumental, that proved very useful. So right now we have AstroSat users from universities all across India. And it's a proposed, mainly I think Bombay, Bangalore connection is stronger. I think. So of course, it's open for international collaboration. So right now, AstroSat users are in many international countries. And as I said, publications are decent, around 20-30 every year. So I will conclude here to honor the 115 lunchtime of Vaya. So AstroSat, we took a extremely innovative approach. And based on AstroSat, now there is many offshoot experiments being thought about in various stages of approval. The cadmium zinc telluride instrument which has been used, similar detectors are proposed for a thing which is jointly with TIFR called Daksha. And infrared instrument exists is in the proposal stage from TIFR. And based on UVIT, the infrared spectral and imaging are proposed from IAA. And actually, AstroSat helped to understand the technology gap. So technology gap is no longer a constraint in space astronomy. Why? See, previously, for example, most of the technology used are device-based. Okay, many of the devices are denied to us for technology transfer way. But today, most of the technology is software driven. So, like for example, you may not get the highest end FPGA possible. Okay, but even the few 5-year-old FPGA with the experienced person sitting in this row who has experience programming FPGA for various satellites, if you use his expertise, the final product is as competitive and as good as elsewhere. So now technology is mostly software driven and not the device driven, except of course some few detectors, some extremely sensitive infrared detector may be still too difficult to get. And for example, suppose you want to build another AstroSat, etc. I personally feel money, etc. is not a constraint. In the sense, suppose you said you want to, there is no technology gap, you want to build something $1 billion satellite for something niche area. So in India, getting $1 billion is less difficult compared to get 100 people who are qualified and willing to work together for 10 years together. Now, if you want a $100 million equivalent thing, you have to make 10 people work together. So having a large number of people, interested people, devoted working together, that culture we are yet to do, I think is in the line. Okay. So with this, I'll conclude and give me enough time for that. Thank you very much.
Thank you.
Yeah, thank you so much.
Yeah. So thank you so much, Professor Rao, for giving us this big ride to the space and everything. So I wish to thank all the speakers of this session and also the chairman, Professor Acharya, for conducting this session. Thank you very much. And now we will break for lunch for 45 minutes. And one more thing is announcement is that today's tea, because it was a high tea, it was served in the West Canteen. Today, later on, tea coffee session and tomorrow's tea coffee sessions will be served in the auditorium cafeteria, where you just, as soon as you go out, turn to the right, and you will see the exhibition by ADAPT organization. So you can also have a look at it, and the tea and coffee will be served to the left of that side. So please do visit this ADAPT exhibition and do help this organization. They are doing wonderful things. And with this, I thank once again all the speakers of today's pre-lunch session, and all of you please have a nice lunch in the West Canteen. You'll all have your old memories of West Canteen coming through. So we'll meet here at 2 o'clock for the next session. Thank you very much. Yeah, it's called Grove Pavilion. Grove Pandal. Okay, thank you. Thank you all. Maybe we can load it, sir. Sir, I load. This is the file. Oh, pen drive? Oh, okay. Okay, just 1 minute. Yeah. Okay, so now I'll just close this. Yeah. I will just exit this. Yeah.
Thank you.
Just we will check it here.
Yeah.
नहीं आप ये ऐसा मत ये व्यू में जाइए व्यू गो टू व्यू लिस्ट ये डिटेल्स और उसमें इस पर क्लिक करना डेट मॉडिफाइड कॉपी कंट्रोल सी
सेशन के पहले इसमें
हाँ इसी में कर लीजिए फुल स्क्रीन Yeah, change it quickly. So. उस पेंटर सबका पूछना पड़ेगा क्योंकि वो आगे फिर वो सुविधा हाँ
ये भी है हाँ ठीक हाँ बोलो हाँ बोलो हाँ ठीक है अभी ये और एक टॉक चेक करना है उसके बाद कीजिए हाँ अभी ये लंच का बाद वाला है हाँ
ओके थैंक यू सर ये निकाल लिए
Hello, check.
So these people seem to have some sort of a power glitch there.
Yeah. That's why that whole thing is.
What happened actually?
I don't know. That switch got.
So you calling somebody?
No, they are already repairing. The
But
whole work is going
I know,
on.
but why today?
I don't know. Suddenly. कोई पनौती
Why today? Huh?
मैं मालूम नहीं क्या है कुछ तो हुआ होगा. Okay, I will just call the security head.
Hmm.
For what? Because I want all of them to eat at the canteen because the food will go waste. You should not waste it.
I know.
All of them should eat. Just take all of them.
So we can't start it. Can somebody get people in back in here? ठीक हो गया?
वो ऑनलाइन ले लेते हैं इसलिए।
वहाँ भाग ठीक हो गया?
हाँ सर, ओके।
अभी दो देर वेट करना पड़ेगा।
नो नो, जस्ट 1 मिनट, आप बात भी कर सकते हैं।
Ready?
Yes, sir. Like this guy, वो कौन देखेगा? Sir, sir,
Light in the screen.
light on the screen.
नहीं, brightness बढ़ाना है।
Sure, sir.
बढ़ाइए। Yeah. I think he'll go and do it from there. And maybe we turn off this lights just in case. Okay, let's see. Can you increase the brightness? Actually, it was he knows the value. $73.
73,
75.
78, 80, 82, 82. Phone ಇಲ್ಲ phone. Hello. Hello.
Hello, somebody at the back, when you say the brightness is okay? It can be better, okay? Good. Try the contrast. Is it okay? Is it better? Look at the contrast. Is it better?
Your first slide. Hey, sir का first slide डालना है. Where is sir's presentation?
Okay, how does it look from the back?
How does this look in the back? Is that one dash okay? Perfect. Yeah, the last row. Okay. Okay, save it.
Yeah, that is what I'm trying to get rid of it.
No, this is because of the Zoom projection also security. If somebody bomb, no Zoom bomb. So they put layer
This is enough? No, it can't go down. It is just getting stuck at the edge. I tried that. Yeah, yeah. I try. See, it is not going beyond that.
So you just push it. Yeah, that's it. Leave it there.
Okay. So shall I start? Okay, welcome everyone. We will begin the post-lunch session. And I am requesting Mr. G. Ramankumar to chair this, and he will be chairing this session. And yeah, please, all yours.
So thanks, Prabhu, and welcome back after that sumptuous lunch. Again, well, no speaker in this meeting needs introduction, but just for the sake of those who came in late and also people who are on the internet, Professor Pentavadia, who is the first speaker, he is the Infosys Homi Bhava Chair Professor at the TIFR International Center for Theoretical Sciences in Bangalore. He is also a distinguished emeritus professor of the institute. He has done many things, which all of us know, but the most important one is in setting up the International Center for Theoretical Sciences, for which he was the founding director. Not to talk of, not to again forget that he was the major architect of the string theory program at TIFR. So we look forward to his latest thoughts on how we have progressed over the last 75 years. Spenta.
Thank you, Ravi, for the kind introduction, and wonderful to see everybody after such a long time. I will I'll start with a small apology in the sense that initially I was asked to talk about string theory and how it becomes, strings become particles and stuff like that. But then I thought it would not be correct if the rest of theoretical physics of Tata Institute is not represented in this meeting. So I undertook to do this sort of ominous job, and I hope I have succeeded to some extent. Okay, so there is some problem with the mic. Can you hear me? Okay, good. All right, so this is the sort of brief plan at the top. So begin with Bhava and then the early leadership, the main areas, and the organization of summer and winter schools and major conferences. I speak a bit about the ICTS because ICTS is 15 years old this year, and that's some part of 40 years, and about the future. Okay, good. So in the beginning, the theoretical physics group or department or whatever was set up by Homi Bhava. The subject on which research and advanced teaching would be done would be theoretical physics, especially on fundamental problems and with special reference to cosmic rays and nuclear physics. I have detailed many things in my slides, which can be available later on for you to read, but I will not go through the details because I have 65 slides. Okay. You'll be here till all evening. All right. So early work, research activity during the first period was almost entirely dominated by the personal work of Dr. Bhava and was principally in the field of elementary particles. So theoretical physics at Tata Institute starts with elementary particle physics. And this is some brief description of his work on relativistic quantum mechanical description of mesons and nucleons, the Bhava equations for higher spin particles, which of course are very, very contemporary even today, in another avatar, which is called string theory. And I'll talk about string theory a bit later on. So I wanted to emphasize that there is from the very beginning an emphasis on education at the Tata Institute. And when it began, people, very eminent people, actually like Alfred Dirac, Pauli, Rosenfeld, Serber, Wenzel, came and gave graduate courses. And in 1964, a regular graduate course program was evolved at the Institute aimed at making PhD training more and more systematic and broad-based. And the theoretical physics group has taken a leading part in developing this program. All this is a quote from this very beautiful volume of the Tata Institute of Fundamental Research from 1945 to 1970, which was brought out by the Institute during the directorship of Professor Srikantan. Okay, so this is a very brief early history, and Baba's students, mentees like Professor B.M. Udghankar and K.S. Singhvi set up the theoretical physics group. That's my information from reading things from the archives also. And Professor Udghankar, very well known to all of us, was a polymath. He was an amazing person with important contributions to particle physics, Regé-Pol theory, and in later years to physics education, actually. And sort of quite instrumental in setting up the Homi Bhabha Center. And the condensed matter person was Professor Singhvi. And these two photographs in black and white are from that volume. Now, around the time I joined, that's in 82, around that, a bit earlier, Deepak Dhar and Mustansir Burma had also joined. So when we joined, the leadership of theoretical physics was basically with Professor Virendra Singh and Professor S.S. Jha. Both of them were chairs of DTP and then became the directors of the institute. So Professor Singh was a very distinguished high energy physicist with work in S-matrix theory, high energy theorems, foundations of quantum mechanics, especially work with Professor S.M. Roy. And Professor Jha was a condensed matter physicist, very well known for his important work on nonlinear optics, surface enhanced Raman scattering, superconductivity, which I will mention a bit later also, and semiconductors. And since I had to prepare this talk, I sought the help of all my friends and colleagues. So I just asked Mustansir, Burma, Moldike, Sri Rup Rai Chaudhary, Nilmani Mathur, Shubhabrata Majumdar, Abhishek Dar, Rama Govindrajan, P. Ajit, all of them to contribute to me some material actually, which I can use for this talk. And the string theorists, I didn't ask one person, I asked all of them, because I didn't want any one of them to summarize what happened in string theory at TIFR. That privilege I kept for myself. Okay, so let's begin with the area of statistical and condensed matter physics in the Department of Theoretical Physics of TIFR Mumbai. Afterwards, I will talk of ICTS, in which I will also talk about the same subject, but a bit later. Okay. All right, so let's talk about self-organized criticality and the sand pile model. So as you know that phase transitions occur when you tune parameters in a laboratory like temperature, pressure, volume, etc. That's but how do they happen in natural processes, big natural processes like earthquakes, etc. And there is no tuning. The tuning comes from the nonlinearities and the complexities of the system. And so self-organized criticality is a property of dynamical systems that have an attractor, which is a critical point. Dynamical systems have attractors, and so it's a critical point that arises without tuning of any parameters. So it's a paradigm for the explanation of many natural phenomena like magnitudes of earthquakes, the frequency of aftershocks, fluctuations in the financial market, forest fires, etc. And this is a very important subject to which Deepak Dhar made a very fundamental contribution by finding a soluble model, which is called a sand pile model, and solve exact solution, which led to a very deep and a deeper understanding of the subject of self-organized criticality. And then there were, of course, many other works with Satya and Tribit Sadhu, etc., in this area. So next, there's a lot of work by Mustansir Burma and collaborators
about disordered driven systems, and especially this very important work on fluctuation dominated phase ordering, in which long range order coexists with macroscopically large fluctuations, and it replaces the normal critical state as a separatrix of ordered and disordered states in several equilibrium and non-equilibrium systems. So this is a big body of work which is very, very interesting. And then of course there's an exact solution. Deepak is very proud of this because the exact solution of a model in higher dimensions actually. It's about enumeration of directed branched polymers in general dimensions. And then I forgot to mention perhaps earlier that Sriram Shastri. Yeah, Sriram Shastri joined the group at the same time as myself. And here, I think he did a very, very beautiful piece of work in showing that the 1D Hubbard model, which is the Hubbard model is a paradigm condensed matter, strongly coupled systems, can be exactly solved. And, he found all the conservation laws and also the Yang-Baxter equations, which underlie the integrability of this problem. Okay. Then there's work in superconductivity, which Professor Jha had for many years. I remember talking to him about it also, in layered materials. Then there's this work of Mohit Randeria and collaborators. Mohit Randeria was a faculty member at the Tata Institute before he went to Ohio State University. And it was on the variational wave function study of high temperature superconductors. Then Nandini Trivedi, who was also a faculty before she went to Ohio State University, did very nice work on gaps across disorder-induced superconductor initial transitions. I know the details of only some of these works, so I cannot describe in detail all of them. And then there is, of course, this interesting work by Nandini and her student Rajdeep on low energy Higgs model. I would have thought that Mustansir would have written Higgs-Anderson model, but he didn't do that. Interesting. Low energy Higgs mode in disordered superconductors. Okay. Then there is work by the younger people of the group, also Rajdeep Sen Sarma and Satya Majumdar when he was young at that time, 1998, on many aspects of non-equilibrium processes, similar to Bose-Einstein condensation, but in real space, not in momentum space. Usually we discuss condensation in momentum space, but it's in real space. Very interesting description of that way of describing condensation. Then there is a Schwinger-Keldysh field theory for entanglement entropy and dynamics of correlated systems, which was done by Rajdeep and collaborators. This Keldysh-Schwinger theory is very important to understand the quantum field theory of open systems. So it's a nice piece of work. And then large deviations in non-equilibrium dynamics is a very important subject, and Tribid and collaborators have done some very interesting work. Conditional large deviation of local density were found exactly in an interacting stochastic system. Okay. Then there is work in statistical mechanics from people doing string theory. Now, I'm going to mix up everything because you see, you think string theorists only do string theory. No, they do many aspects of theoretical physics actually, which impact on their sort of, what shall I say, dreamt goal of finding out the laws of the universe. But on the way, you pick up very beautiful things, and there is a very nice piece of work here of how systems, integrable field theories thermalize, and its connection to generalized Gibbs ensemble by Gautam Mandal and his students. All right, so now let's move to high energy physics at DTP. There's a lot of, my friends provided me with 7 slides for all the work that was done. Now that then I asked them to reduce it. So Amol sent me 4 slides. But even 4 slides is a lot for me to get to. So I'll go a little bit rapidly over here. And I would say that these search strategies for top quark, which were initiated by D.P. Roy and then by Godbole and Pakwasa, is a very important piece of work. And also search methods for charged Higgs bosons were pioneered by D.P. Roy and Devashish Chowdhury, Srirup Rai Chowdhury, and Gushayat. So there are many, many very interesting, important developments here, but this strategies for the discovery of the top quark, I would like to especially mention. Then there is beyond standard model flavor physics, and then there is this very important development. So in theoretical physics, many new subjects, moment cutting edge areas begin, people sort of start subgroups, and this is in neutrino physics and astrophysics. It's a very important development. And here the very important works by Amol Dige and Vasudev Dasgupta and their collaborators, who are really who have a piece of that plot actually internationally. Now let me mention something which I did. I mean, I was a bit very hesitant to put in my work here, but you have to be correct to yourself also. So so here are two works in quantum chromodynamics. There's a lot of quantum chromodynamics in all the slides I showed you, collider physics, for example. But here is a very important thesis by Avinash Dar in 1983. It was his PhD thesis from here. So he provided a complete solution to the problem of the renormalization scheme dependence of perturbative approximants to physical quantities. Now, the point is the following, that whenever you do quantum field theory, you evaluate coupling constants, etc. It's a scale. But in an experiment, how do you make a connection to an experimental result, which is scheme independent? And that problem was solved by Avinash. And I have read very nice things written by, many experts, especially Stan Brodsky, about this work. And then here's something else actually. So in the early 80s and 70s, what was the biggest problem high energy theory people were wanting to solve? They wanted to solve the problem of quark confinement. Why are quarks confined in this world? Okay. So that is what led to lattice gauge theories, which I will talk about briefly. And but suppose you're not working with big machines. Suppose you're not a Wilsonian actually, then what would you do? Then you would try to develop an effective Lagrangian method actually. So one fact about quantum chromodynamics we know very well is that the spectrum of the theory, of this very complicated theory, has a mass cap. There's a massive particle which is of lowest mass. That's the blue ball. And given that fact, what type of effective Lagrangian you can sort of write down? So we explored this, and so we proposed the old Nambu-Jonal-Asenio type model as a low energy model for quantum chromodynamics actually. And this work has been quite useful on many levels, especially to people in nuclear physics also. And the derivations given in this paper are about anomalous terms in the effective action, which we derived as if they are a Berry phase. And of course, if you see the year of our paper, we didn't know about Berry's work, of course. I mean, it's his contemporary. The Berry did much more general for any Hamiltonian system, slowly meeting parameters, what phases you get. But this had to do with this very specific problem of QCD, where we found the Berry phase of low energy pion physics. Okay, so lattice gauge theory. So in a nutshell, for all of you who perhaps work in other areas. Lattice gauge theory is a non-perturbative formulation of a gauge theory, in which gauge invariance is exact, but there is no Lorentz invariance because you're putting it on a lattice, a cubical lattice or whatever. And so Lorentz invariance is broken. Yeah, I cannot resist telling you this, that I was at the meeting when Ken Wilson announced it when I was a student, and that gauge invariance is exact, not Lorentz invariance. And the whole audience and very eminent people were sitting there, just stood up and said, oh my God, what is he saying? Okay, but this is an old subject. I'm talking of the early 80s. And there's a lot of work at the Tata Institute in this area. It's non-perturbative investigation of energy spectra and structures of subatomic particles. This is all at zero temperature physics. There are lots of such investigations about ultra-relativistic heavy ion collisions, quark-gluon plasma, etc., etc. So I can't detail all of it, but it's on the slide. You can see it afterwards. All right. Then there is a niche area of finite temperature lattice gauge theories, where you explore what happens when you heat up the lattice, what happens when you turn on a chemical potential, etc. So here there is very important work by Rajiv Gavai and Surendra Gupta about the nature of the phase diagram. Just put this phase diagram here as a function of temperature on the y-axis and the chemical potential baryon number or quark number on the x-axis. And their lattice calculations did see the critical point approximately for the first time. And I think it had an impact on the RIC is the facility at Brookhaven Collider program to verify their prediction, which is very impressive, I think. And then there is this very important work from India by Sorendu and Vedangadas Mohanty from NICER on further understanding of the phase diagram, and their calculation of the critical temperature is something like 175 MeV, which in more common parlance is something like 2 trillion degrees centigrade. Okay, so this is important work in lattice gauge theory at the department here. Very computationally heavy. Yeah, most of important science is computation. All right, there's one more thing I like to mention here is the work by Sandeep Trivedi and his students on the definition of entanglement entropy in a lattice regulated gauge theory. This is not trivial problem. It's a very beautiful, important problem. Now they have provided one solution for a definition of the von Neumann entropy of in a lattice gauge theory. Von Neumann entropy, I don't want to go into details, is a measure of entanglement between various parts of a quantum system. So usually it is not very difficult to define it. You just take a spin system, make a small sort of area in a two-dimensional spin system, and you ask what is the entanglement of those many spins with the rest of them, and it's not very difficult to define. In the gauge theory, you can't do that because you have to respect Gauss's law, and they found the definition for the von Neumann entropy, which I think is important. Okay, now let me come to string theory. All right. So when we began working in the newly ushered area of string theory in 1984, we worked within the umbrella of the high energy physics unit in the theory group, which was the biggest unit. And the number of string theorists in DTP grew mainly due to the support and encouragement of Professor Viren Singh, who recognized the importance of the questions string theory attempts to answer, which I will mention in the next slide. Hence, in the early 1990s, before Professor Jha stepped down as chair of the department, he called some of us, I don't remember who else it was, to his office and said that we are planning to have a new unit in the Department of Theoretical Physics. So we gave it a broad name, not only string theory, but also mathematical physics, because there were other people like Ashok Raina who were working on, and Divakaran working on mathematical physics. Okay, fine. String theory, mathematical physics. That was a liberation. It's amazing. Because there was all this talk all around us that string theory is not science. And I think these leaders really were very helpful and instrumental in making space for us, because they appreciated the type of questions these people were trying to address and answer. And the quality of the people who were involved in doing this also plays a very important role. So this enabled the group to grow and invite some of the best people in the subject worldwide. Went and got all of these guys to become. So it became one of the top string theory groups in the world. And I checked it with a few people actually, so it's not a totally personal opinion, but I think if you take all the areas of curiosity-driven research in this country, I think any of them, physics, mathematics, biology, there was this time when this string theory group, and I think it's true now also, it's perhaps in the first 5 in the world actually, and it'll be difficult to find other groups actually, and we should strive for that, to be in the first 5 in the world in all the areas in which we work at the Tata Institute. I think this ambition is very important, and this was a driver in the way we do string theory, way we did the string theory group in Tata Institute. We wanted to beat the Americans. That was our main point. And I think to some extent we succeeded, I mean, in doing that. I have lots of American friends. I shouldn't be talking this way, but that's a good competitor. Okay. So here is a slide on why string theory. You must all be wondering, what is it all about? So it's a theory in the making. Firstly, there is no theory as yet. And it has its origins in high energy physics of strongly interacting particles. It's a new paradigm of physics in which the laws of physics are formulated in terms of extended objects rather than point particles. This is a one-line summary of what it is. But historically, the extended object that led to all this was a string. That's why it's called string theory. But it's not really a theory of strings. It's a theory of extended objects. And those extended objects can be one-dimensional up to 9-dimensional. They're called branes. The string is a one brain. Okay, so the work in TIFR, both in Mumbai and Bangalore, has explored and contributed to various important physics questions since 1984. First, what is string theory? What is it? I mean, can we discover a fundamental mathematical structure of it? Can string theory resolve the conundrums presented by the fact that black holes radiate? That's the Hawking problem, which I will come to. Can string theory provide a basis for the cosmology to an expanding universe? Can string theory provide a basis in a language to discuss questions like the origin of the universe or the multiverse? You will need a new language, just like quantum mechanics forced us into a new language. We may need a new language to understand the so-called origin or whatever of the universe. All right, so just describe a few of the early works. So our work on the Nambu-Jonas-Lasinia model in QCD immediately led us to working in string theory, independent of what happened in Aspen in 1984. That's nice. So we began working in string theory. We started with our students. So I knew one thing is that if you want to grow a subject, you have to grow your constituency. You need students, postdocs, and excellent faculty. So we started doing all that. And here are some of the early works, string propagation on group manifolds with Sanjay Jain and R. Shankar. These were my first 2 students. And then there is work on geometric background field method by Sunil Mukhi, and also this program of Mathur Mukhi and Sen on trying to understand rational conformal field theories in 2 dimensions. So all this work has to do with classical solutions of string theory. Classical solutions, because you're looking at conformal field theories. Don't ask me why, but classically. So you wonder about how to do string theory. I mean, how to discover that theory. So here Ashok Sen came up with a conjecture and a very literally outrageous idea. And the clue was basically, I mean, since you're mostly familiar with condensed matter, in the Ising model, you have a high-low temperature duality, right? High temperature phase can map into low temperature phase, and you will tweak the degrees of freedom slightly. Or if you admit magnetic monopoles, in electromagnetism, you have an electric magnetic duality. So strong coupling becomes weak coupling. Okay, so Ashok Sen thought about discussing S duality, this weak coupling, strong coupling duality. If you start a weakly coupled theory, is it possible to make a transformation to other degrees of freedom where the theory is strongly coupled? So in that way, a strongly coupled theory can be understood in terms of a weakly coupled degrees of freedom. And yeah, so for certain supersymmetric theories, a systematic procedure for testing such conjectures was developed by studying the spectrum of supersymmetric states. Supersymmetry is not found. Perhaps this is one of its most important applications, that you can do calculations without going to a computer. You can do analytic calculations. And this procedure was later used by others. Others means Ed Witten, for conjecturing new relations between theories and testing conjectures, and eventually led to the realization that apparently different string theories are all different descriptions of a single underlying theory. So there is this big theory we don't know anything about. We know a little bit of little corners, and we know how those corners map into each other. So at least you know that, you know, there is an enormously huge structure somewhere there. It's there, and this is some sort of an existence of that type of big structure. Okay, then there was work on matrix models, exploring, so it's all statistical mechanics basically. There's no string theory here, except that it somehow comes from trying to understand strings propagating in lower dimensions. So this is some work over here, and let me just move on because I have a long way to go, my God. So string theory is a theory of gravity, right? So it must describe black holes. I mean, there are lots of issues about black holes, which I will come to. So I think this is the first example of a black hole in two-dimensional string theory, which was found by us. Exact solution in just way back in 1991. And I think the 3 of us were all at the Institute for Advanced Studies in Princeton. And we were competing with somebody, competing with Ed Witten for this solution. The special significance of this was the fact that for the first time, this type of work raised the important question whether if you have a black hole or if you have any complex object, whether the degrees of freedom and the dynamics of this object can be encoded in an object in one lower dimension. And in this case, it was a matrix. Later on, that matrix was replaced by an entire quantum field theory, and that was the famous ADS-CFT conjecture by Juan Maldacena in 1996. So this was the first sort of glimpse at that. And then there's this very nice work by Ashok Sen on extremal black holes and elementary string states. He tried to understand the black hole entropy, Bekenstein-Hawking formula, as a statistical formula. I mean, he made an attempt to do that. And it's not exact because the black hole is too small to be understood classically, but at least this attempt is significant. Then if string theory is a complete theory of quantum gravity, it should account not only for the leading Bekenstein-Hawking formula, but also quantum corrections, and that was done by Atish Dabolka when he was here. And there's also the attractor mechanism for non-supersymmetric black holes. Means how do how do you trust strong coupling calculation when there is no supersymmetry? So these people found a nice mechanism for that. Okay. Now comes important part of the story, that the information paradox arose from the work of Stephen Hawking in 1974, as you know. He once lectured on this stage, if you remember, in 2001. In his treatment of quantized matter interacting with classical black holes, Hawking demonstrated that black holes radiate thermally. This is in conflict with unitary evolution in quantum mechanics. And in attempts to resolve this type of problem, physicists, beginning with Strominger and Waffa, discovered that a black hole is just like a ordinary dynamical system, like a piece of gold, which obeys the laws of quantum statistical mechanics. And in fact, this was made very precise by Maldacena in his great discovery, that if you take gravitational phenomena in anti-de Sitter spacetime, it's like a box basically, then the stuff, all the black holes and the dynamics black holes is all coded in the boundary. So this is the holographic description. And so we began trying to understand Hawking radiation in this model of Strominger and Waffa, and we succeeded in doing that, and that played a very important role in the Maldacena's work on the ADS-CFT correspondence. I'll go fast now. Black holes. Now, cosmology is an important question, but string theory has to somehow accommodate. Can string theory accommodate the experimental fact that there is a positive energy density, all pervasive in the universe, like 10 to the minus 8 ergs per cubic centimeter. So the cosmological constant, this is the equal to the cosmological constant divided by 8 pi g. That's why it's such a tiny number. So Kachru, Kalosh, Linde, and Trivedi, popularly called KKLT, proposed a scenario in string theory. A scenario that can realize the fact that the cosmological constant is positive. And their work has been very influential, and I think still there's a lot of interest in it, a lot of debate. Within effective field theory, they gave a model in which this is possible, and I think this is a very important contribution. Because, okay, so I have to say this actually, so sort of the ground state of string theory with so many vacua and saddle points is not very dissimilar from a spin glass actually, okay? I'll just make that provocative comment and leave you. So there's a landscape, and where in the landscape is our universe? Where are we? Are all very pressing, important, fascinating questions. Okay, let me move. So then there is more work on dualities, integrability in string theory, all contributes to our general understanding. And then we come to the, after Maldacena's famous discovery, the group over here, Shiraz Binwala and his students and collaborators made a surprising and precise connection between two of the best studies partial differential equations in theoretical physics, namely Einstein's equations and Navier-Stokes equation. In one line, the point is the following, that if you have a black hole, and the black hole has a horizon, right? The one-way gate, you fall in, you can't come out. If you throw something in, it jitters a little bit. So the jitters of the horizon of a black hole can be mapped into solutions of the Navier-Stokes equation in that gravitational box, which was given to us by Maldacena. That is this is a very important big discovery, this one. It's done here. Okay. Then there is a 10-year project on Chern-Simons theory. Shiraz, mainly Shiraz, and many of us have also contributed on the way. But I just don't have the time to detail this. You can read about it here. Then there's work on trying to understand how unique is the graviton. How unique is Einstein's theory of gravity? So Einstein's theory of gravity gives rise to calculational methods for scattering matrices. String theories also do. So from the S matrix actually, and the number of such S matrices possible, can we glean what is the underlying sort of, what is unique about string theory, Einstein's theory, etc. So I just don't want to detail this. I'm terribly running out of time. How many minutes? Oh, I started 10 minutes late, no? Given that. Okay, I'll take a little bit more time if you don't mind. I'm covering 40 years, so please. Sorry. All right, so there's in 2010, we invited Shubhabrata Majumdar from the. Sorry. Okay, thank you. I'll do that. Okay, so in 2010, we began doing cosmology as a subject, as a unit in the theory group over here. So there are lots of interesting things which people have been doing. Shubhabrata Majumdar and Rishi Khatri and Girish Kulkarni and other collaborators. I will so there's this work. Then the theory group has also brought out many monographs and organized many conferences, including Strings 2001 and Strings 2015, which are very big and successful conferences. Stephen Hawking was here for 2001. All right, so I thought it's important to also include the theory work done in Hyderabad. So here it is, and I think mostly it is in the area of soft condensed matter physics and fluid dynamics. So I thought I should mention the work of Perlikar and Amola Kabir, who was a student, and Samarjit Karmakar, who is a postdoc of Giorgio Parisi. So it's very interesting works. And Surajit Sengupta, and the late Surajit Sengupta was a good friend of mine also. Yeah. All right. So last 5 minutes or whatever I want to cover about ICTS. So ICTS is it is a baby of the theory group here. So in that sense, I have to talk about it. Okay, so yeah. So the idea to create a center such as the ICTS was born in 2001 after the success of Strings 2001, when we knew that we are somewhere in our subject, and a visit to the Infosys campus in Bangalore. I mean, that you can create such facilities in India. Baba created one here, but in the succeeding years, I didn't see anything. But Infosys campus was an eye-opener. And so all of you know about the ICTS. Many of you have been there. And so it's unique in India as an international science hub that could transform the ways of doing scientific research and science education. Established in August 2007. And I just wanted to say that the ICTS, creation of the ICTS was a very huge collective effort by people from TIFR, from the department here, from the DAE. I should especially mention Raj Pillai, who helped a lot, actually, during the difficult years of the ICTS. So I've just, Professor Rao and Dr. Kasturi Rangan, who were very supportive of this whole thing, of this whole initiative, and this is Professor David Gross, who guided me of how to go about doing it, actually. And this is Avinash Dar, whom you all know, and Mukesh Tudain, who was working with us as our assistant, and Uma Madhavan, special officer on special duty from DAE, and the TIFR, who was also very instrumental. So this is my team, the early team actually with which I worked, and without them, I think it's hard to imagine that the ICTS would have happened, really. It is not easy. They helped me a lot. All these 6 people were so instrumental, and many others, actually. If you had given me 2 hours to talk, I would have put many more photographs. Okay, so here are some achievements which I thought. So very important, it's not just an conference organizing center. You have to remove it from your head that ICTS is that. It is one of the best theory institutes in the world today in what it does. This you can check. it is also involved in organizing programs and conferences, colloquia, and has a very active science outreach and popularization program. So these are the three missions of the ICTS, and they all rest on the first one. The research faculty has been first rate and very strong. Okay, enough about the ICTS. I'm sorry, I have to say it. So I'm saying the truth. So. There are these areas of research now we are growing, quantum fields and strings and gravity, from which it all came, fluid dynamics, climate dynamics, computational and physical biology, statistical and condensed matter physics, mathematics and computer science, astrophysics and cosmology. And my assistant made this chart. Then I told her to put this ring. You see, they are all connected. At ICTS, science is one story, basically. In some deep sense, that's true. And yeah, so this is what we do. And maybe 10 years later, when some other person gives a talk on the ICTS, you'll have many more such things all connected. And for that, we need more land. Okay, so this is the faculty. And these are some pictures about the ICTS, which those who have not been may have a look, actually. So this is the red one is the library building. This is the inside of the library. It is designed like the Guggenheim Museum in New York. This is our computer center, and this is our auditorium, and these are the spaces outside the cafeteria. And I think there was a beautiful photograph of the ICTS as you walk in, shown by Jairam in his presentation. Okay, so this is in pictures. This is the work that people do. Statistical mechanics, condensed matter. I think it's the strongest statistical mechanics group in India. And maybe really world class. I'm not an insider, so I can't say first 5, first 10 or something, but really up there. Okay, so they do many interesting and important things. So I just don't want to detail. Then we also have biophysics, actually. Any theory institute, what its name, should study how biological systems work. And with some good advice in the beginning, when we started biophysics at ICTS, of the theorists working on biology in collaboration with experimentalists at NCBS or elsewhere. Okay, and so at ICTS we have this whole group of complex systems. One of them works on so it's a collection of people working in partial differential equations, uncertainty quantification, earth sciences, and fluid dynamics, turbulence, etc. All those words characterize something for you, but we have put them all together to address a very important question about the Indian monsoon, actually. So it's not exactly a climate thing, because climate is more, the scale is longer, but this is about weather. Understanding the monsoon is very important for India. So treating rainfall as a probabilistic manifestation of underlying dynamics, these people showed that most monsoon days of the past 110 years can be described by 1 out of 10 patterns, such as the one that I have actually shown you on top over here. Then there is a lot of work in trying to understand clouds, enigmatic stuff, right? Because they are upheld there by turbulence, and also other studies in turbulence, which I mentioned here, but I cannot go into it. Then there is data assimilation, nonlinear dynamics, fluids, turbulence. I always believe that it's very important for physicists to work in all these areas and collaborate with mathematicians to find out about fundamental problems of turbulence, etc., etc. Okay, then we have a very strong group on gravitational wave physics and astronomy, and now we call it astrophysics and cosmology. So the very important work has been done already in this area at ICTS, especially, for example, when the discovery of the gravitational wave signals in 2015, from the binary coalescing, for example, the mass and spin, the final parameters of the final state black hole were calculated at ICTS in that computer center I showed you. That's amazing, right? It's very encouraging. So a lot of work in gravitational lensing of gravitational waves, and gravitational waves as a probe into the early universe is also a very important question, because ultimately we'll find out about how the universe began only from signatures of gravitational waves, which are not screened by anything, right? Then there is a very important work on resolution of the so-called information puzzle by Surat Raju and collaborators, which brought out the important fact that in gravity, you lose locality, which you are very much used to in usual quantum field theory. And Surat Raju has made very seminal contributions in this whole area. I just don't have the time to detail it, but information in gravity is localized in very unusual ways. Okay. Fine. Then there is this whole program of Rajesh Gopakumar for many years now to derive the so-called ADS-CFT correspondence. Okay. And explicitly working out soluble models in which this is possible, this so-called tensionless limit of string theory, when the string tension goes to zero, that is the mass, the energy per unit length goes to zero. And I think this is important, slowly progressing, slowly. It's a very hard problem, very old problem, but there is good work. And with Anindya Sinha, Apritim Kaviraj, and Kalwal Sen, Rajesh ICTS is also doing some work on conformal bootstrap. A way in which you can, for example, the practical application of this is that epsilon expansions in critical phenomena can be done in a much more powerful and fast way. So it's interesting offshoot. These are all offshoots of string theory. And then, of course, here is the work of Loganayagam, who has worked on the Keldysh-Schwinger method. And so effective action for fluid Diracs and Schwinger-Keldysh formulation. And the first derivation of a nonlinear Langevin equation using the Keldysh formalism. Usually noise in statistical physics is Gaussian, right? But noise is not always Gaussian. There are corrections. There are non-Gaussian corrections, and how to handle them in a systematic way, I think, was first done by Loganayagam and his collaborators. Okay, and this is something I had to put in because I've also been working at the ICTS, so in physics, but collaborating mainly with Gautam and students and with Avinash when he was there. And we have been trying to understand in the SYK model, it's a very soluble model, how a black hole forms and how it evaporates. And there's a surprising results over here that for the evaporation process, which we didn't know anything about, the fully evaporated black hole exhibits very large fluctuations of the metric. I can't explain all this very easily, but this is an important result, I believe, actually. Okay, and now the future, just 2 slides. This has to be said. So I have picked up the courage because of my age, as Pillai said, to say a few things. So first we started with high energy physics in theory group, right? Then condensed matter physics was added. Then statistical physics was added with the induction of Deepak and Mustansir. And after that, string theory was added. So there were high energy physics, condensed matter, statistical physics, string theory. Then we added in 2010 cosmology, because we felt it's important to incorporate all these subjects in our department. And then at ICTS, I consider it as part of TIFR. Okay, no difference in my mind. High energy physics, condensed matter, statistical physics, string theory, cosmology, gravitational waves, climate dynamics, biological physics. I think you should think about perhaps here also or in Hyderabad doing all these things. And my feeling is that it would be important to grow in the areas of quantum information and quantum science. Quantum in the sense of what entanglement implies for physics and for other things. And here it's an extremely rich area where you can have a enormous interaction with experimentalists, and there are outstanding experimentalists in this place working on areas which are very close to this type of quantum technologies and quantum science. So that's one thing about the areas. The second is about administration infrastructure. Please never underestimate this point. And this Homi Bhabha has said it many, many times, and I think we all need to learn from his early writings how important he thought administration infrastructure was. So the Department of Theoretical Physics and other departments too, it's not only for, the chair of the department is sitting right here, I can see him there, could try to achieve greater administrative and financial autonomy in our institute to decentralize actually. Our departments are as big as centers, so they should be given more responsibilities and then they should be made accountable. So that's important. So it could also do better with an advisory board, especially if it would like to explore new areas of research. This is very useful to take advice. I think I felt key in Tata Institute, people don't like to take advice. This was explicitly told to me when I found my international advisory board for the ICTS. But it's important to take advice. You should be humble. And you could try to improve the infrastructure, and this will surely enhance the academic environment. Restructure things. In my time, we put some sofas near the elevator so that all the people can start discussing, and there were blackboards and all that. And then I was so delighted to see that there is a blackboard on the 4th floor and the students are working there. This was not allowed by one director, saying that, oh, the council meets here. So, but it has happened. I'm very happy. And the last thing I want to say is that I think there is this whole issue of ease of doing science in India. It is very hard to do science in India today. Visitors cannot visit us very easily. Experimentalists have enormous difficulty in getting materials, equipment, chemicals. I mean, since I was involved in writing the DPR of the National Research Foundation, so many people had mentioned about the ease of doing science as a fundamental plank there. I think we need a movement of scientists, and I would urge every one of you, including people in the Department of Theoretical Physics, to come out and join this movement and convince the government that you cannot do science in the way they are, with all the filters and difficulties that are put in our way. So with these few words, I'm very sorry for going over time. I thank you very much for your. Thank you very much. So thank God there are no questions.
Yeah. Thank you.
Yeah.
So that was comprehensive and sufficiently provocative. I would like to say that, well, before I invite Professor Antia, that we need autonomy on a larger scale, which seems to be going away as time progresses. And we do indeed want to assure you that ICTS is a part of TIFR. So with that, let me invite Professor Antia, the next speaker. And Antia is again very well known, helioseismologist of a great standing. And he will say what has happened in this area over the last few decades.
Okay, good afternoon. So we have had a little long lecture, so I will try to make up part of the time. So I am supposed to talk about the work done in theoretical astrophysics from cosmology to stars. So let us start. So the first thing is, when I was asked to talk about this, I was wondering what is the definition of landmark, which of course the organizers have not defined, and I have not seen anybody defining it. So I will also not try to define that. But so it is obviously a subjective thing. The main thing is where do you define the threshold? Because you have to define some threshold above which it will be landmark. So I thought about that, and I thought that the organizers have given me 40 minutes, so I should have something to talk about for 30 minutes at least. So that is what was the choice of the landmark. Then, of course, another problem was the theoretical astrophysics. Now, when we joined the institute, that time, of course, the theoretical astrophysics and things were well defined, because the other people had to build instrument and get data and so on. But now, after 90s, things have changed. Once the internet came, almost all data of astronomy is available, and anybody can use that. So there is no real difference between now theoretical astrophysics and the other things. So, of course, in consultation with the organizers, I decided that the definition of theoretical astrophysics is whatever is done by the members of theoretical astrophysics group. Now that itself is not well defined, so I have some loose definition of that, and hopefully we'll stick to it. And I am hoping that the work done, of course, there are other theoretical works done outside the theoretical astrophysics group, because some of it was already covered in the previous talk, and I think I will leave the rest. So now, of course, the choice of the landmarks is obviously biased, and I apologize in advance to my colleagues in case I miss something. So that is there, and I have selected about, my predecessor had a long list, so I have only about 20. So hopefully I will be able to finish faster. So we will start, of course, as usual, start with the history. So the research in theoretical astrophysics at TIFR was initiated in 1967 to complement the observational work in radio and X-ray astronomy, about which I already heard before lunch. Now the group formally, in some sense, began when MS Vardhya and SM Chitre joined TIFR in 1967. They were followed by K.S. Krishnaswamy in 1970 and J.V. Narlikar in 1972. So these were the four founding members of the theoretical astrophysics group. Now, before joining TIFR, MS Vardhya had done pioneering work in stellar evolution and also in opacities in stellar atmosphere. That time there was some problem about that people felt that opacity, whatever known sources of opacity were not enough to explain the solar atmosphere. And it was later on proposed that H minus is the missing thing, that is the hydrogen with the extra electron. So Vardhya had done important contribution to that, and in fact the first tables of opacity with H minus were made by Vardhya. In fact, I also used them in 80s. Then Krishnaswamy had given his well-known T tau T temperature and optical depth relation, which is still extensively used in all stellar evolution calculations. So in that, for calculating the structure of the atmosphere, we need an additional equation because it is not in thermal equilibrium, because it is being radiated out. So that he had given this fundamental relation, and even today all stellar evolution calculations are using it, and more importantly, it is also known as Krishnaswamy's T tau relation. And Narlikar, of course, is well known for his work on steady state cosmology. So that was this people's thing. And then, of course, there was S.P. Tarafdar, who was actually the first student to complete PhD in theoretical astrophysics in 1972 on sources of opacity in late type stars. So Tarafdar actually joined TIFR in 1963, before the theoretical astrophysics existed. And initially he was working with R. Pratap. I don't know how many of you know him. He was a plasma physicist. He moved to PRL later on. And S. Ramadurai also had joined TIFR in 1963, but his PhD was in cosmic ray physics. And after that, he moved to theoretical astrophysics too. So that was the beginning of the theoretical astrophysics. So I will now outline some work in different areas. So I have tried to cover, of course, I have about 20 odd works, but they are spread over different areas. So of course, there will be some variation between different things. So Narlikar established a strong group working on cosmology, general relativity, and quantum gravity. So of course, the most notable contribution in this area is the detection of gravitational waves, which has already been mentioned in the previous talk by a pair of merging black holes in 2015 by the LIGO collaboration. This is of course not a theoretical development, but nevertheless theory played an important role in that. In particular, the templates for the whatever wave pattern that you see were calculated theoretically, and A. Gopakumar from DA has, and of course there are many others from TIFR who made some valuable contribution in this, and this opened a new window to the studies of astrophysics. So that is of course the remarkable thing. And this was followed by detection of gravitational waves from merger of a neutron star and a black hole. And this, because of the involvement of the neutron star, this was also visible in the electromagnetic waves, and there was a huge number of observations in that, and that gives rise to the so-called multi-messenger astronomy. Of course, this is not the first instance of multi-messenger astronomy, because we had neutrinos and cosmic rays even before that, apart from electromagnetic waves. So that is the thing. Now I will move to other things in cosmology. So one of the important thing now, Kaushik probably was not strictly a member of theoretical astrophysics group, but I have included him because I was sure this work will not be included in the DHEP discussion. So Kaushik and McClelland in 1972 obtained an upper limit of 8 electron volt on the sum of the masses of possible light neutrinos by considering the effect of gravitation on the thermal background neutrinos on the expansion of the universe. So this limit was basically based on the then whatever estimate was there on the deceleration parameter of the universe. So that is an important thing. Then another interesting thing was when Manaban and Chitre 1987 explored the effect of bulk viscosity on the evolution of the universe, and they demonstrated that this can lead to solutions which are like inflation. So of course, I am not sure how the viscosity will come there, but nevertheless, it is an interesting idea. And in a similar vein, the next thing is Pankaj Joshi, TP Singh and their group have been extensively working on the validity of cosmic censorship conjecture. Now that basically says that all singularity in general relativity are covered by an horizon. So they have found some counter examples where they have found many solutions of Einstein equation where the singularity is visible outside. But the issue is still open as to whether any of this can occur in realistic situation. So now we move to gravitational lensing. Chitre and Narlikar were instrumental in starting the work on gravitational lensing, which is basically based on the gravitational deflection of light by massive objects. So basically the gravity acts like a lens, and you can get some magnification and even multiple images and so on because of that. So this has actually evolved into an indispensable tool for studying the universe at large scale, in particular the dark matter, because the dark matter does not have any other effect other than gravity. So that can be studied by this means. Now they were later on joined by Narasimha and Kandaswamy to form a pioneering group for modeling multiply imaged lens system. And in fact, TIFR Central Workshop even produced a model of gravitational lens, which Narasimha very methodically worked out to get the shape of the thing to get the correct image. So that is now one of the first sources to be studied was PG 1115 plus 080. That is the second multiply imaged confirmed gravitational lens reported. It was a quasar at a redshift of 1.72. And initial observations had found 3 images, and they said that there should be a 4th image, and they also predicted what would be the galaxy which will produce that image, and later on all these things were found. So this is just an image of this images and that galaxy in between. So then apart from that, they also modeled these other sources, MG2016 plus 112. This is another multiply imaged quasar at a redshift of 3.23. So they predicted that a massive galaxy cluster as the lensing agent. This was in 1987, and this cluster was actually discovered by ASCA X-ray observation in 1994. So this is again some image of that. So basically this A and so this A, B are the two sources and two images, and the A1, B1 are actually the line forming some region from that side. So this is just extended form of that source, and C and D are the lensing object which form the image. So that is the thing. Then of course, now there it was also observed that the lensing model with extended mass things generally predict an odd number of images, while observation largely found only even number of images. So this was, they had proposed that this could be because of the presence of massive compact object at the center of the lensing galaxy. So that was one of the things. Then of course they were also among the first people to point out the effect of the so-called micro lensing, which they actually called it a millilens. So this is basically when a small compact object comes exactly in between us and the background source. Since all these things are moving with respect to each other, so this will happen only for a short period. So you will get a suddenly sharp peak in the intensity. So that is called micro lensing. And of course, you can infer the mass of the object which is forming the thing, and this can be used to study even objects which are not otherwise visible, like black holes or even planets and other things that are too faint to be seen. Then they also predicted the formation of Einstein ring and giant stars, which are, of course, they called it gravity ring at that time. Now it is called Einstein ring. And then, of course, there's one other important work, which was the rigorous general relativistic. So these were all, of course, you need the relativity, but it is all still weak field approximation. So they computed the thing in the real strong gravity. So full general relativistic treatment of lensing in an idealized spherically symmetric configuration. And this was work done by Veerbhadra et al. In 1998. And they studied Einstein ring, critical curves, and all the things in the system. And they also obtained a rigorous relativistic treatment of the complex system of images. Now, this study was in fact ahead of its time, because in 1998, nobody actually thought that those things can be seen. So these are very large number of images, very close to the source, and also people did not think that those things will be relevant. But now with the Event Horizon Telescope, many of these effects have been actually seen. Of course, that is a much more complicated system than what they considered, but nevertheless, all the effects have been seen. So that is about the gravitational lensing. Now I'll come to the high energy astrophysics. So I have put a few works. These are all in chronological order. There is no specific thing. So Sandeep Chakravarti, who was at TIFR for some time, studied shock solutions for stationary, axially symmetric, and rotating adiabatic flows in the accretion disk of wind. So this is basically high energy astrophysics is mostly the study of accretion disk around compact objects like black hole, neutron star, in some cases white dwarfs. So he studied the shock formation in this thing. Now theoretically you can have 4 locations where shocks are possible, but he found that all of them are not physical. So depending on the situation, either 2 or 3 are acceptable. So for the accretion through wind and accretion disk around a neutron star, there are 3 possibilities, while accretion to a black hole from the accretion disk, it is only 2 of these locations are feasible. Unfortunately, the theory cannot distinguish between these 2. So both are equally possible. So then another thing, this was the adiabatic thing. Now it was extended to include the effect of cooling, and they used the smooth particle hydrodynamics to simulate the thing, and of course to find that given angular momentum of the flow, the shock wave undergoes a steady radial oscillation with the period roughly equal to the cooling time. So these oscillations might be responsible for the quasi-periodic oscillations which are seen in many black hole sources and neutron star and other things. So these are pretty common in many of these things. So he had given some possible origin for some of these things. So that is that. Then we come to the next thing, that is Pranav Ghosh and Abramovich, 1997, they critically examined the strength of the magnetic field threading the horizon of accretion disk-fed black holes in quasars and radio galaxies. Now, they pointed out that the strength of the magnetic field in the current, in that time, current numerical simulations was much smaller than what was assumed earlier, and hence this has to be accounted for. And if you include that, then it reduces the strength of the well-known Blandford-Zenek process, which is one of the process for expecting rotation energy from the black hole. So as a result of this, this process may not be adequate to account for the strongest double radio sources accreting at far sub-Eddington rate. Of course, for the medium and weak source, it will still be enough. So that was that. Of course, Pranav had done a seminal work on accretion disk, but that was before he joined TIFR. So then Alak Ray, Purnam Chandra and their collaborators, 2010, reported a relativistic type 1 PC supernova without detected gamma ray bursts. So the long duration gamma ray bursts are generally believed to be due to the death, during the death of the massive star. So once the massive star finishes all its soak fuel, then it undergoes the collapse and leading to a black hole or whatever. And that time, of course, a lot of energy is emitted, and that also results in a relativistic outflow, which basically manifests in the gamma ray pulse. And it also gives a long-lived radio afterglow. So this gamma ray pulse is along the relativistic outflow, so it is a collimated thing. So unless it is pointing towards the Earth in some reasonable angle, you will not see it. So there is definitely a chance that you will miss that. And apart from that, even the duty cycle of the gamma ray satellites is also limited, so there also can miss things. So this was one of the first examples, or probably the first example of such a event. So that is there. And now I will come to the final thing, that is the stars and the interstellar medium. So Prasad and Tarafdar, 1983, they investigated the possibility of UV radiation filled inside the dense interstellar cloud. So basically, when you have a dense interstellar cloud, because of the optical thickness, the stellar UV radiation cannot penetrate to that. And therefore, of course, people were not expecting that UV will play any role in the chemistry in that deep regions. So they pointed out, and of course, the cosmic rays can penetrate that, and cosmic rays were supposed to drive this. But they reasoned that the cosmic ray will, since the cosmic ray will lead to ionization, but then this electron will again recombine, so that will give rise to a UV radiation. And because of that, you can actually have a UV flux inside the cloud, even though the outside thing cannot penetrate there. And they calculated that that will be enough, and they to get a chemically significant UV flux to be present there. And in fact, they calculated that some of the reactions can proceed at a significantly higher rate, up to an order of magnitude higher, because of this effect. So that was an important contribution. So now, then of course we come to the actual stars. So the work in heliosismology was initiated by Chitre in 1975, and a number of important results have been obtained. So I have listed a few of them. So one of the things is the depth of the solar convection zone. So in the outer 1/3 of the solar radius, the energy is transmitted by convection, and the depth of the convection zone is an important parameter. And in fact, it determines it very sensitive to the various input physics that goes into construction of the stellar model, in particular opacities and other. And apart from that, also helium abundance. Now, helium is, of course, the second most abundant element in the universe and also on the sun. But the helium abundance could not be measured from the photospheric lines, because helium, being a noble gas, it doesn't form a line at a low temperature of 6,000 degrees of the solar atmosphere. So the helium abundance was actually determined using heliosismology. Of course, there were estimates from coronal lines and all, but they are very uncertain because they are a very dynamic region. So now both these things can put a strong constraint on the solar models. And of course, these were not the first measurement of these quantities, but they are the most often quoted values. Now, apart from that, the inversion of rotational splitting was carried out to study the rotation rate in the sun, inside the sun. Of course, on the surface, we know that there is a differential rotation with equator rotating faster than the pole, but we did not know before that what happens in the interior. And in fact, there were many conjectures that the core could be rotating faster than the surface, because basically, because of the energy, because of the angular momentum conservation, the young stars will have very fast rotating thing, and slowly the rotation, the angular momentum is lost. The loss happens to the surface, so it was thought that the core may be rotating faster. And in fact, that had some implication on the test of the relativity also. But nevertheless, the heliosysmic data allowed us to first time actually measure the rotation rate in the interior. And of course, we didn't find any fast rotating core there. In fact, the core is rotating slightly slower than the, at least the equatorial region on the surface. So there are, in particular, the important discovery of these things was there are two shear leads. One is near the surface where the rotation rate increases with depth, and another is near the base of the convection zone, which is referred to as the Tecock line. So that is the region where the differential rotation goes over to a solid body rotation in the radiative region. So that is a sharp transition there. And this was, of course, totally unexpected. And the properties of this region were studied, and also the temporal variation in these properties were also studied. So I think I have a picture of that. So this actually shows the rotation rate as a function of time and latitude. So this is basically, you have subtracted the average at the given latitude from that. So this is basically a residual. So if you see the red or blue, whatever thing, that is the faster than average rotation, and the blue ones are the slower than average rotation. So you can see that there are formed these bands which move towards the equator at low latitude, and towards the high latitude they move towards the poles. So this part was actually pointed out by us first time. And then the top, this is using the Gong data, and that is using the MDI data, that doesn't matter. And the top panel also has these black dots, which are the position of the sunspots. So you can see that this bends coincide with the position of the sunspots. So they definitely play an important role in the solar magnetic field, because sunspots are the sites of the magnetic field. So let me go back there. So now there is another implication. So around 2004, the Esplund and their colleagues pointed out that the heavy element abundance in the sun has to be reduced significantly by a factor of 1.4 or so. They claim that that is because all the earlier estimates were based on the so-called 1D model of the solar atmosphere, which basically is the spherically symmetric thing with some effect of turbulence and all built in, while they use the so-called 3D atmospheric models, which incorporates the turbulence inside there. And they found that using that, it reduces the abundance. And so, but then it was soon found that these models with lower, because once you reduce the heavy element of abundance, because they contribute to the opacity in the solar envelope. So because of the opacity, the depth of the convection zone changes, and these low abundances are not consistent with the solar model. And there was a detailed analysis has been done using both opacity, equation of state, etc. And it was shown that the low abundance models are not consistent with seismic data. Now, since then, a number of independent measurements of the solar abundance have been performed, and things are now moving upwards slowly. Though, of course, even Esplund and their colleagues have also increased their estimate to some extent, but the thing still remains. Now, more recently, of course, there is a data from the Borex-CNO experiment, which has been able to estimate the flux of the CNO neutrinos that should be directly proportional to the heavy element abundance. And that flux is also consistent with the higher abundance, though of course the error bars are still large, so you cannot rule out the other things also. So that is the status. Now let me see. So that is about the sun. Now more recently, the study has been extended to other stars, mainly for using the data from the Kepler satellite, which observed many stars for a period of slightly more than 3 years. And Shravan Hanasoge and his colleagues have detected the latitudinal differential rotation in the convection zones of about 40 sun-like stars. And all of them have the sun-like differential rotation, that is equator rotating faster than the poles. And for the most significant detection, the equator rotates about twice as fast as the mid-latitudes. So this, of course, will have implication on the theories of angular momentum transport in stellar interior. In a similar way, the radial differential rotation has also been detected in an early red giant, this KYC 7341231, where the core was found to rotate at least 5 times faster than the surface region. So this, so of course, people were expecting that in the sun, but in sun didn't happen. But it has been found in the, of course, in the red giant, the core is extremely small. It has already condensed during the later stages of evolution. So this result can constrain the angular momentum coupling between the core and the envelope of the red giant. So I think I will stop there. I think I have made up most of the time. So, okay.
Thank you, Professor Antia. And is Prabhu around? Okay, I believe that closes this session, and we'll have a tea break and come back in 15 minutes or so. And the tea is now on the right-hand side as you go out, on the right-hand side in the what we call as the grower canopy.
Raghunathan knows. Raghunathan lecture. First Raghunathan is there, then I channel uploaded. Raghunathan is loaded now. Yeah, I'm gonna check for current. Okay.
Yeah. No. You go to talks. Inside in this talk, you go into this. In that one, TIFR Landmarks. Last one. To check some slide. Yeah, okay.
प्रोफेसर होसू इनका सेंड किया था या नहीं उनके पास है डाउनलोड हाँ है ना है ओके हाँ इसमें अभी उनका है नहीं है मेरे पास हाँ
कॉपी
नहीं उनका पीडीएफ है पीडीएफ हाँ फुल स्क्रीन शेयर करके जब देता हूँ
हाँ शेयर है
शेयर्ड है ये हाँ शेयर्ड नहीं है वो धूम में शेयर नहीं हो रहा है क्या अरे उन्होंने किया ना उधर नहीं आ रहा है क्या एक मिनट एक मिनट एक मिनट क्लिक ऑन
झूम मधलं बाहेर आलं
हाँ
झूम मधलं बाहेर आलं
शेयर है ना ओके ग्रेट थैंक यू शेयर्ड है शेयर्ड है जूम पे शेयर्ड है ना आप बोले हाँ आ रहा है ना?
फ्रेम में रहा हमारा केलं
हाँ लोड किया.
केलं मग कधी जातानाच केलं
हेलो.
last session of this day. And one announcement is that after this session, there will be 90 minutes break, that is 1.5 hours. And dance program will start at 7 o'clock, not at 6:30 as it is mentioned in the program booklet. So please note that you have 90 minutes of break. You can have a walk on the seashore and many other things one can do. So now let me welcome Professor M. Krishnamurthy to chair this session. And there will be two talks from Professor Raghunathan and then Professor Hosu. MK, please come on the stage. Yeah, it's all yours.
Thank you, Prabhuji, for giving me this opportunity. Indeed, it's an honor to be able to introduce the next two speakers. Of course, I don't think anybody here or anybody who knows TIFR needs an introduction to both of them. Professor M.S. Raghunathan, if you know maths, you know Professor M.S. Raghunathan in TIFR. So, Padma Professor M.S. Raghunathan is an FRS. He's a well-known mathematician. He's currently the head of National Center of Mathematics in IIT Bombay. Was formerly the professor of eminence at TIFR and Honorable Chair. He's a recipient of all the kinds of awards you can think of, all the elite societies of academic societies of the world, whether it is Royal Society or Academy of Sciences, American Mathematical Society, and he's also the jury member for the Infosys Science Prize. I welcome Professor M.S. Raghunathan to give his account about the maths department. School, sorry.
I'm teaching at CEBS, and the last 5 years I've been with them. And for the first time in my life, I've been teaching undergraduates. Well, the title of my talk is the School of Mathematics at TIFR, Some Highlights. Well, actually, I want to talk about some highest lights, I must say, because there are lots of highlights which I would like to talk about, but 40 minutes is too short a time. But then I probably can claim some privilege because of my age. I'm 9 years older than Spantavadia, so I should get 9 minutes more than what I got. Okay, so let me begin. I want to say a few more things about my talk. It's entitled, as I said, Some Highlights, but that means automatically some other highlights will be left out. In the 40 minutes time, I cannot say that. And I must apologize to those people who are responsible for those highlights for omitting them. And at my age, I'm afraid nostalgia will prevail over other considerations. So I will probably talk much more about the early days, my early days at TIFR than later period. Secondly, I cannot say that I've kept up as avidly as I used to with the developments of the school in this century. So my talk will largely talk about things before 2008. So I'll be largely speaking about the first 50 years of TIFR. Of course, there are some 15 years, no, not 15, how many years? Yeah, 15 years before. The TIFR had been in existence 15 years before, but I talk say something about that. And I think in some sense, that's probably the most interesting part because many people will not know about those years. For me itself, it's not direct knowledge, but hearsay. Thirdly, the constraint imposed inevitably means something does not get mentioned anyway.
Homi Bhabha from the very beginning wanted mathematics to be a part of TIFR's activities. I think the slide shown by Grover, he had a letter from Hill or somebody telling him that mathematics should be part of the institute, right? Dirac, okay. Dirac, of course, was half mathematician. I mean, though mathematicians had a lot of trouble fixing up his ideas to fit into rigorous mathematics. I mean, the Dirac function, which is zero everywhere but infinity at one point, and so that the integral is one, was something which mathematicians couldn't live with. They finally found a way of getting around it, but that's another story. Okay. As early as 1946, he inducted the mathematician D.D. Kosambi, then working at Ferguson College, Pune. And the second mathematician who he inducted was this man, F.W. Levy. He was a group theorist. He had fled Nazi Germany in 1935 and taken up a professorship at Calcutta University. Jawaharlal Nehru kind of extended an open invitation to Jewish intellectuals who wanted to come to India, and he is one of the few who accepted the invitation and came to India and joined Calcutta University in 1935. So he had been already in India for more than 10 years when Baba brought him to Bombay. Both Kosambi and Levy were good mathematicians, arguably among the best working in India at that time. There were a few working outside India, Indians who probably were of higher caliber, but not very much. Kosambi served on the committee to select the Fields medalists in the year 1950. This is something which not many people know. That if you like, is the start of a association with an international body by an Indian mathematician. Begins the engagement of TIFR mathematicians with the International Mathematical Union. Ever since, someone or other, for instance, has been some member of the School of Mathematics has been a member of the executive committee of the International Mathematical Union. The premier international body engaged in the promotion of mathematics. That involvement continues to this day. I think right now, a member of the executive committee is an alumnus of TIFR, Ramdas. However, barring that foray of Kosambi's into international arena, mathematical activity at TIFR until 1950 was confined to the two mathematicians pursuing their own researches. They didn't even seem to have had students at that point. This was to change in the early 50s. K. Chandrasekharan, then not at 30, joined TIFR as the reader at Baba's invitation in 1949. There is a story, obviously, it's a second and third and fourth hand story, I do not know what, but it sounds very authentic about Baba's meeting with Chandrasekharan. Baba met Chandrasekharan at the Institute for Advanced Study in Princeton, where he was assistant to Hermann Weyl, the great mathematician physicist. And at that time, he offered the job to Chandrasekharan, and Chandrasekharan, after a little thought, apparently accepted. And the story is, one day he was taking a walk with the great John von Neumann, and ahead of them, Baba was walking with Einstein and Yukawa. And von Neumann turned to Chandrasekharan and asked him, "I believe this man has offered you a job in Bombay. Are you going to take it?" And Chandrasekharan said, "Yes, more or less, I've decided." And then Baba told him, "That man is as good a physicist as me, but don't let him intimidate you. Stand him up. Stand up to him." This is the advice von Neumann gave to the Casey. And if anyone stood up to Baba at the Tata Institute, it was Chandrasekharan. Apparently they had their differences, which is why he left in 1965, but they would also had great mutual regard. For example, most of you know that the mural painted by Hussain was decided on after a competition among many Bombay artists. And there was a committee to select the various entries submitted by the artists. Chandrasekharan was the only person from the Tata Institute, member of the Tata Institute, who was on that committee. along with Baba was the chair, and he was on that committee. All the others were related to art in some way. But Chandrasekharan was on the committee. So, I mean, so apparently Baba had great regard for him, even as a non-mathematician, if you like. Actually, Baba inducted him into the Scientific Advisory Committee to the cabinet of those days. He was the chair. Nehru had made him chair, and he brought Chandrasekharan in. And Chandrasekharan, I'm told that Chandrasekharan actually was the person who drafted the science policy resolution of the government of India. Sorry? Okay. Yeah. Yeah. Chandrasekharan joined TIFR in 1949. I think you mentioned that he had been made the offer in 1947, but he could join only in 1949. But that's a picture of Chandrasekharan. He also appears in some photographs which are displayed just now. So, and he was primarily, I must say, he was primarily responsible for making the School of Mathematics an internationally renowned center. When he joined, there were two others, namely Levy and Kosambi. Neither of them really thought in terms of having students or building groups, but Chandrasekharan thought of that, and he set about doing whatever is necessary for that. Komorovolu is the village or something from which he comes. It's a village near a small town called Bapatla in Andhra Pradesh. That's where he was born and grew up, and then graduated from the University of Madras. He was a student of K. Anand Rao, a renowned mathematics professor at Presidency College, Madras. After his degree, he took up a temporary job as a lecturer at Presidency College. During that time, he met Marshall Stone, a leading American mathematician. Stone had acquired an interest in Carnatic music, which made him come visit Madras frequently. And on one of those visits, he met Chandrasekharan. Stone was impressed by the young man and arranged for him to visit the Institute for Advanced Study in Princeton as assistant to Hermann Weyl. Stone has done a lot of these things to Indian mathematicians. Chandrasekharan is not the only one who went to Princeton because of him. There were 3 or 4 others who have done that, who did that because of him. It is at that institute that Homi Bhabha, out on a recruiting spree, met Chandrasekharan, that's wrong, 1947, I stand corrected, and made his offer. The first important initiative that KC, as Chandrasekharan came to be known, was the starting of what was essentially a graduate school in mathematics at TIFR, but it was not a formal structure. But it functioned very much like a usual graduate school in an American university. I think it was, in some sense, better structured than the physics school, than the graduate school in physics. Graduate school in physics got somewhat later a more firm structure, but here Chandrasekharan started the graduate school and started lectures, graduate lectures at the graduate level, right from the beginning. The beginning is probably 52 or maybe even 51. I don't remember exactly. I mean, I've not checked exactly when the graduate school started, but with just these 3 people, it's not clear how to. There's one more person who joined, Bala Gangadharan, who was a lecturer in Pune. He came to Bombay as well. But with these 4 people, it's not clear that they could run a proper graduate school. Only 4 people, of whom 2 of them were not really involved. Levy and Kosambi did not take great interest. Levy, in fact, returned to Germany in 1950, quit in 1950. So what Chandrasekharan did was start a graduate school. Students were recruited as research assistants. That's also the case in physics. But in physics, people went through what was called the training school of the Department of Atomic Energy. In mathematics, they came directly to Tata Institute. And there was a regular pay scale, not like the graduate students today. There was a regular pay scale. And that was, in some sense, helpful. It gave you a feeling of belonging to the institution, which graduate students may not feel. Nowadays, for a period of 5 years, of which the first year was the probationary period with salaries on a pay scale, the recruits being entitled to even provident fund of with the institute contributing. All that was so it looked like you were in a regular job for most people who joined it. This was the Tata Institute continued this practice right up to, the School of Mathematics continued this practice right up to 1984, whereas the School of Physics had given it up much earlier. This was very similar to what was happening in physics, except that the physics students spent the first year at the Atomic Energy Training School in Trombay. Now, a few years after joining this institute, Casey got a colleague from his Madras days to join TIFR. The colleague KG Ramanathan was of great help to him in running the graduate school. Levy left TIFR in 1950. Another mathematician, Balangadran, joined the institute soon after that. With only 4 people, it was difficult to organize courses for the graduate school, which Casey envisaged as covering a wide spectrum of areas. He wanted graduate students to be exposed to a wide spectrum of areas, which is what would happen in a good American university. His own expertise was in classical analysis, as was that of Balangadran, while Ramanathan was a number theorist, which is also of a classical kind. With Kosambi, a third area, differential geometry, could be covered. At that point of time, Kosambi was doing some differential geometry. That is KG Ramanathan. Chandrasekharan was a first-rate mathematician, but not acquainted with the then recent exciting developments in depth. However, he knew what was really interesting, what was going on. He may not know things in depth, but he had a very good idea, a broad idea of what is happening and what is interesting, that kind of thing. He had good instinct for that. Ramanathan had a somewhat better understanding of some of this. Nevertheless, that the students get good exposure on a wide front with areas where big advances were being made was one of Chandrasekharan's objectives. Chandrasekharan hit upon a plan to achieve this, get visitors from abroad to give advanced courses which the local faculty was unable to handle. It was here that his extraordinary abilities came to the fore. Even while his expertise was limited to classical analysis and number theory, he had a broad idea of what was happening in diverse mathematical areas, and he was an excellent judge as to what students should need to be exposed to. It's an amazing ability, you can be a very good mathematician, but this kind of perspective on what is the right thing for development and so on is a remarkable ability which he had. During the 2 years he spent in Princeton, he had made friends with many leading mathematicians in the West and was on first name terms with people like Hermann Weyl. He persuaded many of them to visit Bombay to lecture to his carefully assembled students. He managed to get some of the greats of the 20th century to visit Bombay for extended periods of lecture courses. In fact, every visiting professor he got here was of a very high stature. Some of them had already high stature, but there were other younger people who became great people later. At that time, thanks to his network, he knew from his friends like Hermann Weyl who of the younger generation are going to blossom into great mathematicians. And many of them, long before they became well known, were invited to Tata Institute to give lectures to the graduate students. And coming to Bombay at that time, only with leaving behind your colleagues with whom you are doing exciting research, coming here and spending 3-4 months was not something which one could easily be persuaded to do. But this man had the ability to do that. And 2 of the distinguished visitors were to influence profoundly the course of mathematics took at TIFR. C.L. Ziegel from Göttingen, one of the greatest mathematicians of the 20th century, and the distinguished Fields medalist Laurent Schwarz from Paris spent extended periods of time several times. Each visit would be 3 months long, and they came something like 4 or 5 times to visit Bombay to give graduate courses. It's a a great service they did to us, to this institution. And I mean, the point is that Chandrasekharan could persuade them to come, and they would come again and again because they found the students extraordinarily good. That was another thing which KC managed. He got hold of really good students from all over the country. Actually, at that time, he did advertise all over the country, but most of the people came from Madras, the south, anyway, Tamil Nadu, Kerala, that kind of Karnataka area. So those are the photographs of Ziegel and Schwartz. Ziegel was a interesting man, very formal, always dressed. Both of them are in jacket and tie, but you can't find Ziegel without that dress. I mean, with the formal, always in a suit. And when he lectured, he would not brook any interruption. You can ask questions at the end of the lecture, but not in between. That's the kind of. Schwartz was much more informal. I mean, he was in this picture, of course, he's also in a suit, but he was very informal. And he talked to students freely. Ziegel, you have to make an appointment to see and talk to him. But Schwartz was very different. Even as the graduate school started functioning, KC made a reluctant Baba to create a separate school of mathematics with practical total autonomy. At that time, everybody was a professor in the common faculty of TIFR. That's how things were. After he joined, this man thought what was happening at the Institute for Advanced Study should be brought here. And there were two schools, School of Physics and School of Mathematics. And he wanted the same thing here. So apparently Baba was initially reluctant, but he yielded to pressure. I mean, they had a complicated relationship. It was, they respected each other. At the same time, they had strong differences of opinion. From then on, there were two faculties and joint meetings were rare. In fact, Chandrasekharan probably deliberately avoided joint meetings because he wanted to preserve his autonomy. That's a very, Baba was a person who could, had a dominating personality. So it's not surprising that, and he was living up to his promise to Pannaima. The mathematics faculty in the 50s consisted of just two people. I mean, it should be three. I mean, Kosambi, Ramanathan, and Chandrasekharan. In those days, and right down to the 80s, only associate professors and higher ranks were called faculty members. The people like readers were not considered faculty members, but there could be faculty members at the wish of the director. The director wanted somebody to appoint a faculty member. That could be done. That was done. The students were recruited with great care. The research assistant posts were advertised nationally and the application scrutinized to shortlist some 50 people. These interviews would last, I suppose it was similar in physics, these interviews would often last for 45 minutes, 1 hour, and things of that kind. It's the kind of, but the questions are all purely science, mathematics, nothing outside. My own experience of that was mixed because I thought I was answering badly, which is apparently not true because I was eventually selected. But I liked the questions because they were clearly trying to examine whether I understood things properly. That was the kind of that's the kind of questions they were asked. So on the one hand, I enjoyed the interview, and on the other hand, I was feeling not so good because I was not answering properly. I mean, apparently, from my experience was that eventually what I learned is that they would question me or give a wrong answer, and then they would point out why the answer is wrong. Then I'll correct myself. It will go on like that. So that is what they wanted to see. They wanted to see if I could think on the spot and get to the correct thing, even if I make an initial mistake. Apparently, that's what they were trying to do, and that's what they did in all interviews. And when eventually I was on those interview committees, I had learned what to do from that. Anyway. And these, some 50 were called to Bombay to be interviewed by a small committee. The interview was designed not so much to test the extent of mathematical knowledge as to find out if the student had understood the mathematics she or he had been taught and had the ability to think. Often a visiting professor served on the committee. If there was some professor visiting at the time of the interviews, they would induct him into the committee. The recruitment process proved very successful and continues in the same way till today. There are many things which Chandrasekharan started, which is still being followed by the School of Mathematics. The students started producing research work from the mid-50s. The graduate schools probably started in 51 and 52. From the mid-50s, students produced research work. Of course, Chandrasekharan and Ramanathan were active in their respective fields, but the first research work produced by the students were not in their fields. They had branched out already at that time. T.P. Srinivasan, who joined the TIFR during this time, I don't remember the exact date when he joined, he came up with a theorem which the great von Neumann had said was unlikely to be true. So that made a splash, obviously. I mean, but then it turned out that von Neumann had made many brash statements of that kind. But anyway, this certainly, somebody says von Neumann is wrong, is certainly a big achievement for a fledgling institute like Tata Institute. The first piece of work breaking away from classical areas was a paper by B.V. Singhbal entitled Algebraic Basis of Morse Theory. Singhbal was a very bright man, but unfortunately, in later years, he was not living up to his abilities properly. In fact, he never got a degree. This paper would have been quite adequate for a degree, but the man won't write it up. You get all kinds of characters in science, as you know, and this is these were. But I must consider both these as landmarks. The work of T.P. Srinivasan and the work of Singhbal. Though they are, I mean, over time, you cannot say they took this test of time, but they were at that time certainly works of importance. Well, in general, in mathematics, there is no obsolescence. A theorem, once it's there, it's always there. A theory in physics can get blown off at some point. But nevertheless, some theorems keep being used later and then they have a much greater life. And also sometimes a theorem which has been ignored for ages suddenly becomes important because somebody just used it in a very clever way. That kind of thing happens in mathematics. So it's still possible that the work of Srinivasan and Singhbal may have repercussions in the future. One cannot say. But there are certainly good pieces of work at that time and involved clear good intellectual effort. 1953 must be considered a landmark year in the history of the School of Mathematics. That was the year when two of India's greatest mathematicians of the post-Ramanujan era joined the Tata Institute as students, joined the graduate school, M.S. Narasimhan and C.S. Seshadri. 1953 is the year they joined. By the mid-60s, they became world leaders in the area of what are called modular vector bundles. One problem with mathematics is that you cannot tell anybody outside mathematics what that means. I cannot say what modular vector bundles means. It's even some physicists, I may manage to convey something, theoretical physics, but unfortunately I cannot do anything. I just have to tell you, modular vector bundles was a very active area in mathematics at that time. And these two guys came up with a brilliant theorem which contributed immensely to making TIFR an internationally renowned center. That is some joint work by Narasimhan and Seshadri. Seshadri continued to work in that area, in the broader area of algebraic geometry, which went beyond moduli. Narasimhan has dabbled in several different things. It's a remarkable mind because in every one of those things, he came up with proving long-standing conjectures, which other people were struggling for a long time. This man enters the field, picks up whatever is necessary in no time, and then proves the theorem. That is Narasimhan's forte. And he has proved several theorems like that. I will mention some of them later. The brilliant work, well, I don't know if it's going to make sense to anybody except some mathematics people. their brilliant work gave a transcendental characterization of stable bundles on a compact Riemann surface, which is an algebro-geometric concept. The purely geometric, it's essentially an algebraic concept, vector bundle, a stable vector bundle, but they managed to give it by transcendental, I mean by using methods of analysis rather than algebra. The stable bundles have been defined purely algebraically by a mathematician named Mumford, and these people came up with showing that what he defined is the same thing as something which is which can be defined through analytic means. Never mind that. Obviously, it's hopeless trying to explain what that means. I will not say more about it. Narasimhan and Seshadri had earlier, by 1959, done work of some high quality, which had nothing to do with the later work on vector bundles. Seshadri made the first dent in what is known as Serre's conjecture on projective modules. Again, a string of words. I'm afraid jargon is inevitable when you talk mathematics. Therefore, it's difficult to convey to lay people. There are occasionally some things which you can say, something which become intelligible to lay people, like Fermat's last theorem, but that is rare, unfortunately. So there is one piece of work from the Tata Institute where this will work, but other pieces of work I simply have to use words and tell you is great, and you have to believe me. That's all. So Seshadri made the first dent in Serre's conjecture on projective modules, making him instantly famous. Narasimhan proved a regularity theorem for elliptic equations, which made him known internationally. Once again, these are two very different things. One is a problem in algebra, the other is a problem in analysis. And these two guys were working on different things at the time in 59. In 62, they came together to prove their joint theorem. Narasimhan, as you see, passed away 2 years ago, and Seshadri 3 years ago. They were together in college, the classmates in college, and came to Tata Institute the same year. And their career progression was entirely similar. At every stage, they were promoted at the same time, etc., etc. And some are. Sorry? Age. No. Seshadri was born on February 28th, a leap year. And Narasimhan was born in June. So there was a few months difference, 4 months difference, but the date looks like a year gap. But, well, you know, these are more interesting things than what I can say about mathematics, but which of course is going to mean I'm going to overstep my time limit. So, but the high point of 1959 was either of the two results. That honor should go some work by Raghavan Narasimhan, who was 22 at that time and had joined the institute in 1957. So 4 years after Seshadri and Narasimhan. This is another Narasimhan. His name is, one always used Raghavan Narasimhan because if you use the initial Rav Narasimhan, there's another Rav Narasimhan in the institute, who people know better, of course. He cracked a 50-year-old problem, a conjecture made 50 years before, maybe even more, about Riemann surfaces. He proved that an open Riemann surface admits a proper embedding in C3, proper complex analytic embedding in C3. Well, once again, I have to throw up my hands if you ask me to explain all that. But that was a theorem which lots of people working in the forefront of complex analysis were looking for. And this guy comes in at 22. The previous year, he had a course on several complex variables, and then proves the theorem. And in that course, the lecturer, mathematician by name Malgrange, has mentioned that as an open problem. And 6 months later, the guy has the proof of the conjecture. Of course, it made a big splash with the question. And that meant instant celebrity and got him the prestigious invitation to an address at the International Congress of Mathematicians. The International Congress of Mathematicians is something which meets every 4 years. And they have some lectures called plenary lectures about 20 of them, and about 100 lectures which are called sectional. That is, it's divided into number of subjects, and each subject they invite some people. What Raghav Narasimhan gave was a sectional lecture on in several complex variables, which is the subject of his specialization. He followed that big achievement with a series of path-breaking papers to become a leader in the field of several complex variables. If you name the top half a dozen people at that period who worked in several complex fields, his name will certainly figure. And similarly, Narasimhan Seshadri in the mid-60s, among the people in algebraic geometry, name about a top dozen, they would figure there. That's the kind of stature they had. That's the kind of value their work brought them. Raghav Narasimhan was also from Laila College. Laila College seems to have supplied a large number of brilliant students to Tata Institute. And it's not surprising because it had an outstanding mathematician. I mean, in colleges, you don't find the real research mathematicians, but Laila College had a research mathematician, a Frenchman by name Father Racine. He was a Jesuit, and he was sent out of, he was in fact, had a doctorate in mathematics. He was sent out to teach by the Catholic mission. And after spending some years in Palayam Kottai in Tamil Nadu, he came to Laila College. And that was a great piece of luck for many students in Madras. They learned really interesting mathematics because of the man outside the syllabus, strictly outside the syllabus. So, and that's how both Narasimhan and Seshadri benefited by the presence of Racine, and so did Narasimhan, and so did C.P. Ramanujan. Ramanujan and Raghav Narasimhan were classmates. And apparently these guys used to talk a lot of mathematics, which had nothing to do with what was going on in the class. And they had learned a tremendous amount of mathematics. When I joined the Tata Institute in 3 years after these people did, everybody was of course talking about these two guys and how they knew a hell of a lot of mathematics. They were at once intimidating and at the same time also a source of inspiration. Because if one thought, okay, these guys have learned, maybe I can also do that. On the other hand, my God, when will I get there? Kind of feeling. It's a mixture. It's sometimes when you are in cheerful mood, you thought maybe I can do it. At other times, you felt depressed. Ramanujan too rose to great heights. His thesis was a splendid work on cubic forms, settling an old question. This has been the strength. Every time I talk about one of their works, you'll see that they were solved a long-standing problem, which in itself tells you that it's a good piece of work without any further thing. Something which is 20 years old, 15 years old, if you have solved such a problem, it's clearly, and that is Raghav Narasimhan and C.P. Ramanujan. And they were very different. Raghav Narasimhan was somewhat flamboyant. He was completely extrovert. Ramanujan was the very opposite. He was introverted. In fact, the man had serious problems. He was schizophrenic and eventually committed suicide. You can see he died young, 36 years old. I know, both people were modest in one sense. That is, they certainly, like, you read Newton talking about himself. He says, I don't know what I appear to the other world outside, but I was like small boy and so on. Of course, that was somewhat disingenuous because Newton certainly knew that he was considered a great man by all of Europe. But the second part, when he says that he is like a boy and so on, when the whole ocean of truth lies before me, that is modesty, all right. That is modesty before science. And both these people had that modesty, even though this guy was flamboyant and that guy was not. And Ramanujan, everybody would think was modest in the usual way. He wasn't. He was unhappy that he was not Hilbert. That was I mean, he said, what have I done kind of thing you would say, but that meant I'm not Hilbert. That's what it meant. But the kind of talent he had every reason to hope to become Hilbert. I mean, that he was that kind of mind. It's a fantastic mind. Well, there's one problem which, his thesis was a splendid work on cubic forms, settling an old question, but the pride of place among his works goes to work related to what is known as the varying problem. Here I can say something which anybody can understand. So I will do that about the varying problem. The varying problem was the following. I mean, David Hilbert solved the varying problem. And the solution was this: fix an integer q. Then there's another integer gq greater than 0, such that every positive integer is a sum of gq qth powers. This was proved when q is 2. That is, Lagrange long ago proved that every whole number can be written as sum of 4 squares. And this is a natural question generalizing it. Can you write anything as sum of qth powers, but with a fixed number of qth powers? You shouldn't. I mean, if you want, if you allow any number, anything can be 1 plus 1 plus 1 plus 1, it's a qth power. Everyone is a qth power. So that's not the point. You have to restrict the number of qth powers you want to do. Hilbert proved this outstanding theorem, the solution of the varying problem. Ramanujan proved that there is a integer G capital Q such that any integer in any number field. What's a number field? I can say something about number field. Number field, you start Q is a number field. Rational is a number field. And then you look at numbers like A plus IB. I is the square root of -1. A and B rationals. That's a number field. Or take A plus root 2 times B, A and B rational. Root 2 is not rational, so it doesn't belong there. Such numbers, such a collection of numbers is called number field. And the theorem that Ramanujan proved that there's a GQ such that any integer in number field, once again, an integer in number field is when I write A plus IB, I can take A, B to be integers instead of rational numbers. Then it's an integer. Similarly, A plus root 2B, A and B integers. So that's what you mean by integers in number field. And then he proved that there is a GQ which is independent of the number field, such that any number in K, which is a sum of qth powers, is a sum of GQ qth powers. What happens in the case of number fields is there are some numbers which cannot be written as a sum of GQ qth powers. You simply cannot do that. You cannot write it as any sum of any number of qth powers. You cannot do that in a number field. For instance, if you look at root 2, you cannot write it as root 2 is a bad example. Sorry. Anyway, there are numbers which cannot be written as sum of qth powers. That is true. But the moment you can write the sum of qth powers in some way, then you can do it already in GQ qth powers. That's the theorem of Ramanujan. This is as a result which had defied the attacks of the great Ziegel. Ziegel was, I told you, was one of the greatest mathematicians of the 20th century, and that guy was trying to prove it, but this guy beat him to it. Ramanujan beat him to it. So you see the caliber of the mind, and it's entirely reasonable that he should hope to become a Hilbert. So it's not. There was a major contribution. There was a major contribution to the varying problem from TIFR at a later point. This was much later, but since I talked about varying problem, I might as well do it now because I don't have to recall all these definitions later. R. Balasubramaniam was the person who did it. He joined the Tata Institute in 1972 and wrote his thesis with Ramachandra. That first piece of research was the resolution of a conjecture of a famous mathematician, Titchmarsh. That meant immediately we had great expectations of the man, and he lived up to it. He kept proving beautiful theorems. And the most impressive of his achievements was the determination of G4. I told you, every G4 is the number of numbers you need to have a sum of 4th powers. So he showed that G4 is 19. 19 is G4. That is every whole number, purely in Q. Every integer can be written as 19, sum of 19 4th powers. That is Balasubramanian's theorem. Actually, the varying problem seems to have had some kind of what's the word I want? Affinity to Indians. There's a mathematician named S.S. Pillai, whose name is not well known, but he was actually a great Indian mathematician, I should say. He had determined GK for every K greater than 6 as by 1949. And in 1950, he was invited to the International Congress of Mathematicians to give a talk and died on the way in an air crash. Anyway, Pillai had proved this, and then G3 and G5 were also determined soon after. G4 seemed to be a difficult nut to crack, and finally, Balasubramanian, in collaboration with two Frenchmen, proved that G4 is 19. Okay, that I'm actually jumping chronologically, but I'll go back now. Say, Chandrasekaran became a member of the executive committee of the IMU in 1950. Even before that, you know, this mathematician Marshall Stone I mentioned, he had started. There was an earlier international mathematical union which got into problems because the conflict between the French and German mathematicians. The war separated them, and already the First World War, there was a lot of conflict, and so the organization was kind of deteriorating. And Marshall Stone stepped in and tried to revive it, and got new statutes and everything written. And in that, he took Chandrasekaran into the committee to form that. And he obviously had impressed Marshall Stone for things other than mathematics, as with Baba, for instance. He was to serve on that committee for some 25 years on the executive committee. Every 4 years, they elect a new one. This guy got elected every day. And 6 years, he spent as secretary, and 4 years as president of the International Mathematical Union. So that is the association with the International Mathematical Union, so long as Chandrasekaran was there. But after he left, he saw to it that some of his younger colleagues got in there, and it has been continuing. Right now, as I said, Ramdas, who was used to be here, is a member of the executive committee. Early on, in his first stint as a member of the EC, he got IMU to co-sponsor the TIFR, an international meeting every 4 years in TIFR, and he named it the International Colloquium in Mathematics. Every 4 years, the first colloquium was held in 1956, and already had some very distinguished speakers. In fact, the talks given in this colloquia, in the proceedings, you find some of the, what's the word I want, seminal papers in different areas of mathematics. The first was held in 1956, and not unsurprisingly, Casey was the only speaker from India at that time. The international colloquia have since been held every 4 years, with just one break caused by the untimely death of a TIFR member. That was V.K. Patodi. Well, as you see, I'm in 1956 here. I had demanded 9 minutes extra time. If you give me that, I'll be happy. Okay. Okay. I'll try to rush through for the press. I mean, in fact, the rest of it, if I go on, it will only be something about what somebody proved this, somebody proved that, etc. Okay, and some names will emerge. Okay, the colloquia is regarded as highly prestigious. The organization is responsible to a committee headed by the dean, mathematics faculty. The mathematics faculty decides on what subject the colloquium should be held. And usually what they do is to see what exciting things are happening in mathematics, and then choose one in which there is some significant contribution from TIFR. And fortunately, we have been able to, the School of Mathematics has been able to do that continuously right till now. Okay. Yeah, the 60s emerged as a major international center in diverse areas of mathematics. I've already, Natman and Seshadri, I had mentioned their work, who had made it a hub for algebraic geometry. Differential geometry is another area in which TIFR rose to eminence, thanks to a joint paper titled Universal Connections by M.S. Narasimhan and S. Ramanan. This work is the trigger behind the so-called Chern-Simons invariant, about which I think Spetavadia said something about it. Chern-Simons theory, what he said. The mathematical theory behind Chern-Simons theory is this work of Nathan and Ramanan. It has not been adequately acknowledged. Chern has, in private conversations, said that he got the idea from this paper, but it's not put down anywhere in literature. But clearly, it's this is a. I know this paper very well. It's a wonderful paper, and it's a kind of landmark paper in differential geometry. Ramachandra, who joined the TIFR as a student at a somewhat advanced stage, specialized in number theory of a somewhat different kind from that of Ramanujan. See, the Casey had some general philosophy about the graduate school. All the students in the first year will have to be exposed to certain basic courses. It's compulsory for everyone. But Ramachandra was exempted from that. And Casey saw that he was a very different kind of person, and this kind of discipline will probably not help him. So he said, we leave him alone. And he was left alone. He was not subjected to the first year courses. That is Ramachandra. Of course, the picture was taken when he was pretty old. And he wrote a paper titled On the Chronicus Limit Formula, appearing in the prestigious Annals of Mathematics, which has had a big impact in number theory over the years. It's still very alive paper, so to speak. Okay, at the risk of sounding immodest, which I suppose I am, I must mention my own work in discrete subs of D groups. This is the area of D groups in general. It's an important milestone in the second half of the 60s, which contributed to strengthening TIFR's position in the international arena. Further work I did in this area, some of it in collaboration with Gopal Prasad during the 70s and 80s, served to place TIFR in the forefront of this area. In the latter half of the 60s, C.P. Ramanujam turned to the study of topology of affine varieties. Earlier, he was working in number theory. He started on this. His research on the topological characterization of the affine plane was the beginning of the in-depth study of the topology of affine surfaces all over the world. Whoever was studying this paper had to be the foundation. R.B. Gurjar of TIFR was among the leaders in the subject in the 80s. Some of Gurjar's work was done in collaboration with Anand Shastri, also at TIFR. Important results were obtained by Paman Murthy in commutative algebra, which is essentially affine algebraic geometry. This was also done in the 60s, and he continued to do it in the 70s, but mid-70s he left the Tata Institute. So, Paman Murthy was a very interesting character, but I cannot go into stories about him in the time I have. Many younger people inspired by Seshadri and Narasimhan took to the study of algebraic geometry, in particular modular problems. The leading figure among them was Ramanan. In the 70s, there were more adherents. At the end of each decade, there was a school. At the end of the decade, there was a school in the area, in the sense that a good number of the group. Many significant contributions came from Ramanan and Ramanathan. Even as TIFR was performing at a superior level in areas where it had established itself, in the late 70s, Etanver area came into the ambit of the school. S.G. Dani embarked on research in homogeneous dynamics and established himself as a leader in the field by the end of the 70s. In the 80s, sorry, that was a mistake. In the 70s, too came work further work in affine algebraic geometry. Parimala created a stir by giving a counterexample to what is known as the quadratic Serre conjecture, and I followed this up with a comprehensive treatment of the question. The big story of the 70s is a tragic story of Patodi. Patodi joined TIFR in 1967 as a student. His teachers recognized him exceptional talent, and yet were pleasantly surprised when he came up with a manuscript proving a conjecture of McKean and Singer. I mean, he was not very sociable, so he was not moving around, he was not talking to people in a big way, but quietly he was reading a paper and working on it and proves the theorem. And this is around 1970 or so. 67 is a student, 70 he comes up with a paper proving a conjecture which many others would have been very happy to prove. This was just the beginning of a series of papers that culminated in a new proof of the celebrated Atiyah-Singhal theorem in collaboration with Atiyah and Watt. The stature of the collaborators notwithstanding, Autodis was the key role in this joint work. You know, in mathematics, the authors' names are written in alphabetical order, unlike in physics where you first named authors greater importance is gone. That doesn't happen in mathematics. And as you can see, Autodis' name would have been the last, but in a physics situation, probably his name would have been the first. Tragically, Patodi died in 1976 at the tender age of 33 at the height of his powers. And that is the reason this 78, there's a colloquium supposed to be, interact colloquium supposed to be held around that time. It was supposed to be in his area, so it was cancelled. The pride of place in the research done in the 70s goes, in my view, to Madhav Nori's work on fundamental group schemes. It's a work in algebraic geometry. It's a theory rather than a solution of a specific problem. You know, there are two kinds of mathematicians: those who solve problems and those who develop theories. And those who develop theories think their theories will automatically solve the problem. So that's why they develop theories. So most mathematicians at the Tata Institute have been problem solvers. Madhav Nori has done something towards building a theory, but it's not such a big theory eventually, but it's a theory all right. And it did solve some problems. He left TIFR in the 90s, a really serious loss for us. Other people have left, but this man's going was much more of a serious loss because everybody was talking mathematics to him. And anytime you talk to him, you feel you get a new insight. That's the kind of thing. I have personal experience of that guy coming and asking me some questions in topology because I was considered the local expert in topology at that time. And then I end up finding that he has more interesting things to say than I have to him. So, despite that loss, TIFR has continued to produce research of very high caliber. One piece of superb research that caught the limelight was the exploitation of the concept of Frobenius splitting by Vikram Mehta and A. Ramanathan. This was in the 1980s. I must mention Shravan Kumar. He has done things in diverse areas, but the resolution of the so-called PRV conjecture is one of the outstanding pieces of research to come out of TIFR. This PRV conjecture is a conjecture by three Indian mathematicians, Parthasarathy, Rangarao, Varadarajan, and the Westerners find it too difficult to make all those three names, so it's called PRV conjecture. The conjecture was made in 1962, something like that. This guy proved in the 80s. He too left TIFR in the 90s, so he has done interesting work, but I'm not going to not work in TIFR, so I will not talk about it. The 90s saw the academic leadership pass on to younger people from those who had joined TIFR. I mean, in the 90s, I was still floating around as Eminence Greece, if you like. And so I was still looked up to as the tradition in this country, so age matters a lot. But then towards the end of the century, I was retiring, doing things other than mathematics. So younger people had a chance to come to the fore. Dani was there, and later new leaders were Deependra Prasad, Srinivas, and T. N. Venkatramana. Deependra Prasad left the TIFR just 2 years ago, or a year ago or something. Srinivas and Venkatramana is due to retire in February, and Srinivas later in June or July, something like that. And these three good guys are as good mathematicians as any that the school have had. They don't have the same kind of image some of us in the earlier generation had, partly because mathematics has become different. In the sense that, in the old days, I worked in league groups, but people working in topology, working in algebraic geometry would know my name because everybody kept track of everything that's happening. That is no longer possible. The fields have become so vast individually. So if you ask someone outside algebraic geometry about Srinivas, they may not know. In the old days, it was not like this. So we had therefore a bigger image in some sense. These guys are just as good as we were, but they don't get that image. It's unfortunate, but I suppose it is the way things are developed. There's nothing you can do about it. Deependra Prasad, for instance, he works in automorphic forms, and he made a conjecture in his thesis on which there were at least two conferences in the recent past. The conferences are devoted to the Prasad's conjecture, actually called Gross Prasad conjecture, because two people were involved. Gross Prasad conjecture is something which he made essentially as a graduate student. And that there are two seminars in the recent past on that subject. It's not a resolved conjecture. Srinivas is an expert in algebraic geometry, but not the kind which Nathaman and Seshadri initiated here, somewhat different, and he has done excellent work there. And he wrote a book on K theory, which has received much adulation. I know what's the word, but I'm not kidding. Maybe the word is there. Yeah, Srinivas' book has received many accolades, has been received with accolades. In fact, it was published by Birkhauser, and a leading mathematician by name Sayre was very annoyed with Birkhauser's bringing out of the book. He wrote to them saying that it's such a good book and you have done such a bad job. So, so goes the story. Okay, Deependra Prasad works in number theory. A conjecture he made early in his career has been made the subject of several conferences in the recent past. Venkatramana was my student and has been the main person keeping activity in my area alive and kicking in TIFR. He has done very nice work. There are other younger people performing at a high level and maintaining and reinforcing the standing achieved by the School of Mathematics in the 60s. But I have only a faint acquaintance with some of their work. My apologies to them for not saying anything about their work. I think I'll stop with that. Thank you for how much I overstepped.
Thank you, Professor Raghunathan, for that wonderful seminar. It was indeed exhilarating to listen to you and all the anecdotal details about all the different work. Thank you very much. So I have now the privilege to request Professor Avi Hosur. I think all of you know Professor Hosur, but Professor Hosur served in TFR for 45 years. After that, he was also director of University of Mumbai Center for Excellence in Basic Sciences. He was the convener of National Facility for High Field NMR. Currently, he is associated with TFR Mumbai, IIT Mumbai. His research has been in the area of NMR. And all of you probably know he is one of the most popular when he was taking graduate students. He was one of the most popular ones, and there was a queue of who will leave and who will join him. So, Professor.
Okay. Thank you, Andre, for your kind introduction. It's of course a great pleasure to be here again and talk about the evolution of chemical science in TIFR. Is of course a great challenge because chemistry, as all of you know, is a subject which actually is quite encompassing and goes all over all kinds of topics. And certainly I cannot claim that I can do justice to everything of that one. I will try to do my best and cover the history and try to cover the extent to which I can understand the current research which is going on. So can you start this, please? Yeah. Excuse me. Nice. TIFR Landmarks 75. So this is the pointer. Yes, okay. So I have tried to collect information from the archives as much as I could, and I also tried to collect information from the colleagues in the department and try to put it together in a compact form. And of course, being the last speaker of the session, I can possibly go on till the till the cultural program. But I will try not to do it. There is a dance program. Okay, here it is. So we have this, as I mentioned to you, the chemistry lies here in the sphere of knowledge. You have the maths here, physics, chemistry, and biology. It has an interface, chemistry has interface with both chemistry and, oops, what happened? Huh? Okay. Okay. So you have this interface with chemistry. Chemistry has interface with the physics on one side, biology on the other side, and maths has interface with everything. So you need to have all of them. So you need to have math, physics, chemistry, biology, all put together to make it a good science. So research focus at TIFR has been continuously changing because you have to remain in the forefront. As the science develops all over the world, you have to keep changing yourself, look for new projects, look for new problems, so that you're always with the frontiers. Members of the group regroup. So because as the subjects change, you'll have to regroup yourself, put together the expertise, and then you can solve a consolidated problem. New faculty are recruited considering the emerging fields. So this has been the strategy which has been adopted at the department and of course probably at the institute as well. So this is a successful story, and I will try and give you hints of that kind of activity in the next few slides. Okay, the beginning is of chemistry at TIFR. This is the statement from Homi Bhabha, the visionary he was. And he wrote here, nuclear magnetic resonance is not, in the strictest sense of the word, an electric paramagnetic resonance, he said, certainly not nuclear physics. At that time, nuclear physics was the main theme of TIFR. And these are, however, techniques with great impact and application in chemistry, solid state physics, and biology. It is therefore an appropriate field for the institute to consolidate and develop. And Dharmati has the ability to and drive to lead the program. He is certainly a field with great promise, and Dharmati has in his field very wide and extensive international contacts, starting with the close contact with Felix Bloch. These relationships are of great importance for himself and his students, and thus for the institute. There is a history here that this is Pandit Jawaharlal Nehru, of course, Homi Bhabha, and this is Dharmati here. Homi Bhabha got Dharmati from Felix Bloch, and Felix Bloch had won the Nobel Prize. Well, he had not won the Nobel Prize yet, but he was the discoverer of the nuclear magnetic resonance in the liquid state. And Dharmati was associated with Felix Bloch. We brought him here, and then he went there. Of course, he did something fantastic things, and that was the initiation of chemistry in TIFR. See here, this is the classic paper of Dharmati, which shows the discovery of the chemical shift. Chemical shift is the crucial element in magnetic resonance, NMR, nuclear magnetic resonance. Dharmati wanted, Felix Bloch wanted to measure the moment of tritium, and there was this student, Arnold, who was actually working on that one. And they were supposed to measure the magnetic moment. They thought magnetic moment of tritium or proton or whatever that is going to be something. And there will be one absorption line for in the resonance phenomenon. And Dharmati said, well, why not we put water? They said initially they put water, H2O, and want the tritium from there. But Dharmati said, for what reason one doesn't know, he said, let us put alcohol. So he put alcohol in the magnet, in the magnetic NMR experiment. The NMR experiment consists of a magnet, and then of course the receiver where you put in the RF coil and they get the signal. So he put alcohol there. And when you put alcohol, he actually saw three signals. See here, CH3, CH2OH. He got three signals. Felix Bloch could not believe this. He said, how can you have three signals for the proton? The proton is same. So its nucleus is the same. So how can you have three different signals? But there was a lot of debate, and finally they concluded, okay, it is something to do with the electronic environment around the proton. Proton is not a bare nucleus. It has electrons around it. So different chemical environments can be there, which can cause different chemical shifts or resonance absorption frequencies. And they got these three different lines. And so in this, CH3 belongs here, CH2 is here, OH is here, and their intensities are in the ratio of 1:2:3. This is precisely what happens when you have the number of protons different and all resonate at the same frequency. You have these three different lines. So this is the classic paper. This was the beginning of the chemical shift and entry into chemistry of NMR. And then at that time, so when Dharmati came, actually they started a group here, which was then called as magnetic resonance, but it was called as nuclear and electron magnetism. It was called the NEM group. Professor Vijayaraghavan was already there. Dharmati, Kanekar, Vijayaraghavan, Venkatraman, L.C. Gupta, S.K. Malik, G. Govil, and so on, so on, so on, so forth. Nagarajan is also here, and there were many more. So, and therefore, with this, actually, they started this activity here, and this was called as the nuclear electron magnetism group. And unfortunately, Dharmati died in 1963 because of he had a heart attack somewhere. So while giving it, and then of course, some differences developed, and then they split this group into two. One was called the chemical physics group in 1967, and Arun, of course, you can correct me if there are any errors in the in the history. And solid state physics group, this was Vijayaraghavan, Gupta, S.K. Malik, and so on, Nagarajan and so others. And then here's the magnetic resonance we had here: Kanekar, Venkatraman, Govil, Khetrapal, Prabhananda, M.M. Dhingra. And magnetic susceptibility, this was an area which was followed by S. Mitra. The Mossbohr effect, which was S.K. Date. Electrochemiluminescence, K.S.V. Santhanam. And microspectroscopy, Doreswamy and S.D. Sharma. Theoretical chemistry, theoretical biology, it was B. Venkatraman, G. Govil, Anil Saran. These were the people who were actually working in these areas. In those days, many of these people were actually coming from the training school. They would join the training school, then of course they top the training school, then they come here. Likewise, actually, Professor Govil came from there. And there are also others in the physics arena. And the emphasis at that time, during the first 25 years, I tried to collect this information from the archives and also from the book which was printed in the 1970. So the 25 years of TIFR, and the emphasis was on instrument building and using as much as possible, try to build instruments to be on the front line. And this was the first NMR in the country. This was the Varian machine, and Dharmati, Bhabha got it for Dharmati. This is the 60 megahertz NMR machine. Varian high resolution NMR spectrometer. Those are the only machine of its kind in the country at that time. There was no other NMR machine in the country. And then you know what were they doing with this? They were actually recording the spectra of organic, inorganic small molecules and molecules oriented in the limmatic phase. This limmatic phase, these were the liquid crystals. This was a Khetrapal's work. CL Khetrapal was also present here at that time. And Govil and Professor Govil and Professor Kanekar, they were interested in measuring the chemical shifts and the coupling constants with other parameters, which we will not talk into the details of those. They were also actually calculating the NMR spectra from quantum mechanical methodologies. So simulating the spectra, comparing with experimental spectra, and try to extract these parameters of chemical shifts and coupling constants. So this was the instrument at that time, and this was an electromagnet here, and this is the control. Electromagnet requires huge amount of chilled water supply to cool the magnet, otherwise it will become hot, and then of course it is not stable. Then all sorts of aberrations will happen in your spectra. And this was another instrument which was built here. This was the Gaui balance. Gaui balance, it's called, it's used for the magnetic susceptibility measurements. And with the magnetic susceptibility, you can determine the electronic structures of transition metal complexes and intermetallic compounds. Of course, magnetic susceptibility is very crucial in magnetic resonance. You can measure the magnetic susceptibilities in every molecule. In those days, of course, they were actually measuring on the transition metal complexes and intermetallic complexes. Samaresh Mitra was the primary faculty during that time. And then the ESR spectrometer, this was Professor Venkatraman's baby. So they were actually they built this instrument using electromagnet here, and they were using this to measure free radicals. ESR means electron spin resonance. You need a free electron here, and the electron spin is used as a magnetic resonance probe. And you have ESR spectrometer. They were measuring C13 hyperfine splittings in free radicals and photochemical and kinetic studies. That was what was going on. And look at the instrumentation here. It will occupy the whole room. If you see today's spectrometer, they actually sit in a small corner. So this is occupying a whole room. And they were, this is all built here in this institute. And this was done by Professor B. Venkatraman and Professor Prabhananda. Prabhananda actually shifted later on to some other areas, but in those days, actually, he was with Venkatraman, and primarily he was working on the ESR spectrometer. And this is Doreswamy and Sharma. These again people came from BRC. They were working on microwave spectrometer. This was the initiative from Professor Venkatraman, and they said they work on a rotational spectra of molecules. Incidentally, I remember people talking about something like astrochemistry. What were they measuring? They were actually measuring the rotational spectra of small organic molecules. Maybe they are present in the galaxy or somewhere. So whether the spectroscopy can help in detecting any of those ones. So therefore, they were actually doing rotational spectroscopy, and the instrument of the microspectrometer was built here. And the molecules in a gaseous state, dipole, and quadrupole measurements. This was Doreswamy and Sharma. And then they had this another X-band ESR spectrometer, the rotating magnet. And this was actually so that you can rotate the magnet for oriented magnetic field in a particular direction you want. And this was used to measure relaxation times. So this was done by Professor Venkatraman and Professor Prabhananda, and they were using this to measure spin lattice relaxation times in the microsecond region of organic free radicals and anisotropic studies in the solid state. And look at the effort of the instrumentation here. And this is the electrochemiluminescence. This was Santanam. Santanam was actually measuring the emission during electrolysis from photoexcited molecules, the heterocycles. So this was used to understand photochemistry and that happens in your molecules. And the instrumentation was built in this year. So the emphasis, why I'm showing all of this is that emphasis at that time was to build your own instruments as much as you can. So you choose your projects, choose your problems, of course, build your instruments to be on the forefront. However, of course, they could not last for too long. That's a kind of a tendency. If you have for too long, then so surely you are getting lost to the commercial market and you are not able to produce outstanding science. That kind of a thing actually came in the way. Okay, and then that was the experimental work, and then also this area called theoretical biology. And theoretical biology here, what people were trying to do is predict shapes of peptides, proteins, the nucleic acids, and lipids by calculating their energies using various methods. And this is, of course, you use your different kinds of methods were used. One of these called the classical potential functions. This was initially started by G.N. Ramachandran in Bangalore. He used classical potential functions to calculate the energies of a dipeptide to find out the conformations of peptides in the find out the minimum energy conformations. And then Govil and Saran, of course, they used different methods. They used quantum mechanical methods. Parisar power Popple, these are approximate methods. These are not rigorous quantum mechanics. These are actually quantum chemical methods, which are lots of approximations, various kinds of approximations in the integrals. Of course, the integral approximations are also based on certain experimental data. So you use these methods, complete neglect of differential overlap called C and DO, intermediate neglect of differential overlap, I and DO. These are SCF methods, okay, the variation principle methods. But then, of course, you have this one more. This actually will take very time consuming. At that time, you used to do these calculations in a computer called CDC 3600. So it was such a slow computer by today's standards that you submit your data with a punch cards, you would get the results after 2 days to find out that there is a mistake in the format of your data. So, and then you submit it again, wait for two days again, and that sort of things used to happen. This is a very painful exercise to do these calculations, but nevertheless, they were quite successful in achieving this. And this was the PCIL or perturbative configuration interaction using localized orbitals. This is the perturbative methods, relatively faster, and you can do it relatively easily. And search the conformational space or minimum energy conformations. Shapes play important roles in biological functions. Of course, after all, why do you want to determine the shape, the conformations? Conformation means the geometry of the molecule, how does it look like, what are the active sites in there, where the interactions happen. All of this is very important. So for that, you need to do the conformations, and these are important for biological function. This was primarily followed by Govil and Saran. And so this is the kind of a approach. So this was the Ramachandran map. This is also called the Phi-Psi map for the peptide. You have the peptide going like this. You have particular torsion angles here, which are crucial. This is called the phi torsion angle. This is the psi torsion angle. Is the relative magnitudes of these torsion angles which determine the geometry of the whole molecule, the shape of the molecule, peptide. And you have this also called as Phi-Psi maps or Ramachandran maps. Orange regions indicate the allowed regions, or rather one should say, this, if you are anywhere here, they are not allowed because they are sterically out, they overlap. If there is a steric contact force, it is not allowed. So therefore, if you get a molecule which has phi torsion angles in this area, it is a disallowed conformation. If anybody, even today, if it determines the structure by whatever method, crystallography or NMR or whatever, if you get a value which is falling here, is incorrect. You'll have to go back and look at it once more. or find a justification why it has happened under those conditions. So therefore, this is a very, very fundamental discovery. Actually, many people felt that, okay, G. N. Ramanandran should get the Nobel Prize for this, but it so happens that, okay, you don't get everything. And then based on these angles, you have the different kinds of structures for the proteins. This is called the primary structure of the protein, which is the sequence of the amino acids. And as you know, there are 20 different types of amino acids. You connect them one after the other here, and then you call a polypeptide chain. This forms the primary structure, and these ones can arrange themselves in a particular manner to have certain interactions here. These are hydrogen bond interactions between two chains. One chain is running like this, other chain is running like that. And you have interactions here which will hold them together. This is called the beta structure. And here it is a chain which is running like a helix. And the interactions here actually hold the molecules together. It provides stability to the molecule. This is the helical structure. And then, of course, you can have combinations of these to form a tertiary structure where your helices and beta sheets together. And then, of course, the structures of such can organize themselves in a more elaborate way that's called the quaternary structure. So you can have structure defined at different levels, and all of these are important to understand. And similarly, on the nucleic acid side, nucleic acid is your genetic material. Typically, one knows that it is a double helical structure. You have two strands running here, go in the opposite directions. And this is called the bDNA. And the later discovery in 1979 was the zDNA, which is the left-handed DNA. So the chain runs in the left-handed manner here, whereas these are right-handed helices. And two chains are held together by hydrogen bonds between base kind of a base pairs here. And that is the genetic code. So the sequence of the bases is important, and that is your genetic information. So we'll not go to all of those details. But at the fundamental level, the structures of these, the backbone structure is determined by these kinds of torsion angles here. This is the molecular structure of the DNA. You have the sugar ring here, the phosphodiester bond here, group here, then there's the sugar here, and then it goes on like that. And at this point, you also have a basis attached. There are four kinds of bases, which are called as A, T, G, C. The sequence of these bases is the genetic information, and these bases pair themselves here, A pairs with T, G pairs with C, and that is what is responsible for the replication process. Okay, and here these are so-called the isoenergy contours. So what are the allowed energies, allowed conformations, and you plot here two particular torsion angles. This is omega and omega prime. You plot the two torsion angles here, and what are the allowed conformations? You see it is only this much area which is allowed. Not even this actually is 5 kilocalories or 3 kilocalories per mole. You have very little populations. So if it has to be allowed, it has to be below 3 kilocalories per mole, and you have mostly in this area, this sugar geometry is, the phosphodiester geometry is allowed. So these are the values which are present in all of these. It's written here, the structures, all RNA structures, so the DNA A, DNA B, they are all present in this area. So this was determined by the classical potential functions. Okay, there was also analytical quantum chemistry, which was happening. There was a theoretical biology, there was theoretical chemistry. We also had here theoretical chemist, Ramakrishna Ramaswamy, and he actually collaborated with Deepak Dhar in theoretical physics. And he was actually a non-linear chaos process, so chaotic process. So he was actually interacting with Deepak Dhar here. And I also happened to do something of analytical quantum chemistry here, quantum mechanical theory for transport across biological membranes. The idea was to choose the membrane as a potential barrier and calculate the flux through the potential barrier. And interestingly, this was used by some other group in Spain. They derived the laws of thermodynamics, irreversible thermodynamics on the basis of this theory. So that was something which is quite satisfying. Okay, so that was for the first 25 years. And what happened next? After 1975 onwards, this research areas continued, but actually took a different shape. And now, because the technology had developed, you had better equipments, more equipments, all kinds of things happened. Then the research could be classified into these particular areas: molecular biophysics and structural biology, bioinorganic chemistry, chemical dynamics, materials chemistry, electrobioluminescence, biochemical fuel cells, molecular electronics, theoretical chemistry. I've colored them here, and the same kind of colors are present here to identify the faculty who are doing in those areas. I don't want to go through the whole list, otherwise it will take a lot of time. And certainly I will not be able to describe achievements of all of these people in every area. Here my objective is to sort of list the kind of areas, how the progression has happened, progression of science has happened, progression of chemistry has happened in the department, and highlight some of those things which are, well, not too many, because otherwise there is danger of leaving out some of those in the process. Nonetheless, I will just say that the techniques which were used are magnetic resonance, laser spectroscopy, mass spectrometry, calorimetry, circular dichroism, AFM, TEM, IR, Raman, etc. And the department has made pioneering contributions which have enriched our knowledge of basic chemistry and chemical principles of biological function. And once again, there was an emphasis on instrumentation, building. Indigenous equipments have been built for supersonic jet spectroscopy. This is actually the work of Sanjay Vatagaonkar, and he is not here. He has his daughter's wedding recently, so he's quite busy there. Fluorescence correlation spectroscopy. This was actually the one which was built by Sudipto Maiti, who is the current chair of the Department of Chemical Sciences. Multiphoton imaging also was from him. The T-jump was actually from Professor Prabhananda and G. Krishnamurthy. GK is here. And these were done for the kinetic measurement, to do the chemical kinetics, study the kinetics of enzymes. And to name a few major ones. Again, then of course, the National Facility for High Field NMR, established as members of the department, is now an acclaimed international NMR center. This was one of the major achievements. Actually, it served not only the Department of Chemical Sciences, but the whole country in a big way. So I would like to spend a little bit of time here explaining these ones, how it has gone on. And the Chemical Physics Group was renamed as Department of Chemical Sciences or DCS in 1997. You know, the department has been going through review processes as other departments. Actually, the whole institute is going through the review processes, and every now and then, of course, there are inputs from the various reports, and these actually have influenced also the choice of the projects for the subsequent years. And so evolution of NMR at DCS, it started, as I said, from Dharmati, and the Professor Vijayaraghavan's group went into the solid state physics group, and there it was the wide line NMR, and L.C. Gupta, Sampath Kumaran, Grover, these people are working in the wide line NMR group. And I'm not dwelling into that one. I will focus mostly on the things which were in the chemical sciences, which is mostly high resolution NMR here. So high resolution NMR started with Dharmati. Then the first 500 megahertz spectrometer was installed in TIFR in 1983. And this is a big contrast to the 60 megahertz magnet which was there, which I showed you earlier. 60 megahertz magnet was an electromagnet with occupied a huge room, and this 500 megahertz is a superconducting magnet, stays in a corner like this, and your console sits just adjacent to it. Then, of course, the whole technology change was there. Of course, you could not have kept pace with that sort of a technological development. And then regularly the system was upgraded to keep it state of the art. Then in 1995, a 600 megahertz NMR spectrometer was installed. And why did this happen? Look here. The research focus has been changing. You are initially with small molecules, 10 atoms, 20 atoms, 30 atoms. And slowly you are moving towards complex large biomolecules, proteins, nucleic acids, membranes, in vivo, metabolomics. The whole area which was being developed. And therefore, they required these sophisticated equipments, and these were acquired by TIFR. Of course, I must say that the government of India has a great support for this facility. All the Department of Science and Technology, Department of Biotechnology, CSIR, all of them came forward to support this and funded to installation of all these spectrometers. Upgradation of the 600 megahertz console, installation on 800 megahertz spectrometer with a cryoprobe, and then, of course, in 2006, a new building was built to accommodate all of these spectrometers that is standing today as National Facility for High Field NMR. And the people who are associated with that, they are all listed here. Of course, we need not go into the details of all of those names here, but they are there for the record whenever somebody wants to see this. Okay, so this was the first 500 megahertz NMR spectrometer. You can also see outside on the display there. People are trying to identify what this photograph is. So I said, okay, this is the NMR spectrometer. Unfortunately, this slide is not very sharp here in this. So, but this is the magnet. This is the 500 megahertz superconducting magnet. You compare this with the 60 megahertz spectrometer, which I showed you in the beginning. And this is the console. So therefore, absolutely clean. And once you charge this magnet and you put liquid helium, keep on putting liquid helium, you don't have to worry about anything else. The temperature remains the same, absolute perfect homogeneity. You have the homogeneity of the sort of 1 in 10 to the power 9, sometimes 1 in 10 to the power 10. That level of homogeneity you have it, and therefore you can get very sharp lines in your NMR spectra. And this is the NMR facility, which was new building which came up in 2006. And with this, we could accommodate all the spectrometers here. And now this is the inauguration of this building. This you have here JJ Bhava, and of course all the big people are here in this. You can see Shovo here, and Professor Vijayaraghavan who is here. Shovo inaugurating this. This is Professor Khetrapal. Then you have Professor Govil here, and the other members. And Anil Kumar is here. From all over the country, people had come for the inauguration process. And this is the 800 megahertz. This was the highest field available at that time anywhere in the world. And this is the pumped magnet, and this requires very careful management of the NMR system. The technology is still developing. We should continue to maintain the technology and keep it state of the art. And it was very interesting to see JJ Bhava was so curious to know what was happening, and so he is explaining to him. But then we also explained in some other pictures later on. And this is one in the same picture a little bit. This is the 600 megahertz. Now it is inside there. That was also inside. This is 800 megahertz spectrometer. Now this is a 500 megahertz wide bore magnet, because this now we entered into the solid state area, solid state physics, solid state NMR. And this was the wide bore spectrometer which was obtained. The success of the national facility prompted DST to suggest expansion. What I mean success, not only the good research what you do, but also the service you provide to the rest of the country. Because we said this is the only place where there was facilities available for every researcher from across the country to come and use it. And therefore they were all coming, the service was provided, no charges, some charges, but of course you can pay some charges, otherwise no charges. So that was the service which was provided, and to serve the nation even more. And they said, okay, why don't you expand it? I said, okay, at that time, that okay, where is the space? I don't have a space to expand it here. If we got more spectrometers, surely we will want to have it, but there is no space. So we actually made a proposal to make an NMR center elsewhere. And at the same time, this proposal for the TIFR Hyderabad came up, and then the land was given in Hyderabad. And it so happened that, okay, this could be shifted. This new center could be created in TIFR Hyderabad, and MK is now there taking care of all of that. And that is developed, and this has played a major role in the creation of TIFR Hyderabad. Now, this is actually a kind of a picture which shows the evolution here. All people, see, this was in the 1974. This is Felix Bloch here. TIFR organized an NMR conference in 1974. This is called International Society of Magnetic Resonance. It was held in this hall. This particular, I remember this. And Felix Bloch is here. There is Schlichter is here, and all big stalwarts. They were all present here. The T.P. Das was here. T.P. Das was a big name that time. So, and Felix Bloch visited this NMR labs, and this is Richard Ernst here. And I see this Richard Ernst, Chidambaram here, Professor Govil, this is Professor Khetrapal, Shobo, and this is JJ Bhava, this is Mustansi here. Then this is Malcolm Levitt, who is actually from UK, who came here. He keeps coming here. And here you have Anil Kumar, this is Kurt Wittrich, and as you know, all of these people got Nobel Prize. Kurt Wittrich got Nobel Prize, Richard Ernst got Nobel Prize, okay, and Felix Bloch had got Nobel Prize. And Schlichter is here. Of course, Purcell was not here at that time. And the first announcement of MRI, which was called as gigmatography, was made on this stage. This was with Paul Lauterbur. He was giving a lecture in this platform. And this was taken at a meeting. It was a summer school which was held here in TIFR. And this is the standard place where we take pictures of all of those. And this is Kurt Wittrich here and Richard Ernst here. And at that time, of course, people were surprised at how did you get both these Nobel laureates on the same platform? I said, they are there. So how did you manage to? I said, okay, don't ask me that question. They accepted my invitation. They have come here. We are very happy. So you be happy as well. Okay. So research at the NMR facility was, this is the physics, chemistry, biology interface. And here, Professor Vijayaraghavan, you can see here, he played a very major role in the establishment of the NMR facility. He was all supportive for us to provide any kind of help that was required, and liquid helium, liquid nitrogen. And this is Imam Sharma, who is an FRS. and this is Professor Khetrapal, Professor Anil Kumar. These are all the stalwarts of NMR community in this country. And the areas that happen here, the nucleic acid structure and dynamics, peptide protein structures and dynamics, protein folding, metabolomics, drug design, in vivo, NMR methods, solution state, and solid state NMR. And solid state NMR started with the appointment of P.K. Madhu, who is also now in the leading the NMR group at TIFR Hyderabad. Okay, now this I will just show you one of the major achievements here. We're using this. We had 5 minutes. Which slide? Okay, possibly 7 minutes, 8 minutes. Okay. So this is one of the major accomplishments, which was I just want to show you here. This is the largest protein self-assembly elucidated. This is the size of 20 megadalton. We are talking about 10 kilodalton or even less, 5 kilodalton, things like that. That is the kind of a size which one was working on. Here is an achievement which shows several megadalton size protein is associating into a several megadalton size aggregate. The mechanism of that was elucidated here using our facilities that was here. Of course, this required a lot of methods development, solution state and our methods development that was preceding this. It allowed us to calculate this and showed us how association can lead to the formation of a rope-like structure. This is by protein, which is called as dynamin, which is involved in endocytosis process and biological function. We will not go into those details, but point is that this was the first one to be demonstrated that with the protein getting folded, it is getting associated and forms of rope-like structures with the self-assembly. Okay. So in that I can probably skip this. The result of all of this, I don't want to go into the individual accomplishments, but all these people get recognitions here in the country in terms of various kinds of fellowships, with awards and things like that. We will not go into those details here, but nevertheless, the research was very well recognized by this Indian community and the international community. And this was able to do many international conferences to India, overcoming stiff competition. ISMAR meeting in 1974. This was the International Conference on Theoretical Biophysics in 1980. International Conference on Magnetic Resonance in Biological Systems twice, 84 and 2005. International Biophysics Congress, IOPAB in 1999. Symposium on Recent Trends in Biomedical Research in 1999. Symposium on Advanced Bioinorganic Chemistry 2009-2017. Of course, a large number of national conferences have been organized. Now, I come to the current faculty. The current research, last decade, as I mentioned earlier, there's a lot of people have been recruited. They are promising new areas of research. And now, the good thing is that all of their research, although they have the individual projects, they can be grouped into certain areas. They themselves are grouped, right? The molecular biophysics and imaging, and these people are involved in that. Maiti, Koti, Ancona, Dasgupta, Venkatramani, Shamla Mazumdar. Theoretical computational chemistry, Venkatramani, Vora, Vatgaonkar. Chemical biology and synthetic chemistry, Ancona, Dasgupta, Polshetivar, Kushlani, Maiti, Patra. Bioinorganic and biomimetic chemistry, Shamla Mazumdar, Kona Datta, Malay Patra. Nanoscience and catalysis, Kushlani, Dasgupta, Shamla Mazumdar, V. Polshetivar. Chemical physics and dynamics, you have Maiti, Dasgupta, Vora, Venkatramani, Mazumdar, Vatgaonkar. Notice that each one has his own project, but they are such that they can be grouped into others, they can collaborate. So that is a very good idea. So that you can go ahead with these contributions. The wisdom of each of these persons can contribute to the development of a great science. And indeed that has happened. And here are the individual achievements which I want to show, individual projects which they have. This is of Sudipto, as I mentioned to you earlier. He is one of the senior ones there. Sudipto Maiti and Shamala Mazumdar, these are the most senior ones of this. And Sanjay Vatgaonkar is already super innovated. And we developed several types of biophotonic tools to probe interactable problems. Some of these instruments have become high-tech commercial instruments here. So this actually is a high-tech commercial instrument. And Sudipto, I know, he actually conducts workshops regularly to teach how to build fluorescence correlation spectroscopy spectrometers. And he has also donated several of those to the individual groups in other parts of the country. And important publications are coming out here from this. And this is Amartya Bose on focuses on using formalisms of path integrals and semi-classical mechanics to derive computational frameworks that render specific simulations feasible. And this, we will not go into the technical details. In fact, these were the slides which were prepared by them and given to me. I just show it to you here for your benefit. You can follow it up later on. to the individual exercises. Okay, this is Jyotishman here. So he is engineering molecular chemistry, which drives solar energy conversion. Okay, research group that uses time-resolved laser spectroscopy to develop new materials and chemistry paradigms for solar energy conversion and photocatalysis. So they have very important, very nice publications there. There is indicated that the photocatalytic cycle has the various steps. You start with the different molecules. Okay, you have the radiation coming here, then it generated ion. Okay, so and then you have this ion goes out. Okay, radical is created. Of course, you have the aldehyde here. Anyway, so these are all details, and the designing new chemistry, that is agenda what they have, and this is the instrument which has been built in the lab, which of course uses lasers and so femtosecond lasers. And this is Ankona Datta. She is a chemical biologist. She actually develops molecules, identify biosensors to molecules, and this is a group there. Track essential biomolecules to second messengers in vivo. The ultimate aim is to apply the tools to visualize and track crucial small molecules and ions involved in regulation of essential life processes like cell signaling, autophagy, and neural activity. The modus operandi is to design and synthesize selective fluorescence and magnetic resonance imaging probes that can image target molecules in living systems. And this is Deepa Kushlani. She is a materials chemist. She actually joined in somewhere in the late 1990s. And her objectives are here: capture solar energy, photovoltaic cells, storage of solar energy. These are pictures of the same one, but the aims are here: conversion of solar energy into chemical energy, formation of useful chemicals via photocatalysis, pollution remediation, conversion of carbon dioxide via electrocatalysis. So these are the specific details of the individual molecules and individual analysis that happens in these ones. She was invited to write a review article on all of these areas. Okay, now Koti. So he is actually a graduate student who is a product of TIFR itself. And of course, he diversified into other areas after his PhD. And during his PhD also, he did outstanding work. The following are the research interests: investigation of mechanical behavior and functional role of different classes of proteins. So he actually connects these molecules and puts a force, mechanical force, and how does the mechanical force affect the performance of the structure of the molecule. Engineering novel proteins with diverse mechanical functions, elucidation of mechanical unfolding pathways, and the relation with biochemical pathways. Development of novel single molecule assays for protein DNA, and protein RNA interactions. Shyamala Mazumdar, of course, he is one of the senior ones, bioinorganic chemistry. He has been working initially with small porphyrin complexes, and then of course slowly went into the enzymes. Biological enzymes which contain these porphyrin rings. Cytochrome oxidase is one of the enzymes which he has been working on for many years. The metalloenzymes currently being studied are variants of cytochrome C oxidase, cytochrome P450, and peroxidases. All of these contain porphyrin rings inside, and the structures of these, some of these ones are indicated here to understand the catalysis process, the mechanism of their interaction. And of course, he uses all kinds of techniques: NMR, high resolution mass spectrometry, and several spectroscopic techniques. And this is the new faculty. Of course, I have not met him. Chemistry under light matter strong coupling. These optical modes are tuned to electronic vibrational transitions of the molecule to generate polaritonic states. The role of polaritonic states in modifying physical and chemical properties of the molecule is studied. So this is a picture. Actually, these are the slides which they provided to me. So I am showing this for your information. Chemistry under light matter strong coupling. Okay, so this is another chemistry under light matter strong coupling. Oh, this is the same one. So that is only half of that has come, is it? Earlier. Okay. Malay-Patra synthesis, medicinal chemistry, and drug development. These are the keywords here. You have the drugs, you have the anti-cancer screening, cell biology, targets, in vivo efficacy and biodistribution, toxicology, pharmacokinetics and metabolism, antibacterial screening. So what it involves: synthesis, characterization, and bioconjugation. These are the ultimate applications there. Okay, and then of course the methods are here. So you synthesize them and characterize them for the purposes what has been mentioned. Okay, when topics are here, you have the chemistry biology interface here. It's on one hand you have the diagnostics, and the other hand you have the therapeutics. And this is nanocatalysis. This is Paul Shetiwar, and he is a materials chemist. Actually, he is one of those who actually created quite quite a name in by discovering this dendritic fibrous nanosilica. This is his invention, DPNS, and this actually has attracted worldwide attention, and people from all over the world are using this molecule for preparing various kinds of structures. Okay, it has applications like nanotraps for carbon dioxide capture, CO2 to fuel and cement at room temperature. They have the sand and beach convert CO2 to fuel, black gold as artificial tree, nano sponges of solid acids. This has great implications for the climate change, how to control the climate, and that is the and then convert carbon dioxide into fuel. So these are important applications, and you can see how the department has moved from one area to another area, continues to move from one area to another area to be on the forefront and contribute to the development on the fundamental side on one side and on the applications on the other side. And this is Ravi Venkataraman. He's a computational chemist. So he actually develops what is called as the protein charge transfer spectra to interpret these spectra. Computational techniques are used, and electronic molecular breadboards, okay, quantifying protein dynamics. These are all very in detail, they are themselves in detailed topics, so you cannot go into all of those details there. So molecular dynamic simulations, electronic structures, charge transport between molecules, and therefore these are all at the forefront, and a lot of effort is required, and this is one, it requires a lot of computational effort. Sophisticated computers are required for this, and today, of course, computation has become a keyword in many of the research areas, especially with artificial intelligence, the deep learning, things like that, that has become even more important. Yes, so this is probably the last one, and we have quantum chemistry group on CRS is a relatively young man, probably 1 or 2 years old. I mean, joining here. The group is developing quantum chemistry tools to understand the nature of charge transport in organic materials, intermolecular interactions where fundamental van der Waals scaling laws are not applicable, the nature of core electronic states, how they are influenced by weak van der Waals interactions. Understanding of these will develop better materials for solar energy capture and energy storage. Okay. So the department has been organizing workshops at regular intervals, schools at regular intervals. This is a whole list of those, which is, yeah, of course, you cannot read this, but I just say that, okay, there are so many, this is only a partial list. This is still not complete. Whatever I could put in one slide in reasonable resolution, I put them here. Okay, so with that, I will stop. So therefore, the trend has been like this, that you keep developing, you keep moving, your fronts keep moving, recruit people accordingly, and continue to do research at the front line all the time. That has been the main aim. So with that, I thank you for your attention. Thank you.
Thank you, Professor Osur. That was a very nice account of the past and also leads to what is happening now in the Department of Chemical Sciences. With this, we come to the end of this session. We break now. If I don't see any more.
Okay, so I'll hand it over to Prabhuji for the. So thank you, Professor Udge, for conducting this session, and also thank the speakers because they had to, really go through a vast material and take out the complete overview of the work. So thank you very much for both the speakers and also the chairman for conducting this session. We now break here. Basically, this session is over for the day, and now we are going for this cultural program, which will start at 7 o'clock. But right now we have tea break for almost 90 minutes. So please come here by 6:50 and please have a tea break. So thank you very much. Close.
Meeting and meeting and
Hello.
Hi. Leave. क्या बोलता है?
अभी डांस के लिए आएंगे।
हाँ,
ये वो डांसर्स आएंगे अभी, उनके लिए सब निकालना पड़ेगा।
वो निकालना पड़ेगा। हाँ, वो है वो लोग। हेलो मंजपा, सर आ रहे इधर? कोई नहीं है? ठीक है, बंद कर दो, कल देखेगा। हाँ, हे राम, कैसा बात है? अरे वो राम लोग किधर गए? हेलो, ये लेबर लोग किधर गए? इधर नहीं है कोई भी। हाँ, स्टेज पे कोई भी नहीं। हाँ, जरा भेजिए। हाँ, ओके। हाँ हाँ।
राम को बोला है।